也都 share screen。share 是那个
你是不是进错了？那为什么看不到那个screen？
我也不知道为什么是你这个是偏偏看不到。
但是我这个才是就是得 live stream 上去的。
我们那用你这个，用你这个。嗯，你给我发的是这个字幕，你给我发的是这个字幕，你给我发的是那个字幕链接。你再给我重新发一个字幕，先没有办法先开始了，对吧？
嗯，你现在让你这样子的话，那要不不直播？
你已经用这个，你告诉一下我你的这个字幕链接是什么？发的
这个送链接啊，我知道哪个送链接啊？
告诉你来自你的。
我看
If to begin right now, as there's some technical issue a little bit, we will be ready in 1 minute. Okay, everybody, let's get started. And thank you very much for coming to our workshop, the Science International Workshop on Visual Odometry and vision, computer vision application based on location rules. It's organized by you, myself, Brandish from Dover is here as well. Yan from Illinois State in Illinois Technology University. Nico City from University of Toronto, and China Tamaki from University of Delaware. So first, why we want to organize this workshop is always very important information to estimate the motion based on cameras, and as well as you want to know the location quite often, and your camera wants to access your location information from the video. So that gives us quite a lot of hints and information from the camera information and from the visual information that we want to know the location, yeah, and we want to use the location to support the visual information analysis as well. So there are many applications already. For example, in robotics, autonomous driving, and you can use the you can use the camera information to analyze the motion and to localize yourself as well as building the maps. And meanwhile, there are quite other applications. For example, you augmented reality, and you want to know the depth information, and you want to know the motion so that you can augment the graphics on practical vision. And in many different applications, for example, agriculture and in energy, mobile phone applications, in shopping malls, and even in the craft field, and you can find quite a lot of applications using UAV, using ground robots, even sometimes underwater robots for the odometry, for mapping, for localization, those kinds of tasks. So briefly talk about the schedule. And in the morning, there are two small sessions, and one is from 8:50 to 10:30. And that is the first session. We mainly composed by 3 oral talks as well as keynote talks. And after that, there is 3 keynote talks. That is the basic morning session. And after that, we will have the lunch and the poster session, and you can go to the poster to talk with the others. And they will also give a talk in the first 3 in order. So in the afternoon, we also have 2 small sessions from 2 to 3:20, and that is given by 2 talks. And after that, we have 10-minute break. We will have another 3 talks, keynote talk. It's a very tight schedule for today, and we hope you will enjoy the workshop and learn from the presentation. The first one will be given the talk given by a group from Senior Life as well as Technische Universität in Hannover, and this is from Germany. And after that, there will be Intel and the UCSD giving their talks, and as well as the last oral talk is from Zaragoza and the group from there to do the time motion estimation. So for all the papers, for all the 3 papers, and we accepted, we have a poster session. And the poster session is in the noontime, and is in the number from 438 to 440. So the first talk will be by Lars, and okay.
All right. Does the screen share? Okay. Yeah, perfect. Then welcome to my presentation. I'm Lars Hinneburg. I'm working for Spleen Lab. We are working on computer vision perception software for robotics in general. And I'm happy to welcome you to the talk. I'm going to present our paper, weakly supervised end-to-end deep visual odometry. And what is it all about? So the challenge is that deep visual odometry solutions require high quality ground truth data. And our goal was to enable efficient training on real world data sets. So in automotive and aviation, especially UAV sector. And the problem here is that the data set often lacks in terms of size and quality. So our solution is a weakly supervised approach that only needs RGB images and an estimated optical flow. The related work so far are well-known geometric methods like OrbSlam and TSO, supervised methods like DBVO that need end-to-end neural networks, and supervised loss functions that rely on good ground truth data. And then there are the self-supervised methods which yields good performance for single view depth estimation, but the total performance is substantially lower compared to standard VO approaches. We base our work on DPVO, shorthand for deep patch visual odometry, and the method improved accuracy and robustness. It achieved state-of-the-art accuracy using sparse patch-based matching between frames, and it was real-time capable. So with less memory consumption, we tested it and were able to run it with around 5 FPS on an Jetson Xavier, or with up to 30 FPS on an Orin. So it can be used on edge. But there are two big limitations. First, its dependence on ground truth data and the slow training. So DPVO relies heavily on synthetic data sets for the generation of dense depth data, which is then used to compute the optical flow. And the reliance on synthetic data sets introduces a significant domain gap. And we noticed that the computational cost for the co-visibility graph is really high between the frames, and unnecessarily high. So how we tackle this? What is our contribution? So the problem, as I already stated, is the dependence on dense ground truth depth data, which is used in DPVO. And our solution is, we have two approaches. The first one uses a monodepth to estimate the depth image from the RGB image. So we generate a depth image ourselves and don't need ground truth for this. Here we use feature depth, which was trained on Kitty image data. And the second approach skips the whole depth image part of DPVO and just uses a neural network to estimate the optical flow directly based on the RGB image. So we use GMFlow for this. Further, we introduce forward and backward consistency checks to eliminate occluded pixels. The second thing I already mentioned is the computational cost of the co-visibility graph. We noticed that the majority of optical flow values are near to zero between frames. Of course, in domains like autonomous driving, only frames nearby each other have an overlap, and therefore you can compute optical flow. And that's why we introduce a neighboring approach. So we only compute the optical flow for pairs of frames within a certain frame window. And here we use n equals 10 for our contribution. Here you can see the co-visibility graph for the Kitty scene 7, and this compared to our approach, neighboring co-visibility on the right. This is our proposed method. So we have two branches. The first one is A. There we use the optical flow network to estimate optical flow directly without the need on depth images. This is then used for DPVO training. And the second branch, B, uses monodepth to estimate the depth image, and then it's used in the normal DPVO training with the optical flow estimation based on the depth image. We evaluated our approach on Kitty, and here we trained our network on sequences 0 to 8, so and used, as usual, 9 to 10 and 10 as evaluation. And as you can see here, the dashed line is the ground truth, and our approach with optical flow and the neighboring co-visibility graph, as well as the approach using the depth image and the full co-visibility graph, results in very good performance. The green and the blue graph lies nearly directly on the ground truth. Here are some more numbers compared to other methods I mentioned earlier in the presentation. And you can see the small gap between the start and the endpoints for the sequence 9 of the Kitty dataset on the right. So without loop close, we are really close to the starting point at the end. So to summarize what we did and what we achieved, we proposed a weakly supervised approach that only uses raw camera images and generates the optical flow based on RGB images, and we then further only need ground truth poses. We achieved state-of-the-art performance on the Kitty dataset, and this empowers practical applications like mapless navigation in automotive and aviation domains, and reduces the dependence on high-quality ground truth data. So we are able to use real-world datasets more easily. Here I have a small video prepared. Now close, yeah. I think, unfortunately, the lighting is a little bit bad. Can you see anything? So we recorded some data in our neighborhood and ran the algorithm. If you're interested, you can check it out on the paper session again. We can have a look in detail with better lighting. All right. Then one small disclaimer, we also worked on a second CVPR challenge as part of the OmniCV 2024 workshop. And there we created a visual odometry data set. And we also launched a Kaggle challenge, which is closed at the moment, but we are going to reopen it again. So check it out and feel free to participate. And now I'm happy to answer all your questions.
We might have one or two questions. Any questions in the audience? Yes, go ahead.
How does it do it on the UAVs? You've trained on 15, not really. How much of you like doing
Yeah, so we trained and compared our approach on Kitty because it's the most used benchmark data set, and there are not that many. So the algorithms don't compare on any UAV data sets. So therefore, we use Kitty for now. But the same approach is applied already on drone data sets. Okay.
No question here.
You mentioned that you use RGB data set grayscale.
Sorry, could you?
You mentioned that you use RGB camera data set grayscale.
Yeah. Okay, that's true. That's a good point. So we're transforming it to grayscale, of course, for this algorithm. Yeah.
Second question, what are you doing the optical flow? Are you using actual values, or are you using some kind of conversion of the data before doing the
just as usual normalization for training neural networks. So normalizing from 0 to 1, nothing else.
Okay. But no gamma change. Have you published your result?
In this paper, yeah.
No, have you submitted your result?
No, not yet. Not yet.
I would be curious to compare how it is.
Yeah. So at the moment, we only use the ATE metric. So we have to use the Kitty metric again. for submitting to Qt itself. That's why we didn't do it yet.
Any other question? A minor question, what is the price for the challenge?
Oh, I have to check it out. I have it in mind, but I think around $1,000,
Okay.
I guess. Let me check.
Just want to advertise. Here's the challenge, here's the price, right?
Yeah. Yeah, I don't find it this quick. Challenge. There it is. So $1,000.
Okay. Okay, thank you very much. The second one, Simon. By the way, is Samuel here? The third talk, the third talk presentation, Samuel. Okay. I remember to log into Zoom, so that we will live streaming. Sorry. The Zoom. I just sent you the Zoom link if you remember.
Hello? Okay.
Probably can open your panel. Okay, see.
Okay, thank you all for coming to this talk. I'm presenting by GP, which is short for Bundle Adjusting Accelerated Neural Graphic Primitive. My name is Dainan Liu. My co-authors are Shangling, Jingpei Lu, Alexi Sudkov, and Michael Yip. Alexi and I are from Intel Labs. Shang, Jingpei, and Michael are from UCSD. So the main achievement of this project is to simultaneously optimize camera poses and reconstruct the 3D object from multi-view images 10 to 20 times faster than the baseline model BART without par or better quality for novel synthesis task. At the time of the development, existing neural representations or INRs have gone through a rapid development phase. This representation, in contrast to traditional explicit 3D representation, such as mesh, point cloud, and blob cells, has drawn a lot of attention due to its high quality performance in a novel view synthesis task. The model I'm referring to as INR, implicit neural representation, normally learns from a set of multi-view images as supervision with given camera poses and intrinsic information. Once trained, the model can then be used to implicitly infer what a novel view looks like from an unknown camera perspective. As a side effect by design, an estimated 3D object can be implicitly extracted through post-processing steps. There has been many faster implementations in this field. However, the majority of them requires one true camera poses. Bundle adjusting neural radius field, or BARF, was the first network that tried to optimize camera poses end-to-end. The BARF model is able to estimate the camera positional information with known camera intrinsics. While it can also achieve state-of-the-art novel view synthesis results. It supports wider use cases in comparison to normal INR. However, it takes hours to train. We propose a solution that combines the best of both worlds and enables the training of camera poses within an hour at minute scale with the same data set and problem set up with R, and relaxes the requirement for ground truth camera poses for INR. Now, before I dive into our method, let's quickly revisit NERF, which is a vanilla neural radiance field. NERF is the original first INR that introduced the concept of using position and view direction as the input of a neural network. The network could be a single MLP, which is multi-layer perceptron, and train it to overfit the one scene so that it is capable of output the color and density of the same scene and new viewpoint during inference. However, to better capture high fidelity information of the scene and improve the network's learning efficiency, the network does not just take position XYZ directly. Instead, they use a positional encoding technique with increased input dimension. As an example, if we consider an input as a set of 2D coordinates for visualization instead of 3D, and the sample along the 2D area shown here, we borrow the code from our studio to show that using 4 frequencies ranked from low to high for every coordinate, where for each frequency we apply the sine and cosine function, we would end up with 16 values for every set of 2D coordinates. Now, keep that in mind. I'll also give a quick introduction of BARF. The BARF model built on top of an NLP-based NERF, and they designed 2 toy problem for pose refinement. They concluded that the key solution for simultaneously pose estimation is to use a coarse-to-fine strategy, meaning that they want to encourage the network to learn coarse scene representation first, which help resolving large pose misalignment issues, then gradually transition to granular pose misalignment implemented. High fidelity representation so that we can define granular pose misalignment in later stage. The way that the open network is a pose misalignment is to gradually expose high frequency together, like a video recording, as we see here in the diagram. So visualize in one today. If you remember the key frequency theory example, here's the dynamic visualization for a maximum of 30 simulations. On top of the different frequencies, we also original input at the beginning as well as first input into okay. And then what point the first sequence starts. So here we will become the start. Making time of the simulation, which is that's when the first sequence started. And then the operating simulation, we talk about the that's when all the frequency they use. And so this setup is very common. And the rest of the frequency is just and the last component of our is activity, which is introduced by infinity. This is capable of reducing the pain sensitivity with very high. In high level, It literally divides the space into lower resolution grid and higher resolution grid. Here, the two examples, the blue is the lower resolution grid, and the red is the higher resolution. Again, hashes block cell registry of the nearest block cell for each species and treatment. This will set as vulnerable features. And these features, the hospital is fixed, and then continue to utilize the table. The output features again incorporated to be used as features of the space. Different features from different resolutions of the and then has to be calculated. Implement features are normally with resolution 3. Resolution is normally about 1500. The feature dimension approximately features are for the minimum. Additionally, the learning features that is given this in the dimension, which is a technical reason why we're using a much smaller dimension here for this, which facilitates translating. Additionally, learn that introduce the additional vision mechanism as dynamically telling and stages, which further introduces the resolution. Here we use the same set of features of the demo and visualize the features of hash study with feature size and scale in order to see the features in RGB and effect of the feature. So we use the here we use a level for the visualization. Like I mentioned earlier, these features are going to run throughout the process, but we are almost in the implementation. So putting together in order to see the first and middle of the model adjustment to the required, so you can just do it like that section. And based on the special properties of the features from the we designed a different portion strategy. One observation is that instead of doing outpacing features like in the house paper, we said it's first feature. And the closest first feature of that level. We find that an operates with the nearest of first features that are already used. Here we're using the nearest features with our first feature strategy for the system. In a European country, we expect these features to be relevant and transmitted. Our hypothesis is that due to the nature of the network features, the meaning of feature 0 is drastically different from feature 0, which explains the behavior after to other things. When feature 0 are now added to the resolution of small specification. Finally, we show that for process understanding, the results are also promising in variables with zero interaction. We are defined outside of the core area, which is factored on the first dimension, as part of the easy using a secondary method. We follow the same hypothesis with the experiment. We are given 5 hypotheses as here. We have the network to the medium, while also fitting into a high quality database neural. We show that the quantity working solution network with function coding combined to keep the information together with less noise and most other applications instead of putting everything together. And it was well with combo adjustment enabled. The person who registers a local in quickly is less than available system as one type of There's a vanilla social learning connection. DLCP may be to start that option learning process at very early stage, often at the other stage towards impact methodology. After introducing first design feature planning, I will find models and achieve better optimization. For speed experiments, we also follow the large experiment setup. Therefore, boundary pages are usually recommended historical and visually integrated. For real world boundary pages, it is identified as the initial solution. We show that without method, we can achieve clear instructions and developing quality with limited use here. So, for example, quality, we can use and accuracy, especially with our businesses, has its limitations. As the state solution is divided into different. The experiment is method and interpreting on the state inspection method by introducing the first animation is separate measure playing that goes on activity, yield better results overall for the service. Here we want to see this number of chemical-based activation and creation. A question is and making work. For those things, in order to do the function. However, for others, the chemical process struggles with the available optimum as the interaction between the country. So things such as room, birds, and the birds, the room without the clear distinction between program and problem. The performance of an individual is here's some of the limitations of the person. There is still clearly allowed to use for existing or boundary things that are seen. And of course, the problem setup for bars is pretty limited. And one thing, and the boundary synthetic is only allowed a limited amount of discussion. As the amount of years are very limited, and the boundary we are using to the system, instead of the global optimum. Similar to the unbounded thing, and even though it is initialized as a reality, it is still similar to the boundary thing in that the function places is not that far away from the reality. As the force is drift away from the reality, and the things can model and the thirdly, the chemical specific and non-existent experiments. There have been studies on how to apply chemical legislation and the organization with communication at the feedback. And so there are more indications as we can realize that. And so naturally, some of the direction is the direction. We are also aware of other options especially when the activation between the light and in the people in the both people, and we can achieve better quality results on the team. However, we think there's still value in GM. One such example is another research space, which is thanks for other adjustments that we can understand video instructions from the industry. You're probably aware of networks that optimize the optimal analytical techniques in the video. Here we're focusing on the problem where the medical solution network the entire students before going. And end-to-end optimizations and solutions can help us to maintain the seeing definition differently. We are open for collaboration to learn how this related values. So please feel free to find me in the budget section. And with that, I'd like to thank all the wonderful collaborators from the last team. And thank you all for your attention. We have to request them to next evening.
Yes, a couple of minutes for the question. Any questions?
ready?
I mean, it's half okay.
Oh, like I will be using a phone on the door. I can turn it I think based on my weight, I was going to based on my weight. I think they use it, oh, so that's, so one of the activities my favorite is because for the recycle related to cycle reuse of the cycle of the and then when things fall out, they use some of the issues of the home to the future and then so that's we continue to have into every forward construction experience. The reason why the construction is really taking is because a few years already helped and through the point of the series, it's not kind of work in this area. So that you can have a better readings
Okay, probably we don't have much more time. Yeah, thank you very much for doing. Okay.
So, this is first, we consider the three thermostats. This is the physical thermostat. This is the total derivative. If we have to find the occupied place, we get, and also like the partial derivative, and have which is done because we consider one that directly differentially we cannot consider. So we consider here we have done the time. We know consider the ability, but actually we will consider this ideology and this ideology first we will learn to find the reality and so from the first time we consider this for data our residual associated with the triangular velocity, consider white noise and also variability of the virus. At second point, we have a life change in the virus. As I said, we consider that maybe about the issue of the virus and then for that, I will not be able to do that. I will do that. And in this time, here we consider different data values of the level. If we start out with the lower value, we need to memorize the value one value where we study. We need to consider this quantity and value of the one. For example, let's say the related and for that, we get so finally we have to up to the time So So, depending on the value of the regular, the value that we have value, so, for example, here we can see one equal to the three one, and this is that and also one. So we have another thing we have to do that here, and but we can also consider only one. The last thing is going to be considered also one. So, this is like a river, while this is like we start from the first part, we have to concern the information. So, graphically, we can reflect that this we can see here. Now, for example, we have two points here, and we can see by the definition but when we start the third that is part of the information. So this information related to but the problem is how time. So for we take a look on the central area of the function. Somehow the report information about how the environment affects each other. So for this, we go to the first, alpha is the part, and we compare the time. So for this, we have the first graphically, apply the system that is the of so here we have found the value term that we will put in the second part of the optimization. This prior term is also being valued from the start and the start, which is the full sum of the value of the optimization and the value is the value. Okay. So, after the time, we can see here we very high we can see that While we react to those. So, we have developed a novel camera motion optimization based on LCD generation systems. Our knowledge camera value in order to obtain the kind of system and then we also have developed a term optimization that consider what is low, the zero, and also I will evaluate the zero, we also use the contact of the equipment, we have every space of the system, we have the carrying the second equipment, and space, and we are not
We have time for one question.
Yeah, we for the gravity parameter, we use only two. It's not a 3D vector; it's 2D vector because we consider also the length of the gravity as known, and we provide an initial guess, and then gravity converge on the one.
Okay, this is a short one. Another one, if you have one. By the way, what is the window size? And I know the window size determines also the accuracy as well as the speed.
Yeah.
And what is the window size you chose?
For example, in this table, we choose 2 frames, and 3 frames, 4 frames, and 5 frames.
Okay, and which one do you can conclude is the best one? The best trader, let's say.
We only try until 5 frames, but from 4 and 5 frames is enough for our system.
Yeah, makes sense. Yeah, sure. Yeah, thank you. That is our presentation part, and after that we are coming to our first invited speaker. Sorry. Oh yeah. I just need to share screen. Okay. Let me introduce our first speaker, Dr. Yunxiang Lu, and he's a professor in Purdue University, and he was also director of Dorm Marketing Engineering and Center at Purdue University. He's a IEEE Fellow, ACM Distinguished Speaker, Distinguished Scientist, and Distinguished Visitor of the Computer Society. His research topics include efficient computer vision for embedded systems, cloud, and mobile computing, and he was also the leading organizer of the IEEE Low Power Computation Challenge from 2015 to 2023. And as a special thing here is Professor Lu provides 2 books and as a gift for the first 2 people who asked him the questions. So yeah, welcome, Dr. Lu.
Okay, thank you very much. It's an honor to be able to speak here. So today I will talk about why it's important to have efficient computer vision for edge devices, and I also share with you some of our work on this topic. All right, first, let's start today with the test. Okay, so how about human vision? Can anybody tell us what this picture tells us? I'm sorry? Commonwealth? Okay, that's a good way to think about. Can you tell us more about it? Okay. Okay, so this is actually a picture showing the driving direction in different countries. All right. So how many of you have been to a country where the driving direction is different from the place where you are used to? Okay, many of you, right? So how many of you know how many pedestrians are injured in traffic accidents a year, roughly? Can anybody give us a number?
1 million.
1 million. Okay. Anyone else? Yes. 5 million. Anyone else? 50? 50. Okay. So I just looked up it from World Health Organization. The number of pedestrian injury each year is approximately 12 million people. And Seattle has population about 3/4 million people. So what that means is everybody will get traffic injury 16 times a year. So once every 3 weeks. So that's a very serious problem, right? However, you may say, okay, I know the direction of traffic. So if I go in one place, I should look left, I should look right. But to make things more complicated, you know the street around here are single direction, right? So the rules do not apply. So what does that mean? Now imagine we could create a device. Actually, the technology is almost there. I'll talk about a few things. Suppose we have some kind of electronic device, and I can see and listen to improve your safety. So you put on a wearable device. It will tell you you should look left, you should look right. There's a sign there. Or even better, you go to a country where you do not speak a local language, you'll translate for you. Now imagine you see a sign and you don't really know what it means, right? Wouldn't that be nice? So what are the barriers for this technology? Many. Well, first, it has to be very lightweight, right? It has to be wearable. It has to be real time. And it has to be able to analyze many different kinds of data, including vision, language, and speech, and so on. Maybe somebody screaming at you and tell you it's dangerous to be here, it's dangerous to do that, but you don't understand local language. Of course, it has to be very high accuracy. If it has very many false alarms, people will not use it. And if you miss a danger, then somebody gets injured. It can be personalized for your personal language, or maybe your preference. And you need to be able to localize using GPS and so on. But among all these computation, one of the major barrier is the low power consumption. However, if you look at the trend in the last several years of machine learning, the trend is going to be bigger and bigger models. In fact, the size of the models grow faster even than Moore's law, several orders of magnitude higher than Moore's law. In the last several months, many media have said the real challenge for AI now becomes energy. Can we power the systems? This was an IEEE spectrum a few months ago, saying before AI can take over, you will need to find a new approach to energy. This government technology also says AI challenge is energy and many more. This is 3 months ago, and this is 2 months ago. In Bloomberg, AI have a problem of energy. We started this research on low power computer vision more than 10 years ago. At that time, the most common question I got is, why don't we just send to the cloud? So all problems solved. Well, there are several problems of this solution, send everything to a cloud. First, cloud is very, very energy consuming. So this Jason Huang took out the GPU from an oven. I don't know how many of you have seen that commercial. It's very big and it's very hot. So if you have ever been to any computing cluster, you probably know cooling is a big, big problem there. So from the energy viewpoint or from the environmental sustainability viewpoint, sending things to a cloud is not very good for the Earth. But the problem is much more than that. The problem is you may have many situations where you don't have high-speed network to the cloud, right? You need to send a very large amount of data because it's on your camera, real-time image or video. You may not have that kind of network everywhere. Also, from the energy consumption viewpoint, if you send a lot of data over the cloud, that wireless communication is very energy consuming. So you will drain your battery even faster. Two other important factors will be the uncertain delay over the internet, as well as the privacy. You may not want your competitors to know what kind of inventory you have in your factory, right? So these are factors where you want to process your data on the local device, not in the cloud. So this, since 2015, I've been organizing the Low Power Computing Challenge for the IEEE Computer Society. This book collected the winner solution up to 2021. So I brought 2 copies here. If you are interested, you can come take a look. And this, it turns out many companies are very interested in low power computer vision, and these are the sponsors of the challenge. These are the winners. You may say it seems a lot of winners because over the years, many sponsors wanted us to have more tracks. That's why we add more tracks, and we have many more winners. You can see the winners come from academia as well as industry, shows that really people are really care about low power computer vision. This shows how many people participated since 2018. In the first 3 years, 2015 to 2017 is an on-site competition. So you have to be there, bring your hardware device. The advantage of doing that is we have no hardware restriction. You can bring any hardware. The disadvantage is that you have to travel and bring your hardware. So since 2018, we changed the competition to an online competition. So you don't have to bring your hardware. You don't have to travel. But the disadvantage is you have to use the hardware we provide. So this is a trade-off. But the number of submissions and number of teams have been growing very quickly over the last several years, showing this is really getting more and more important for people to think about low power computer vision on the edge devices. So I give you just some examples of the computer vision problems we ask people to work on. The first is in 2021 is the multi-object tracking. You probably can tell these are the object, the video taken by the drone. And the problem we want to do here is we have multiple objects, including people, and there are also several balls. People will pass balls around. And the challenge is the computer vision needs to track who holds the ball. If you remember what happened in 2020, that was called COVID. So we did this outdoor for safety of our students. Another example was last year we had the segmentation challenge. This was inspired by some of the natural disaster in different parts of the world. So we give people images and they need to segment the images based on different type of objects such as buildings, roads, vehicle, and water. Over the years, there have been many methods improving energy efficiency of computer vision. Here I will give you a very quick overview of a few of them. Many of them have a lot of details in the book by the winners. The first one is called quantization. The second is called pruning. The third is filter compression and matrix factorization. Network architecture search is also a very popular method, and another method is called knowledge distillation. Then after I quickly summarize this a few methods, then I will explain some methods developed in my research team. The first method now is very standard. It's called parameter quantization. When people started thinking about neural network, usually we start thinking about 40-point numbers. But 40-point numbers are very expensive, both for computing as well as storage. You don't want to use so many bits to store your parameters. Also, when you compute 40-point numbers, usually it takes multiple cycles for your processor. But if you use lower precision, then you have a problem of accuracy. Therefore, people have been doing a lot of studies about the trade-off between precision and speed. Some studies have shown that usually 4 bits will be enough. Of course, it depends on your data. But if you reduce the number of bits to 4 bits, usually you don't see much degradation of your accuracy. So that is now very popular. You go to many studies, they will tell you they use quantization. In fact, quantization has 3 major methods. The first method, I don't know what happened to the microphone. I think I saw that yesterday too. Suddenly. Yeah, okay. I don't know. That happened yesterday. Okay. Yeah. I guess it has its own mind. There are 3 types of quantization. The first is called dynamic, the second called static, the third is called the quantization over training. The difference between them is, let me talk about quantization over training first. So usually when you do the training is you use the floating point for backpropagation because you need high precision, but you use quantized data for your forward calculation because that's what you use when you do the inference. This will adjust your training parameters, therefore you can improve accuracy. But the problem is you need training. That means you need training data, you need to spend time to do the training. Another 2 methods will be what we call post-training quantization. And the post-training quantization can also be divided into dynamic and static. Static means you do a quantization before you do a computation. And you do a quantization for both your weight and your activation function parameters. So the advantage is you get a better speed because you quantize everything. And you also reduce the number of bits you need to store for your parameters. So you also get an advantage for storage. But usually you get lower precision. I mean lower accuracy. So there is somewhat in between, it's dynamic. So you have the quantized weight, but your activation parameters will be using floating points. The advantage is you somehow have a balance between the 2 extremes. You have a better accuracy, but your speed will not be as fast as such. Quantization now is very standard. In fact, it is supported by PyTorch. You can go to PyTorch, and then you can just use the built-in PyTorch support for quantization. And if you search PyTorch quantization, it gives you lots of documentation, tell you how to do, and with a lot of sample code. Another method is called network pruning. After you have done your training, then you can look at which weight has very small numbers, and then you can remove your network connections. It's also very common when people use something called dropout. You just eliminate that connection. That will reduce the computation as well as your storage. Usually this requires much longer training time, but it's also very standard. As you can see here, we can use the pruning and quantization can be used together. The amount of memory can be reduced, as well as the error has relatively small change if we use this method. Another popular method is called the filter compression and matrix factorization. So basically, you take a very large filter by multiple small filters. For example, you have a 3x3 kernel, you change that into 2 orthogonal kernels, and then in terms of computation, you get the same result, but you reduce the number of parameters from 9 to 6 in this case. Network architecture search is a common approach. Basically, you will adjust your hyperparameters, how many layers you want to use, how many connections between different layers. The advantage of doing this is you have a very large amount of freedom. You can find really good network architecture for your problem. But the disadvantage is you usually require very large amount of computation time because the search is very, very large. Usually when you do this, you have some kind of particular target application. So you are willing to spend that amount of time to optimize for your applications. The way you do it is usually through this process. You have a controller and you have a trainer and estimation process. You will set some parameters, then you will, by the controller, then you will train your neural networks, and you'll estimate the performance as well as the parameter size and so on. Then after you get some estimate, then you decide whether you should keep doing it or not. Very often you will have an early estimate and say, this is not worth continuing, and you'll stop, and then you will try some other combination of your parameters. Nudge distillation is another method getting more and more popular, I think. The concept is you have a pre-trained neural networks. Now, probably you use some kind of foundation model. And then you take another smaller neural network you want to use. Then you try to use the pre-trained large neural network to help you train your small neural network. This is particularly helpful because your large foundation model may solve many different problems, but you may want to solve a particular problem. Therefore, you don't need very large model. Then you use this process to help you train your small neural network for your particular application. So these are the few common methods people use. In the next few minutes, I'm going to talk about some of the work we have done in my research team. The first one is called hierarchical neural network. We take a different way looking at neural networks. We call it make early decisions. So let me explain what this figure means. Usually you have a deep neural network, and then you pass your data through a network, you get all the results after you pass all the data. So imagine you have, this is an example of image classification. You have images, you want to classify them as truck, car, cat, and dog. But you do not really need to compare all of them through all the steps. You can have a small neural network that can classify them into different categories. In this case, we consider vehicle versus animal. I will talk about, it's actually, we call the visual similarity, not semantic similarity. I will talk about that in a few slides. But after we separate them into two categories, vehicle versus animal, we don't have to compare a car with a cat because we think they are sufficiently different. We early on, we separate it. So later on, we don't have to do the comparison between them anymore. By doing this, we can have a very, very small neural network to do the work, and we can get almost the same accuracy as an original very large network. So now let me explain the steps we need to do this, construct this hierarchy. First step is we need to find the similar categories. In the early example, we will say cat and dog are similar, and car and the truck are similar. But how do we make that decision? The second step is we need to train the neural network. We also need to decide how many layers, how big the neural networks should be. I also need to emphasize we do not predetermine the size of neural network. The size of neural network is determined as we are doing the training. We also do not restrict the neural networks need to have the same layers. So these 3 neural networks on the right side, they may have different sizes. Also, we do not restrict the neural network to have the same number of fan out, you may have a situation where one neural network will have a 2 fan out, another neural network will have 3, another will have 4. All these are depending on the data. And of course, we need to do a training of each neural network. The first step is we need to group the classes. In my research team, we have done quite a bit of study about how do we group them. The first intuition is we want to group them by we call visual similarity versus semantic similarity. What do I mean? If you look at the visual similarity, the bird and the airplane will look similar because they have wings, they are in the sky, and the shape are somewhat similar. But in terms of semantics, they are very, very different. One is an animal, one is a machine. So semantically, they are very different. If you consider semantic similarity, you'll say banana and apple are similar because they are fruit. But in terms of shapes, they are very different. One is a long shape, one is a round shape. So we study the difference between visual and the semantic similarity. This is an example where we can put them into 4 different quadrants. On the lower left corner is the high semantic similarity and high visual similarity. For example, the dog and cat, they have 4 legs, they have ears, eyes, and so on. On the right side, at the lower part, we call it the high visual similarity, but the low semantic similarity. A plate and pizza, they have a round shape, so they are visually similar. Or you can eat one, you cannot eat the other. So that is low in semantic similarity. Then of course you can have a upper right corner. They are visually dissimilar. They are also semantically dissimilar. And then when we go to using an existing pre-trained neural network, we actually see this very clearly. Suppose we have this CVPR10 data set. We'll compare an untrained neural network with a trained neural network. They will have a high confidence thinking about bird and cat and deer and dog and so on. We'll have somewhat high confidence they will be somewhat similar. In contrast, truck and automobile will be considered related. So what we have done is we take a pre-trained state-of-the-art neural network, and then we pass our data into our system, and then we will look at what's the most likely they be considered similar. In this case, an airplane is considered similar to a ship, primarily because they have straight lines, they have a similar shape, compared with bird or cat, they have legs and eyes and ears. Therefore, in this case, we consider airplane and ship, they are similar. We will then put them into the same group when we put them together in our hierarchy. So now we have decided which objects, which classes are similar. The next step is we need to decide the neural network sizes. We use a very simple method. Is what's the marginal improvement if we make the neural network bigger? So A here is the accuracy, M here is the size. If we increase the size, does the accuracy improvement is greater than the threshold? So AI plus 1 means the next iteration we make the network bigger. AI is the previous iteration. And as we make the network bigger, the accuracy should improve, but the size also increase. So if we look at the ratio of the accuracy improvement divided by the size increase, does that exceed a threshold? If it exceeds a threshold, means adding more layers will be helpful for our network. Therefore, we keep adding more layers. If it's less than a threshold, then we'll say adding more layers does not help, so we stop. Now we have decided the size. So the way we do it is we start from the top, and then we decide how many groups we want, and we decide the size for the root module. The root module is the first separation for the input data. Then after we do the root module, then we will start propagating downward. It's important to understand that the one major difference between our method and other method is we take the intermediate result from each module as an input for the 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 lower module. What that means is you can think about the way the data pass through different modules is they go through more and more layers. So you go through a root module, you go through several layers. Then you go to one of the child of the root module, you go to a few more layers. Then you go to another child module, you go to even more layers. So going from the root module, going all the way to the leaf, where we decide which kind of object it is, it goes through many, many layers. So conceptually, you can think about going through multiple modules is going through many, many layers. But as I said earlier, we don't have to compare them if we can decide very early on. We don't have, yes, different enough. So as a result, going through all the layers, our method is still much smaller than typical neural network. As we train, we will freeze the parameters from the top, and we'll train the child module of the frozen parameters. So this is what I described. We will first decide the groups, then we select the size, and we will train, and then we'll repeat to train the lower layers near the leaf node. This is an example for the CVPR10 data set. So I want to spend a bit of time looking at this. Again, our training, all the parameters are depending on the data. So we see truck and the automobile are similar. They are put into the same group. Ship and airplane are put in the same group, and animals are put in the same group. Even for animals, then we will further separate them into cat and dog into the same group, and deer and bird into the same group. Look at this hierarchy. There are a few things here. One is we do not predetermine fan out. The fan out is determined by the data. We also do not predetermine the height. That's also determined by data. It turns out there are some trade-off we can decide. If we intentionally force the fan out, then there's a trade-off. If the fan out is very small, that means the tree is very, very tall, then the accuracy will drop. The reason is at each node we will lose a little bit accuracy, but very small. But if the tree is very, very tall, that means the accuracy loss will accumulate, and eventually our accuracy will be low. So we don't want the fan out to be very, very small. But at the same time, we don't want the fan out to be very, very big, because the fan out is very, very big. We basically degenerate through the original neural network, because the original neural network, the fan out is the number of classes you have at the beginning. So we don't want to have a very large fan out. Therefore, it's a trade-off between these two factors. These are examples of trees of several data sets. We have some tuning parameters we can tune, but these are some examples we can show you. SG here means a supergroup. In terms of comparison, we compare then Raspberry Pi. I assume everybody knows what the Raspberry Pi looks like. This is an example. Yeah, so we run on a computer like this one. It actually doesn't have GPU. So we compare then different methods with Raspberry Pi and different data set. The first one we compare is the inference time. Our method is much faster than other methods, and also we compare the energy consumption. Our method is much smaller consumption. So here, MMN tree is the modular neural network tree. That's our method. All right, we think this method is great, but it's not perfect. There are many things we can improve. We do encounter the situation where sometimes the neural network makes a mistake. Let's imagine a neural network mistake. It should be a bird, but somehow it thinks an airplane. So what will happen if at the root module it thinks an airplane? You will go to the neural network 2 and neural network 4. But if it turns out it is a bird, so it makes a mistake very early on. It never has a chance to recover. Then we introduce a concept of recovery. So we change it from the tree, now become a directional acyclic graph. But we do have a chance to recover. So that means we will add a new link from the neural network module 1 to airplane. that will improve accuracy. But now we make neural network module 1 more complex because the fan out is bigger. It has to handle more different classes. So it's a trade-off. We can improve accuracy, but our network size will be a bit bigger. So you can see in this case, we can apply our method. The circles are our method. We want to improve accuracy at the higher memory requirement. Another problem we are still working on, we don't have a good handle on this yet, is our method seems to be very sensitive to some human parameters. So if we choose the batch size, a lot of time it's pretty stable, but if we change a little bit on the left side, then suddenly the accuracy drop very significantly. We don't have a good way to solve this yet. Another parameters we also study is the group size. If we restrict them to the group to be very, very similar, that means the fan out will be very big. If we group similarity will be very small, that means the fan out will be very small. But it turns out our method is very sensitive to that parameter. So they will have a very different shape of the tree. Okay, so that's hierarchical neural network. The next, we'll talk about another piece of work about how to discard irrelevant pixels. Imagine you have a security camera. You want to count how many buses you have in your parking lot. You probably don't care about the pixels in the sky. The question is, how do we detect the pixels in the sky so we can discard it? You don't want to first detect the pixel and then discard them, because detecting a pixel requires computation. So it turns out many data sets, they actually have a lot of pixels are not really necessary. So this is a heat map. Let me explain what it means. If you look at the data set and you say, okay, this is an object of interest based on the annotation, then you put a number on number 1 for that particular pixel. If a pixel is not in the region of interest, you put 0 there. So after you process the entire data set, then you have a heat map, means which pixel is interesting for this particular data set. As you can see, many pixels are blue, means the pixel doesn't really contribute to the object interest. So we can discard those pixels. How often does this happen? It actually happens very, very often. This picture shows the number of pixels needed for you to achieve the highest accuracy of a state of the art. Some data set needs only 70% or sometimes even less than that to get your accuracy. So it means a lot of pixels can be discarded. What we have discovered is we can take advantage of the convolutional neural network structure. We'll look at the first few layers. If a pixel has triggered any kind of feature, we'll keep that pixel. If the pixel does not trigger anything, then we will discard that pixel for later layers. This will be a trade-off, because if you consider too many layers, then you are not saving anything. But if you consider too few layers, you discard pixels too early, then you'll degrade your accuracy. It turns out we can find a method. I think I'll skip that. We can find a sweet spot where you find just enough layers to process your data, and you will not have an accuracy degradation. You also have significant computation reduction in this case. So for our method, we can reduce the computation by about 10 to 20%. Due to interest time, and I think I would only talk about this slide, is because of the way hardware is designed, when you look at your transformer number of tokens, the number of tokens and the amount of time computation is not a straight line. Very often you have the number horizontal axis means the number of tokens, vertical axis means your execution time. When you have more tokens, your execution time will increase, but not a linear relationship. So you may have a situation where you remove some tokens and your execution time can drop very significantly. That's a hardware characteristic, so you have to look at your hardware. Then the question is, how can you find those pixels to remove? There have been a lot of studies showing in the last several years, showing that people have been looking at how to remove the tokens in your transformers. So the black regions are the tokens removed. You can see the different methods. To me, is token merge. They do progressive token removal. And our method, we try to remove tokens early, because if you remove tokens early, you can reduce the number of computations. But there's a trade-off, because if you remove tokens too early, you will lose your accuracy. So the question is how to do that. Our method uses some training to determine which tokens we can remove. So to summary, I hope you agree that computer vision can solve many problems, including save lives. Energy efficiency is really crucial to deploy computer vision edge devices. I have presented some work about hierarchical neural network that can reduce execution time and the storage requirement. And also removing non-informative input tokens for transformers can be an effective way to reduce accuracy. I'll stop here. Thank you for your attention.
Any questions? Remember, we will have both sides to reward. I don't want to hold the book by myself. Two together, so one by one.
So, you told us about the Maya that has like two views and then kind of for the
Yes, we have a comparison with GPU in the paper. Here I just show the example without the GPU. Yes, we use the GPU such as just a Nano. The trend actually similar. Yeah, so we also use devices like this. The trend are similar because this is architecture change, not the computation method. So we see similar trend. Maybe next time I should add the graph about JSON in the slides. Okay, so the question is what type of parameters we have. The number throughput is not a parameter, it's the result of the data. The parameter that decide is how to determine two objects or two classes are similar. That's what we call similarity index. So if you allow more classes are considered similar, it will be considered one group, there's a fewer groups. And in the extreme, we'll make it very strict. That means there's no group, and we just separate into the original classes. That's the Turing parameter. Based on that Turing parameter, everything else will be decided from there. Does that answer your question? So that's the similarity index we use. And then the others will all depend on the data. Oh, sorry, this machine is making noise. I don't know what happened. Okay. Can you speak louder? Sorry. So how does the hardware in mobile phone affect the state? I have not done study on that. We use device study because it's easier to program. We have talked to some manufacturers, but I don't have any data to give you any insight. Yes, please.
Okay, and this first after evening morning, and we will have start with and let's have it after 5 minutes. Thank you. I don't know what when that maybe not going to the 15, I don't know. We were mentioning lots of and then we were wondering where are you and that's what he said very well, right? Because education no, I was like that's not saying
I feel so. I feel some currently it doesn't sound too loud. Hello, Dr. Ye Tang. Are you here? Can you hear me?
Can you hear me?
Can you hear me?
Yeah, I can hear you.
It's not on the I couldn't hear you. I need to figure out how to can
Can you
you
hear
try
me?
whether you can share screen?
Can you hear me?
I don't know why I couldn't hear you. Well, I can hear you, but it seems the system is not.
Hello? Hello?
Um, um,
Can you speak right now?
I'm not speaking, but can you hear me now?
I can hear you now. Okay, now.
Okay. I think the problem is at your side because I don't make any change.
Okay. Yeah, I changed the laptop. Can you speak right now?
Hold on, let me. I'm not speaking, but can you hear me now?
I can hear you now. Okay. Okay. Can you share the screen?
Yeah. So can you see my screen?
Yes. Wait a second. Let me share the screen on the room.
So you see the biggest one, right? So not the other one.
Yeah, the bigger one. Yeah, the bigger one.
Okay, because I'm using two monitor. Okay, can I begin now? Or I need to wait?
Just give a second. I just need to close
Okay.
the.
Just let me know, okay,
Okay.
when you are.
Okay. Let me first introduce
Dr.
Ye Tang. So sorry. Can you hear me right now? Well, probably I don't know the reason actually. This one is in our CVPR original one could not. I can hear, but Hello? Hello? Let me introduce Dr. Cang Ye, and he is currently a professor in Department of Computer Science in Virginia Commonwealth University. He got his bachelor and master degrees from the Department of Precision Machinery and Precision Instrument, and from the University of Science and Technology of China. And he got his PhD from University of Hong Kong, and he was a research fellow and at the Mobile Robotics Lab of the University of Michigan at Ann Arbor. And since 2003, he was a research faculty at the same university. He joined University of Commonwealth in 2005, and Dr. Cang Ye is a fellow of American Institute of Medical and Biological Engineering, a senior member of IEEE, and a member of IEEE SMC technical community on robotics and intelligent sensing. And he's also a program manager at NSF. And his topic is on visual initial odometry for small size robots. Dr. Ye Cang, can you try to talk and see whether the people can hear you clearly?
Okay.
Yes.
Oh, can everyone hear me?
Yes, yes. Works well.
Okay, great. Yeah. Kind of I'm using the webcam's mic, so I don't expect that the audio quality will be very good, but I will speak as close as possible to the webcam. All right, so for this research, actually the motivation behind this is some kind of real world application. So we are looking into one actually is that what we call the robot cane. So that is developed to be used for assisted navigation for actually wayfinding for the visually impaired. So, and also some smaller robot, for example, like drone. So this drone is not small, but there's a smaller drone, right? So, and also I show one, this actually the capstone project, undergraduate student did that. So, but it's kind of use this image as a kind of idea about kind of this wearable device that actually we are also looking into. And for this type of application, so kind of because of the high portability requirement, so that means you have limited resource, and then also, oh, sorry, so here is the duplicate. So kind of also you need to consider the cost, right? So that for this type of application, so cell phone actually kind of represent a very ideal computing and sensing platform because it does not require dedicated electronic to do the work, right? So especially for some application like this wayfinding, so people are not always use this device. They probably just use that for a while. When they get their destination, they don't need that at all. And then you have it's a way is to have a dedicated electronic, right? So device there but it's not doing anything once they get to the destination. The same thing here. For example, this is a wearable device that can help you identify the visually impaired people, okay, identify a target object and then guide the hand through some mechanism, and then you can eventually grasp, take a hold of the object, right? And for this type of thing, you just use that for a few minutes, and then other time you don't use that. So, and then cost is a very important factor to be considered. So if for device adoption, so if you make the device very expensive, the visually impaired people won't use that, right? And of course, there's other type of application, like for example, like virtual reality and augmented reality that based on phone, right? Cell phone. So, and that is a very natural application of using smartphone as the computing and computer vision platform. So now, as you know that today's smartphone actually get very powerful. in terms of computing and sensing. For taking this iPhone 15 Pro as an example, so actually it has a quite powerful CPU, right? So and also have like GPU and even like the neural engine that for AI type of task. And in terms of sensing, that you can use the camera and also iPhone since I think since iPhone 12 Pro, there's always LiDAR, right? So these are from Sony. And then it integrate IMU. And for outdoor application, you even have like a compass and also like GPS, right? So that's a quite impressive suite of sensor. All right, so this made iPhone an ideal platform for certain application like those example I just point out. But the problem of using this camera that with this cell phone actually is that the optical image stabilization mechanism now it actually is the mainstay feature of any modern cell phone. So this camera actually use this we call it OIS, optical image stabilization. So it is a kind of a actuator here that actually the camera lens is mounted to, and this actuator actually is driven by a voice coil motor. And as you know that when your hand jitter, kind of handshake, introduce kind of image, kind of vibration, right? So and that actually change the somehow the optical path of the thing or object to be image, right? Being image. And then this system actually now can detect like the hand jitter movement by onboard sensor like IMU, gyro, for example, and then it will know that how your optical path move. And then it now actually generate a counter reaction movement, kind of bend this lens barrel so that to compensate that optical path movement, and then you will get a stable image. But this mechanism will cause a problem, like actually it will make these optical parameters, so that actually camera's intrinsic parameter actually is always changing. So if you have TO angle change, for example, then it will keep changing. So when you do these like the visual inertial odometry or SLAM, without considering this camera intrinsic parameter change, then you will end up with unwanted post-estimation error. And in our case, for our application, we need to consider that because for that robot gains and also the hand one, you have roll and pitch angle change all the time. And that actually introduce this CIP variation from time to time. And we need to consider that in doing this visual odometry computation. All right, so the method we actually propose, the first one actually is we call that CIP, camera intrinsic parameter, VMobile. So because VMobile actually is an existing algorithm that actually only consider like using the monocular camera and also inertial data without considering the camera intrinsic parameter variation. So we actually introduce this method. We actually term that CIP VMobile because it's used it's based on a mobile phone. So this is in essence is a graph SLAM algorithm. So it treats camera CI intrinsic parameter as a state variable, and then tightly coupled it with other state variable, for example, like pose, velocity of the device, and IMU bias and visual feature, right? So and in a graph optimization process. So and in order to make this system work well, we actually introduce kind of a through characterization of the OIS mechanism, and we find a linear relationship between this CIP change and also the acceleration of the device. So then using this model, we actually can estimate some the initial CIP value for a particular time step or at the node. And then to start the graph slam calculation, and then this value kind of is a kind of good starting point, right? And then it will be updated as the iteration of this graph optimization proceed. All right, so the algorithm look like this way, so kind of standard, right? So we have a kind of pre-processing module here, kind of taking camera data and also IMU, extract visual feature, and then use that linear model to get a initial CIP estimate, and then use this window approach actually to create a graph for this process for optimization. And the system also have an initialization actually module here. So kind of we try to do this visual initial alignment. So if that alignment is successful, then the actual visual initial odometry actually can begin. Otherwise, you cannot use the initial data. So this actually degrade into a just structure from motion computation. So there will be a scale problem, right? So and the scale won't be correct. All right. So if the visual initial odometry initialize successfully, then we get into these kind of post graph construction and optimization process. And here, this is a kind of it is a standard process, right? So like a linearization and then approximation, and then repeat that again. And then we actually use this robot cam to demonstrate that how well this system actually work, okay, in the real world scenario. All right. And just like standard factor graph based algorithm, we actually create a factor graph like this, right? So and then differing from the like standard like Win mono or Win mobile, we actually add a additional node here. So this is called I think it's called CIP, camera intrinsic parameter node here, and that's the fundamental difference. So when we compare this with the Win mobile algorithm, and this is the example factor graph the system built, and then the goal actually is to optimize and then estimate the pose here of the camera within that window, and then to minimize the total graph actually error. So this error actually is a kind of a model that define as these state variables PDF probability density function. And then if you find the best estimate for this pose, then this error, the total error that is called residual, will be minimized, right? So and now, and in the literature, people actually have done some work kind of to analyze the conversion property of these Win mobile or Win mono method, and kind of this algorithm has some guarantee in conversion, or at least it will convert with some bound there, right? So now by adding this CIP node, so as we can recall that, so there is a linear relationship. You will actually see that later between these CIP value and acceleration. So this is equivalent to that we add a acceleration node here, right? So now velocity node actually is more complicated because it's subject to that kind of bias and drift, and this node is much simpler. So and we actually have quite kind of reasonable expectation that adding this acceleration node will not affect the conversion property of the graph optimization process. All right, and this slide show you actually how we actually get this model. So now there's a two way to actually get the initial value for the CIP. So sometimes if you have an API, so for example, that iPhone, you actually can read that somehow from that API. But if you don't trust that value, then you can do your own. So here actually is how we do that. We actually use a kind of, we mount the iPhone here. So this is the iPhone 7, okay? So it's the older model on the rotary table. And then so that we can rotate the phone around the XYZ coordinate. And then we will collect the data of these acceleration. So that measured by the IMU. And then by doing camera calibration, we can find the camera's intrinsic parameter. And then we do the data feeding. And then you can find that actually these straight, very much follow a linear relationship, right? So because it is a spring model, okay? So the actuator itself is a spring, can be actually modeled by a spring model. All right, so by fitting this, we get a kind of this equation for this. This is actually is the focal length, and then the image center, right? And of that, and then the fitting itself auto produce like the variant, and then we can treat that as noise in that model. All right, so to demonstrate how well this system work, actually we use some simulator to generate the camera image and also like the camera's parameter and also like the acceleration of the IMU. So here is the IMU model, okay, property, and then we actually now can run this algorithm. So we compare a two method here. So this is the baseline method. So it's wings mobile, and then we adapt this wing mobile into CIP wing mobile, right? So and then this is our method. This is ground truth. So you can see that actually the proposed method track this ground truth very well, but wings mobile without taking into account the CIP variation actually does not do the work well, right? All right, and this also shows simulation result, kind of try to show that how the method actually track the CIP, right? So here is that this is the ground truth CIP value, and this actually is the CIP. So that is the initial value computed by using the linear model. And then this actually is the proposed method, and it keep tracking actually refine the initial value that for this CIP, right? So and you can see that so that this purple color line actually is much closer to the ground truth, right? So for all of these parameters. All right, so and then we also use simulation to test that with or without the CIP model. So that using this CIP acceleration model to get a initial estimate, actually did a good work, right? So in terms of the end result. So if you don't use this model to get the initial value, you probably end up with much bigger post error. And because you start your the iterative optimization process from a not so good point, right? So and then the system can be tracked by local minimum, and that actually probably can be far away from the ground truth value. And also this model, because you start with a good estimate, and then it actually reduce the iteration number of the graph optimization procedure, so that it speed up the SLAM computation. So here actually shows some experimental result. So we actually handheld a iPhone and then move the phone that kind of sway the phone on purpose. And then while people is moving around the lab, And then we actually compare these method, so the proposed method and the standard, the baseline method. And you can see that actually we actually show here we have 10 experimentation. So for most, I think for all of them, our method actually get a much better result. So this in terms of the end position error percentage, in percentage of the total trajectory length. And we do an average here, and then you actually can see that this improve the result actually about I think it's about 35% better. Okay. All right, and then we made this we put this approach that onto this robot cane, and kind of here show you how the system look like, right? So these we have some hardware to control the robot cane. So the robot cane, different thing here is that here we have a kind of, we call this robotic roller tip. Actually, it can steer the cane so that it can guide the people to make turns, something like that. Okay, and here is the proposed VIO method. And then we put that into a navigation system that can do path planning based on some map, and then can use this map to guide the people by sending both these guiding instructions through the roller tip, and also can use some audio interface for human device interaction. So this basically kind of show you, this is not the cell phone based version, but it actually can show you that how the system actually works. So it's some, we speed up some of the video clip to save time. Yeah, and it can actually turn and then to indicate that the user need to make a turn. Right, so like here. All right. And then when they get a destination, for example, this from that room to elevator, and then it will actually signal that you arrive at your destination. All right, and so here is some experimentation result that, and then you also can see that we compare that with the baseline approach, and it is better. I think it's about 20 something, 24, 25 better than the baseline approach. All right, so now this is based on the old like the iPhone. Now because now Apple actually integrate this LiDAR into the iPhone, so actually we make attempt to integrate that LiDAR also into this visual odometry. So we call this LiDAR in visual odometry. So to incorporate this LiDAR data into this post-graph SLAM process, we actually did several things. So including like we try to characterize the LiDAR measurement and then come up with some model, for example, how the error look like. And then we use that property kind of to do like the range, like the data filtering to remove those not so good depth data. And then use the better data for that. And then we also use like here we call this hybrid PMP method to compute the visual feature with projection error. So kind of we use all inlier to computing the rotation, and then we use the inlier with LiDAR data from both like the previous frame and also the current frame to compute these projection error or computing translation. So because we use both frame, the inlier in both frames, so we actually get more inlier than just use one frame. Okay. All right. So the extended version, so VLIO look like this. Okay. So the different that from the previous, like the one that CIP V mobile actually is that we add
1 second.
This.
Seems like it sounded a lot.
Excuse me.
Now it's working. Now it's working.
Okay. So the difference that here is that we actually now add this node So that's represent the depth. This is LiDAR data. So this is in terms of inverse depth. So these nodes are not added. So this is the difference from the previous one. And again, the same thing. So we look at this residual area. So now we have a new, I think, a new term here. So which one is that? Depth. I think probably these two, depth. And then this will actually integrate the LiDAR data that into this graph slam process. All right, so in terms of this measurement, like the characteristic, we actually do some characterization study and find actually some of the mean error actually follows something like this. We don't know actually what caused this, but it looks like there's some, because this is something proprietary, so Apple didn't actually made it public how the LiDAR work, right? So Sony didn't do that either. So we have to do some characterization study and then to find out the kind of how this error follow and also like the standard deviation. It will look like this way. So as the distance range increase, the standard deviation actually also increase. So we can somehow use this actually to make initial correction to the range data. And then another thing we look into that is that in complicated indoor scene, actually this LiDAR actually, as you know, that can actually have measurement that we call that mixed pixel. So that means when the measurement are located at the edge, what actually we measure actually is a distance or range in between the front object and the background object. And those data, we need to remove them, right? So we can do things like this, do the boundary tracing, and then if there's any visual close enough to the boundary, then we actually will remove them, right? So and by this actually we can do a data filtering, do the preprocessing, and then with that we actually run the extended method that in the lab, and we actually do some comparison here. So like we start here and then end about at the same point, okay, and then we actually plot the ground truth here, and then you can see that the proposed method actually here actually do much better than the baseline method. So here the baseline method we use actually is the Win RGDB because this uses that data also. So then here actually we do some comparison between the baseline and the proposed method. Right. So and then another comparison we did actually is that we try to actually disable the tracking of this CIP and actually end up with a worse result, right? So that actually shows the effectiveness of the CIP estimation and also CIP refinement process. All right. So now when we looking into like the application for this, when this algorithm is used in that large, like the real world navigation scenario, usually we have an indoor large scale environment, and then several things that will pop up and then need to be considered. For example, like if there's a kind of after the long navigation, you come back to the same place, like you will need to do loop closure detection, but that's a very computationally expensive. And hopefully we don't need to go into that avenue. And then there will be another thing like the scene object recognition. So we can use this to limit or reset the accrued pose error, right? So, and that's another approach, probably is better than this loop closure detection. And also in this indoor man-made environment, we can use some linear, like the planar structure that to limit the growth of the pose error. And that probably can partially address the problem and that can make navigation possible that in this very big environment. And also another challenge actually is that the dynamic object, right? So, and then that actually is a difficult thing to do. So, but we currently look into like, for example, detect object and use semantic information. For example, some object actually static, you actually have prior information on that, right? So wall, like the floor, some furniture, they are static and use that. And then we can do some ransack process to identify static visual feature and only use those features for this visual inertial allometry computation. So, and I think the most difficult thing now actually is that a refractive surface. So if there's a refractive surface, then this will pose a biggest challenge to any SLAM method that use visual information, because you will get a lot of this refraction like that, right? So, and then that actually is a real problem that when we look into this real world navigation application. All right, so with that, actually, I can open to any question that you may have.
Any questions? Probably I can get started with the first question. Actually, the CIP system and in the indoor environment, usually the motion is relatively slow. And if we want to use the CIP system you developed from your lab in faster motion environment, for example, autonomous vehicles, and do you think there will be some differences in the performance?
No, I think the CIP, because your orientation, kind of your pitch and roll angle actually can affect that. It doesn't need to be like the real, like the movement, like the acceleration that induced by drastic motion, right? So if you tilt you tilt or roll the cell phone, that will cause the CIP change, because the gravitational acceleration will change that CIP value.
Okay. Okay.
And I think that actually played a major part, other than like the drastic movement, because I think if the human use that, there won't be very drastic motion. But your orientation of that device actually play a big factor that caused the CIP change.
Okay. And also, follow-up question is for the LiDAR camera visual odometry system, and in comparison with some traditional totally LiDAR-based, for example, ICP, those kind of algorithm. So the visual information on improving the performance, and how much is the improvement from the visual information to improve from the LiDAR?
We haven't compared with that, because we are looking at that small device, and also in like the indoor with limited range, right? So, but looking into that, we recently collect the data set, actually allow people to compare with that. We put a like a Veridon LiDAR and also the Intel LiDAR, and I think there's other camera that have depth measurement there, and then we also use RTK that to generate the G kind of a ground truth, and then that data set can be used to do the comparison. But in frankly speaking, we haven't done that for this type of setting, because this is a short range LiDAR, and it's kind of a little bit newer than those Veridon LiDAR long range, right? So this iPhone LiDAR actually they have very limited kind of resolution. Apple actually applied the image processing to that, actually to kind of to make more data. Out of that, probably 64 data point that they use some AI and image processing method kind of to actually kind of how to say that, upsample the range measurement, and we don't know how well it works, and but in some case probably that data are not very correct. So that will be a problem.
Yeah, that totally makes sense. Any other questions from the audience? Okay. Oh yeah, one more question. Can you come here? Can you come here to because he may not be able to listen.
Hello, Professor. Let me come back to the slide proposed VIO method CIPV mobile.
This one, right?
proposed VL method CIP. Okay, fine. I want to ask the reason. Why does the marginalization factor is only mounted with position 0, velocity 0, and biases 0? I want to know the marginalization factor. How does the marginalization factor is constructed?
So when a node move outside the window, you always need to marginalize that. So there's a standard way to handle that. But I cannot go into that very technical detail. It is a very standard process, but we probably need to also handle this, right? CIP, but there's a way to do that. So it is some computation thing.
Okay, thank you.
So it can be do the similarly like the other, that is standard approach, because as I said that this CIP node is just is equivalent to a acceleration node, right? So then if you can do the marginalization for other, then you can do marginalization for this.
Why does the marginalization factor is not connected with
Yeah, this probably is just a diagram error, so it need to be connected, right? So there's a marginalization too.
But there is no connection with position 2 or position 1 or position 2 and more.
Where?
Oh, I want to know the marginalization factor. Why does the marginalization factor is not connected with position 1 and position 2 or more? I want to know the
your window move this way, right? So only this move out, and when this move out, you need to marginalize, right?
Okay. I know.
Because the other does not move out. So for example, when you shift one post, then your P1 now become P0. So that you always need to do marginalization for only P0. So
Okay.
this is a sliding window, right? So, and it slide this way. So you always need to look at the far end of this window and only do marginalization for this one.
Okay, got it. Thank you.
Okay, thank you very much. And let's thank you, Dr. Yesang, for his great talk. Thank you very much, Dr. Yesang.
Okay, thank you, and bye-bye.
Thank you. Bye. Let's continue with our next speaker, and I think he's already here. Dr. Yeah, here. Right. Dr. Nikos Papanikopoulos. Sorry, my pronunciation may not be accurate. And he's HB fellow, and he received his diploma of engineering in electrical and computer engineering from the National Technical University of Athens in 1987, and his MS and PhD degrees from electrical and computer engineering from Carnegie Mellon University. And his research interests include computer vision, robotics, sensors for transportation, precision agriculture applications, and control system. He's director of Minnesota Robotics Institute and the presidential endowed professor at the University of Minnesota. He received numerous awards, including 2016 IEEE George Saridis Leadership Award in Robotics and Automation, and he's a fellow in IEEE. Dr. Nikos, and thank you very much for agreeing to give the presentation. You can go ahead.
Good afternoon, everybody. Sorry that I missed the in-person aspect of the meeting. Can you hear me?
Yes, we can hear you very well.
Okay, thank you. So I would like to talk about object localization and 3D reconstruction for real-world applications. And needless to say that this work wouldn't have been possible without the existence of a large group of individuals. The PhD student of mine, Thanasis Baharis, the PhD student of mine, Henry Nelson, Dimitris Zermans, who graduated with a PhD and now is Chief Technology Officer at Centera, Dr. Morelas from Electrical and Computer Engineering, David Mula, who introduced us in the area basically of precision agriculture. He's professor in soil sciences at the University of Minnesota. Ted Morris, who is a research engineer at the Minnesota Robotics Institute. Dan Kaiser, who is a faculty in the College of Food and Agricultural Sciences. Si Young, who is an associate professor at the same college. And George Bebis, who is our collaborator at this NIFA project from the University of Nevada, Reno. So as always, it takes a village to do these things. And as I was talking with the organizers, one of the things that I will try to highlight is basically some of the challenges associated with object localization and 3D reconstruction from two real-world applications. One comes from precision agriculture. The other one comes from intelligent transportation systems. And I'm going to mention some results from an effort that's going on for almost 10 years, and with the last deployment at the state of Kansas, where we're trying to assess truck parking availability in real time by using hundreds of cameras at 22 different sites. So without further ado,
one second. You lose the sound. Let me back.
can you hear me?
Oh, now we can hear you. Yes.
So if you look at the motivation for object localization and 3D reconstruction, one can look at intelligence systems and basically how, for example, we can start from manufacturing and autonomy in manufacturing, autonomous operation, for example, for intelligent vehicles or connected vehicles or semi-autonomous vehicles. And something which is really were active the last few years, which is enhancement of human-computer interaction. So in other words, we're using some of the information that comes from the from a trainer in order to train a system, a robotic system, to execute complex tasks such as friction stir welding. I don't know if my audience is familiar, but friction stir welding is a process that can create very strong bonds between different surfaces. For example, when we manufacture aircraft wings or other parts where we need this type of an environment and this type of rigidity. Now, whenever we mention object localization and 3D reconstruction, we have a lot of challenges, especially when we're taking these systems out in the real world. An object appears in many different variations. An object may be part of a clutter scene. We may have scale and pose variations. A great issue that is basically almost omnipresent in all our implementations and applications is generalization of the methods, the real-time performance, and also something that is coming more and more often as a pronounced impediment is actually the limitations that we have in
we lose the
training
sound again.
data.
1 second. Can you try right now?
Can you hear me? Can you hear me?
Now we can hear you again. Sorry for that.
So without further ado, let me jump to the problem of precision agriculture. I don't know how many of you are familiar with this term, precision agriculture or digital agriculture?
I'm familiar with precision agriculture.
So how many from the audience have heard the term?
Not many people.
Just I want to.
They are shaking their hand, their heads.
Okay, so let me tell you, I will try to give a very rough overview of the area. In fact, I was introduced to this area by Professor David Mulla, who introduced me to the Corn Growers Association of Minnesota. When I went there, I said, what a roboticist / computer vision person has to do with corn. But this produced some of the most interesting work we have done the last few years in the lab. And in fact, this was the basis for the recent NSFAI Institute that was awarded to the University of Minnesota. And again, this speaks volumes that sometimes the biggest gains come when we open ourselves to different disciplines, and we'll try basically to see how we can move to the next level of multidisciplinarity. So let me mention, can you hear me or still there is an issue?
We can hear you, yeah.
So if you look, for example, at corn, which is everywhere in Minnesota, and it's almost exceeds $1 billion business. If you look at the efficient cultivation of plants like corn, can have a significant financial and ecological impact on modern societies. So we need to feed the world, and we need to do this with the smallest impact on the environment. If you look at the deficiencies in nitrogen or potassium, basically, if we don't have enough nitrogen or potassium, then we have significant financial losses, and I will give some numbers in a little bit. And precision agriculture focus, among other objectives, on the early detection of nutrient deficiencies and treatment of these plants. In the case of a soybean is a very interesting plant because unlike corn, it's basically the plant stems and leaves are intertwined together, are mingled up. So it presents a big obstacle to have effective computer vision methods applied. And basically there we're looking for aphids and infestation of aphids. And
One second. 1 second. Are you changing the slide just now?
No.
Oh, okay. That's fine.
Just...
Yeah. Okay. I was just trying to make sure your slide is not freezing. Yeah.
No. I'm just trying to provide some background. So basically, we apply pesticides in order to kill aphids the same way that we apply fertilizer. And fertilizers and pesticides in excess amounts can basically have such a pronounced impact on the environment. And for example, Dimitri Zermas, David Mulla, and several other people from the group presented this work in Computers in Agriculture almost several years ago on how we can use, for example, information like, I don't know if you see at the bottom, right, we have a leaf that shows nitrogen deficiency because it has these yellow stripes along the center of the leaf. And on the top, we have a healthy leaf. So we try to detect these patterns on the leaves and basically make assessments about the overall plant health. Now, let me give you some numbers which are staggering. If you look, for example, at Minnesota alone, I'm not even talking about Iowa, North Dakota, or South Dakota. We have 100,000 tons more nitrogen applied than what is needed. And where does this stuff end up? End up basically to Mississippi River. And basically, if you look at the water system, and basically, if you look, there's so much algae developed, especially in the Mississippi Delta, that basically there is almost no fish life in this delta. If you look at the yield, which is lost because of nitrogen deficiency, is around 20%. Now, the goals are basically to reduce the nitrogen fertilizer, saving around $100 million, and improve the yield harvesting, which is again just for the state. These numbers are for the state of Minnesota, $835 million. Now, trying to do this, it's an interesting problem that brings basically to the surface some of the challenges that I mentioned earlier. For example, we have immense differences in scale. There is need for data which are spread over an entire field, but detail enough data to diagnose problems of individual plants. Because the current format is actually in October, we apply enough nitrogen with the hope that after a harsh Minnesota winter, some of this will be left over for spring and when we seed the corn. But basically, this generally leads to an agronomist going and eyeballing the field and saying, okay, we need to put more fertilizer or less fertilizer. And this is generally highly inaccurate and not effective. If you look at the data, it's often context or location dependent. The soil in one field looks very different than the soil in another due to the differences in moisture and soil chemistry, among other things. We have severe occlusions. The corn has several stages of growth. As we go to stage 6 or 7, the plants are packed as close together as possible to use the space efficiently. When in the early stages, we have good separation. And we believe that advances in robotics and computer vision can focus on these challenges. Now, if you look at scale and occlusion, these images show the scale differences, spatial content, as well as scale differences in the plants. Occlusions is a big problem in both. Think about the field in the left, how you can make an assessment about the existence of plant-based yellow strikes that I saw earlier. The plant on the right, or the set of plants on the right, is more clear, but basically this is the environment we need to work. And if we go to soybeans, we have basically the leaves that you see on the right completely mixed up and cluttered. Why do we need 3D? Some of the measures we would like to obtain are explicitly three-dimensional and most accurately obtained in 3D. For example, we want to have something that is called leaf area index. The leaf area index is associated with the canopy of the plant. And the canopy of the plant is a strong indication of the overall plant health. In other words, a dense canopy shows a healthy plant. A not so dense canopy shows basically a non-healthy plant. We are interested in other things such as stem length, leaf angles with the stem, and volumetric features. Moving to 3D, it gives us enough context and reduces this impact of occlusions. For example, assigning a leaf to a proper stem is a challenge, but if we have 3D reconstructions of plants, this is something that we can do far more effectively. So there are different ways that we can obtain 3D information. We can fly over the agricultural field and take in images. we can reconstruct into point clouds and process these point clouds to obtain metrics associated with these features that I mentioned earlier. Now, having said that, there are systems, robotic systems with cameras like the robot system from a local startup in the area that basically is think about a tall, a narrow robotic platform that drives very fast through the corn rows and can acquire images under the canopy of the plant. But basically, this can be destructive. And one possibility is actually to coordinate these images with the images that we get from the basically from the aerial platforms, or basically fill the gaps that some of these point clouds may have. Or basically, we can go with these aerial platforms and make assessments about the overall situation. Now, this takes us to a problem that Thanasis Baharis has been working. Thanasis is actually is studying 3D reconstruction as an intern at NVIDIA. And it goes back to the problem that I have examined as part of my thesis 35 years ago at Carnegie Mellon on how we can do visual servoing. For example, how we can move the UAVs, capitalize on the uniformity of a field of raw core crops. And if you look at the current methods, basically they follow a predefined flight plan. And this is long and costly, both on power and in financial aspects. So the fundamental question is, can we exploit the viewpoint selection methods for better crop monitoring? So Thanasis has developed, and there is more discussion about these methods in the paper that was published in IROS in 2022 on how we can build this view planning realistic pipeline, which is, can be summarized as follows. We have an initial flight by the UAV in the field, and we have a sparse reconstruction. Then we apply a mesh in order to fit what we have obtained. And then we use a view optimization method, which is a highly nonlinear optimization method, in order to plan a second flight and have this complete reconstruction. In other words, think of the following. I'm moving around the plan, and I'm moving randomly and without any clear knowledge of my dynamics, or basically how the plan may look like. I collect some information, and then I have a method in order to find gaps in these 3D representations. And then my optimization method highlights the missing viewpoints that I have. And these missing points basically are aggregated together in order to plan a second flight and complete the reconstruction. Now, this leads to the second type of work that has received quite a lot of attention, which is mapping and basic phenotyping. This is work of Henry Nelson, Christopher Smith, Thanasis Baharis, and myself. It appeared in ICRA 2023, where we try basically to say, for example, if you see in the image on the right, we have with blue the stems of the plant and then the leaves. And then we can collect all the statistics and data that tell us something about the health of the plants. Now, for example, we try to measure the height of the plants. We try to estimate the location via point clouds. And we basically focus on what we call corner localization and phenotyping. Now, the third piece of work is actually something that Henry Nelson in his thesis is doing, which is actually instance segmentation. We try to segment plants in order to have measurement of the different traits, and we'll try to have highly scalable methods that can help us in having large-scale instance segmentation. And the outcome of this can be shown in the figure that we have at the bottom. And this is particularly challenging because, as you can see, and as the different colors indicate, we try to extract a lot of information about the plants and how basically we say, oh, you know, these plants are more important than the plants, for example, that you may have on the edges of the field. Now, Henry has worked also on semantic segmentation. By using neural networks, we can segment plant instances and derive the semantics, allowing to have detailed metrics for individual plants. Here you see the leaves and the stems. This is ongoing work, but basically we achieve the following dice scores. Like for instance, segmentation, we have 0.93, and for semantic segmentation, 0.96. But if you go to stage 7 or 8, this data change significantly because we're talking about very cluttered sites. Now, I would like to close this part by saying efficient cultivation of cornfields can translate to big economic impact. Precision agriculture or digital agriculture can improve cultivation via the early detection of nutrient deficiency in crops and effective intervention, and robotics in creating efficient systems to detect nutrient deficiency from 3D point clouds can focus on problems in visual surveying, plant localization, and phenotyping. And again, when I was asked to speak, I thought, look, we are trying to localize plants, and we try to extract a lot of traits and characteristics of these plants, and also the issues of semantic and instance segmentation. Some of the future directions is actually we're looking at, we're preparing a PAMI paper on how we can have improved view planning for better and more efficient data collection. In fact, this is joint work with Professor Giannakis from electrical engineering, and focus on the optimization process. Try to see basically, since the plants move under disturbance such as the wind, how we can incorporate the noise in the models that we use, and how we can have efficient scaling for the visual surveying methods via divide and conquer approaches. So this covers the precision agriculture part, which is really ongoing work, very exciting. And in fact, something that when Zermas told me, is this computer vision? When he started his PhD thesis, and I told him, you bet. And basically some of the most challenging problems that we have faced in all these years we're doing work in this area were found in this domain. So I would like to spend around 10 minutes, even less, on this system, which is running at the state of Kansas for the last 8 to 10 years. It runs 24 hours, 7 days a week. It has survived tornadoes and other extreme weather situations. And it even surprised us ourselves when this basically produced these results. So the idea is the following. There are federal regulations on how many hours a driver of a truck can drive and how many hours can rest. Especially in the winter, drivers have a tough time finding rest areas. So there was a Federal Highway Administration initiative a few years back and several state initiatives in order to have systems, sensory systems, and algorithms that are going to find how many empty spots are available for trucks and how basically we can notify the drivers about these available spots. Now, this is very important because it can improve the rest time for the drivers, and it can have a pronounced impact on the overall, basically, traffic safety of intelligent transportation systems. Now, I'm going to talk quickly about the motivation, the system, how the system works, where it has been deployed, and some of the results that we get. So contractually, we were obliged to have something that was non-intrusive, have complete 24-hour, 7 days automation of direct detection of parking space status, accurate and scalable, requiring no human intervention or rezeroing, cannot interfere with facility during installation or maintenance, and develop an architecture to aggregate, archive, and broadcast information to roadside, web, and in-cab mechanisms. And in fact, it was a challenge because basically as a University of Minnesota, we had to be a major deployment contractor of a sensory and algorithmical system. And we needed to do the maintenance. And in fact, right now, for the next 6 years, we are the main provider for the state of Kansas, Department of Transportation, of basically this overall architecture, which is quite unique. So think of the following. Trucks are going in all weather conditions, and they are parked. If we are lucky, the site has basically these lane markers or rest area markers, and then they are parking there. Now, if you look in Minnesota, especially in the winter, you have a lot of snow on the ground, as you expect, and you have trucks, as are indicated by the red arrows, which are parked on the sides, which can be not the safest selection of a parking area. So the architecture is actually, we have multiple cameras deployed and reconstruct the scene in 3D. It measures the space occupancy directly by seeing the vehicles present. And we need to be robust to sharp shadows, partial occlusions, and other light changes that traditionally confound non-3D image processing techniques. And we cannot have recalibration because we are hundreds of miles away in Minnesota. We cannot travel every week, nor we can have rezeroing of the system. Here you can see we have to build basically the site installations. We have subcontractors that mount the cameras. This is an area in Minnesota where we built a prototype system. We mount the cameras. We need to calibrate them. We need to calibrate them in a way that are basically robust to wind disturbances and other weather-related phenomena. This is an installation 2013. You can see another location, basically in Minnesota, the Big Spunk Lake. Again, 2013. And this is basically just looking at some of the data that we use. Look at the image basically on the left. White snow has covered everything. We have 21,000 parking events, 20 days of varied environmental conditions in winter, and we achieve a per space detection accuracy of 97.87%. And on the right, you can see the reconstruction, and on the left, you can see, so all the markers that we can use have disappeared. Let me show you a video So you can see the easy stuff. Basically, the red indicates occupancy. And then we're going to move to tougher, more extreme weather conditions. Think about doing that in Kansas, where there are no markers, and basically the trucks can park sequentially, so they're not parked next to each other. We're very grateful for the state of Kansas because basically it gave us the opportunity. You can see here in snowfall. And especially when the trucks are not exactly parked between the lanes. So as is the case, is with many of these systems, we're missing some vehicles. We're missing vehicles, for example, who are maneuvering, as you can see in the middle. We have problems when we have lane encroachment, but basically this technology has proven the only one that is meeting the federal standards of having an accuracy of more than 85% accuracy. Now, a common criticism that we receive is actually that this is fairly expensive, but in the end, for example, if you look at the alternate methods of basically having counters at the entrance and at the exit, and you need to have people who are going to go and re-zeroing the counters, this has been proven to be the gold standard in this area. And in fact, we are in discussions with other states in order to have these methods. Now, if you look at the persistent per space parking status is greater than 95% accuracy. If you see, we don't need the person there to do recalibration or zeroing. And we have continuous operation at 23 sites for the last 8 years. And in fact, if you look at this project, it's ongoing for more than 10. Now, the state of Kansas, just to give you, this is the data we have to deal with. You see the trucks basically parked one after the other, sometimes in different directions. And then we try to find the appropriate gap and the vehicle that maybe fit in between. So it's a far tougher environment and something that it has worked equally well. So I would like to close. Hopefully I'm still on time. Robotics is extremely exciting. But basically, if we forget the robots, we have all these sensors. They give us so much information. And this is where I think the next challenge is how we can apply some of the recent developments in federated learning and other techniques in order to have this capitalization on this data, on these massive amounts of data that is coming forward. I'm a firm believer in the robotics plus X paradigm. It's very important to produce robotic systems which are data-centric. And in fact, as a director of the Robotics Institute, where we have a robotics master's program, which is the fastest It has become the third largest master program in the college. We want to produce roboticists which can not only do the harvesting, the process, the analysis of data, but also the extraction and the design of all these embedded robotics/computer vision systems. Thank you for your attention. Any questions?
Thank you very much, Nikos. Any questions from the audience?
Could you ask me what computational power of the platform?
Do you want to
What's the computational power of the platform that's in the architecture?
Okay, actually, there is a question from the audience, and what is the platform? And that is,
Computational platform.
what is the capability of the platform, and for the drone system, or for the agriculture, or for the agriculture? Yes.
Can you repeat the question, because I didn't hear the first part?
I mean, the question is, what is the platform and what is the capability of the platform for the agriculture system when you try to do the 3D reconstruction and phenotyping?
So basically, we can do, I will say, if I understood the question, is actually what is the capability and how much we can do.
Yeah. Basically asking.
Am I right?
Yeah.
So basically, we can cover, just to give you an idea, an average size farm in Minnesota is around 1,000 acres of corn. We can do this in a couple of days, because basically the drones we use, they fly for 30 minutes, and then we need. So in 2 days we can have, and there are a few startups which are basically they try to embed hyperspectral data and fuse them, and basically have more accuracy. If we're looking at phenotyping, we do one plant at a time. So basically, this will take a few minutes in order to do the 3D reconstruction.
And
I don't know if I answered the question.
And what is the platform like? What is the computational power, or some other sensors and the speed, or what kind
Yeah,
of
that's a great question. We're trying to do this on the edge, but a lot of the stuff is on an NVIDIA platform offline for the phenotyping.
Okay, and another question is when doing the phenotyping, and when the crops are begin to grow and when they begin to merge to each other, does it affect the outcome of the phenotyping?
Absolutely. And in fact, there is some work that Baharis is doing that shows basically probably we can do this till stage 6 or 7. But after this stage, the phenotyping, you need a ground platform. You need to go under the plant. So and also we did some efforts to do plant phenotyping for soybeans, but due to the structure of the plants and how the plants are distributed in the field, we have not been successful. In fact, we focus more on the use of pesticides in soybeans.
Okay, got you. Yeah, that's very helpful information. Any other questions from the audience? Okay, if no further question, thank you very much, Dr. Nikos, and we really appreciate your talk. Yeah.
No, thank you very much, and I hope you enjoy the meeting.
Yeah, we enjoy. It's held very well. Thank you very much. And that comes to our last speaker in the morning session, Dr. Jason Kozel. Well, you are setting. I can introduce you. Oh.
Should I connect this to audio?
I think so. Yeah, you can connect with this one. It doesn't matter to us actually. For the in-person ones.
Okay.
Can you guys hear me now on Zoom?
If they cannot hear you, oh yeah. Right now it works. Yeah.
We just that's like 3 NeurIPS papers right there. We solved it. All right, sounds good. All right, cool. So just again, basic analytical solution, and we're able to compute like. Sorry, that was my mistake. I won't touch that again. We'll now compute or estimate like against ground truth. We estimated 0.292 meters. Ground truth was 0.26 meters. I don't know exactly if that's just more like a human estimate of that or real ground truth, but close enough. Which is an estimate, an error of 0.03 meters, 0.032 meters, right? Which is quite within sort of error margin to be able to estimate and plan for grasping. Like that's the idea here, right? But still, maybe we want to even reduce that error further. So how could we reduce the error further? We can, instead of, we're there, yeah. So instead of just taking 2 measurements, Z1 and Z2 or Z10 now at 0.38 meters, what if we sample that 10 times in the middle, and we're able to track that object, with, again, sort of basic video processing the whole time, so that we can compute a least square solution. And if we do that, we're able to reduce the error to 0.012, right? And again, this is fairly, one assumes in this case, you're doing some notion of video object segmentation as part of the processing of your vision stack. But even if you're not, we'll talk later when just basic object detection can get you this far as well. But at this moment, why don't we take an interlude and note how in classical visual servo control versus video object segmentation based visual servo control, where we take these basic ideas and are able to update the sort of policy that's learned in visual servoing from sort of classical methods with one that's based on this sort of like real-time segmentation-based update, Hadamard-Broyden update that we proposed in a WACV paper a few years ago, to be able to, let's say, sort of like learn control policies from 2 cameras and 7 actuators on the fly to center this particular piece of laundry on the floor. In practice. If we had used the classical update, we diverge pretty quickly. And here you're seeing it tracking Brent's different sweater than he's wearing right now, but gray and white striped sweater on the fly, in a room, and sort of learns that on the fly and is able to use these basic ideas in practice. Also to do mobile object grasping as well, right? In these cases, it's going to do, the kind of like cleanup scenario based on these segmentations. You sort of like first servo it so it's in the center of the field, then estimate its depth, plan the grasping algorithm, and then move on to the next object. All right, awesome. So, all right, now, so that was an example where it worked pretty well. Here's a case where the analytical solution that's just based on that basic trigonometry sort of fails, right? So the object of interest here is a small marker that is in the middle of a cluttered tabletop or floor, very much like my playroom looks in my house with my daughter. Here we have an error. We find using the same ideas, basically with say maybe 3 samples or 10 samples or whatever. We find an error greater than 0.1 meters, which is just not, especially it's greater than the lateral diameter of the marker itself, but it's just not resolved enough to actually be used for path planning. So how do we solve this problem? How do we address this problem? Well, we take these basic ideas, these basic things we've learned, and we learn a object depth estimator network from simulated examples, right? So the basic idea is going to be that we'll feed in a bunch of binary segmentation masks to this ODM model, or learned object depth model, and we'll feed in addition, camera positions, given to us by odometry or something else. If we don't have odometry, we could use structure for motion. That kills our argument of minimal but extra processing, but at the same time, it's plausible to do that. And we'll be able to feed this and predict these object models to reduce this error from 0.114 to say 0.003, which is well within the resolution we need to do grasping and planning, for example. And interestingly, an interesting point is that we'll be able to do it in a way that we are able to adapt to the typical errors we expect from video object segmentation, or even like just jitter in the camera, for example, or in the future, the types of errors we'll find in object detection jitter as well. The network itself, actually in Brent's original slides, he didn't even include the network because it's so simple, so trivial. It's like there's nothing special here. All we're doing is inputting camera motion, feeding it all the way down to the end, and then we're using a bunch of conv layers on these binary segmentation masks. Nothing straightforward. Relatively small input resolution, 112 by 112. I.e., like I think this network trains in 2.5 days, roughly a little bit more than 2.5 days, on something like 15,000 examples. But ultimately, it's able to then go and be used to do processing on these binary segmentation masks. Here's just some examples of the method working on uncluttered scenes for typical objects. These are like typical kitchen type objects, but we've tested it on like the YouTube VOS challenge, for example, as well. Or sorry, the YCB challenge. So how do we train this network? This is part of the innovation, or the angle we took here, is that like since the input is only these arbitrary binary segmentation masks, and there's no sort of semantic underpinning in those segmentation masks that we need to latch onto, we can basically sample them ad nauseum, right? So we basically built a generator that generates these objects by scale, or at scale, by varying a bunch of parameters like SP, the object size, the number of points in the actual convex hull of the object, or perimeter of the object. And then for each of the points along that convex hull, we'll randomly sample them in this square grid, and then ultimately close that gap and then fill it in based on the object size. And then we'll sample it at the dmin and the dmax distance, either choosing like fixed boundaries or you sampling it as like a Bezier curve as well. All right, so we can sample these so that during object training, for every batch that we need to generate, it's pretty trivial to go and generate a brand new batch every time, and that so we can train it at length, right? So as far as like what we actually estimate, we actually train 3 different models based on small variations in the loss function, right? So the one that we've talked about essentially so far is this one at top, ODND, like a direct depth estimator based on that mask, right? So it's trying to actually predict the absolute depth, and the input signal we give it is absolute depth. It's good because it's sort of straightforward. We can understand it. It maps directly to that least squares method that we already talked about. And it does learn sort of an absolute prior that we don't have to do any other processing on afterwards. The second one is what we think of as normalized depth, which just sort of divides out the total range of depth in the input signal that we're going to be, in one batch or one sequence of samples, which makes the estimator dimensionless and allows us to have more broad applicability, right? I.e., like, tabletop environments versus automotive autonomous vehicle depth estimation, for example. But it still is predicting a sort of the range of possible predictions is large. And then the last one is what we call relative scale, ODNL, which allows us to move even farther to, essentially is predicting in relative coordinates in the image plane. So it's the simplest prediction, still dimensionless and also broadly applicable, but it does require that we go and like undo these dimensionless transformation that we did beforehand, but that's a simple computation. So to benchmark this work, we threw a lot of stuff from YCB onto our floor and tabletops and so on. We used the HSR and got a lot of examples. We also used Cynthia images as well and generated, I don't know the exact number, but I think it's on the order of a few thousand samples per 3 different settings, if I'm remembering correctly. And we're able to demonstrate that, the ODNL, right, that like fully dimensionless operating in relative pixel coordinates is the best among the variants we chose. and it's the best almost by 50% to the least squares solution, right? So why is that winning? Well, if you look at the paper, there's a lot of sort of like nuanced ablation results that we showed, but basically, like we believe the the ODM model, like that, the trained model is able to filter out, if you will, like learn about these noise variations in the segmentation itself, and be able to smooth them out over time. If you're interested in this work, it is available on GitHub, including the data generator, and other models as well, at this link here. But you say, we don't want to run segmentation, or we don't run segmentation. It's too expensive, or it's error prone, or the scene's cluttered, and so on. How about just detection? And I say, sure, we can do it by just detection as well. In fact, the analytics are just the same. It's like the analytical model is essentially the same as well. These are the results from a CVPR paper a couple of years back, right? So imagine the HSR is being tasked with something like get the cleaner, right? This is the view from the HSR. And only using the RGB onboard camera, we want to be able to essentially plan how to go onto the shelf and pick up that cleaner if we have an object detector that can detect the cleaner from the iced tea, from the Domino sugar box, and so on.
For motion and detection. Using our motion and detection model, we'll show a few different examples. Assume that we have an object in view of a camera. Using object detection, we can find the bounding box for the object and determine its scale using box height h1 for the camera's current position p1. Notably, if the camera moves closer or further away from the object, the bounding box scale will change with the new camera pose. If we can measure the relative change in camera pose, for example from vehicle odometry or robot kinematics, we can compare camera motion to changes in scale to solve for depth using the following solution.
So I just had to give Brent the kudos and let one recorded snippet there. This is just to show, like, you can do it from optical expansion, like I showed in some depth earlier, but you can also do it from lateral motion, right? The actual mechanism for the computation is the same, basically, or very similar. And importantly, we can train another network as well on this, right? So the actual OD, in this case, we call it object depth from motion and detection, right? So the input are these detections at the top there, and the bottom half here are the actual camera locations. And these are input to a depth prediction network again. And we're able to go and predict either absolute depth, or dimensionless depth as well, like we did last time. In this paper, though, we did change the style of the network to go from a sort of standard feed forward, here are all of the fixed number of estimates I'm going to get, to an LSTM style network that will incrementally revise and refine the estimate of the object depth based on the most recent readings from the, or inputs, if you will, or state, if you will, from the data. And we train this model much in the same way we train the segmentation-based model, right? Like generate a huge amount of semantic-free bounding boxes. We vary their depths. In all cases, we have the absolute simulation-based or synthetic-based depth values for tracking and so on. And as long as we get the range of possible motions and expansions, this is sort of like a fully sim-to-real applicable model. This is why I put it in quotes, but sort of like it's a foundation depth model based on object depth or object detection or segmentation. So you see here, working like cell phones in a garden, or maybe like for the crop signal we saw in Nikos's talk, or in the home here, or also in AVs and so on. We benchmarked this one much in the same way as well. We got a bunch of samples, 20,000 examples across 4 validation sets, using household items, using YCB items, and so on, and demonstrate. I find this a little bit of an interesting result. The detection-based model not only outperforms the segmentation-based model, but it's also trained in 4 minutes, not in 2.5 days. And so like 20,000 samples and this was done a couple years back. So I think we're operating something on like a 1080. We're not talking like a massive V100 or something like that, right? So like really small network to run at, if you want, then you can train at the edge on the fly to learn control policies on your hover, on your robot, right? That's the key message. I gave you this teaser earlier, but it works across domains. This is one model that was trained and it's deployed in these AV cases. It's deployed on the HSR, the home service robot. It's deployed on cell phone cameras as well. All right, so some summaries, right? So free depth or everyday depth from motion and detection or segmentation, right? So it's fast, 1,000 object depths from detections, given the detections in 4 milliseconds, 4.3 milliseconds. Wildly low cost, can probably even be trained on the CPU locally, if that's a constraint. It is in quotes for free, right? Like minimal extra computation, and it's domain invariant. But obviously there are some disadvantages. So we don't get it's not dense, right? There's no background depth. And we don't currently compute that, although we have some ideas on how we might do that now. You're only getting depth for those objects, and you do need to have some notion of the odometry, or so the embodied agent movement. Okay, so I appreciate your patience with the Zoom hiccups here, but glad for the invitation, right? And happy to present these ideas, right? So in summary, this research vector seeks to sort of enrich a physical platform's ability to interact in an computationally efficient and flexible manner with the environment. This work specifically was funded mostly by Toyota Research. You can find everything here online, and if you are interested in sort of a little bit more general discussion about my research thoughts on how humans and machines collaboration is going to be evolving, here's a link, and I'll just end with an advertisement. So my company has a booth here, 1519. Voxel 51, we make the software package that is open source and will help you get your next CVPR paper for sure. Also, we're hiring 8 machine learning people now. Well, 7. One of them was just hired he's sitting over there. But, and also I'm hiring 3 or so PhD students in my lab. So happy to talk and happy to take any questions. Thank you for your attention.
I have a question. When you do the grasping, you show several very successful examples. For the grasping, how can you explain a little bit more in details? How do you decide the orientation of the grasper?
Brent could probably answer that since he developed it, but I guess it's probably along, it's sort of basic ladder, whichever axis is the smallest axis based on the configuration of the arm. But yeah.
So you grab the narrowest axis possible. So you have a segmentation mask projecting the grippers into the edge plane, and you can just rotate that to find where on the segmentation mask. So you get the least interference already centered on the object, so you can grab it. And in case of bounding boxes, you don't have as much information, but it is a robot, so all you have to do is rotate your wrist, and the bounding box rotates. So you can actually find the minimum width of that object there. And this works for even the drill and device data set, which is kind of wild. So it's not completely box.
Yeah, those are understandable. For some, I see some other objects like bows. Are they doing the same? Like they are around, and probably most time you are actually grasping the edge of the bow. And in that case, how do you decide the orientation?
So the bowl, you would probably want something a little more advanced than this, unless you have a very large gripper. But in that case where you're getting outside of even the grip width of the robot, you probably use a different strategy for gripping.
Okay, thanks. On YouTube, there's Jia Lin, and from Jia Lin, there is a question: can depths be predicted simultaneously when there are multiple targets of the same type of view, for example, multiple pedestrians?
I think the question is, can depth be computed simultaneously for multiple objects detected in the scene? And I think Yeah, the answer is yes, 100%. Yeah, you can do it. I mean, it's not free. You have to do it for both signals, but you can definitely do even segmentations. You can compute it simultaneously. So for example, if you had segment anything, you could, and like you had some notion of like running segment anything, and then like, a camera phone or whatever, the robot arm moving into the scene, you could simultaneously compute depth per segment of segment anything, for example.
So does it affect the speed much?
No, these networks are so small. They're tiny networks. Yeah. Yeah.
And what about your data set? And is it a very big data set or is it relatively moderate size?
Tens of thousands.
Thousands.
Yeah.
Okay.
Yeah. So it's relatively small.
Is all simulated or
All-
is real?
All simulated. Yeah.
Any other questions from the audience? Okay, if no other questions, thank you very much for Dr.
Thank you.
Jason Cotto, and that's end the morning session.
And then we could have done it in single.
Can you hear me?
Either way.
Michael? Should I call you? Oh, you are muted.
Oh, I didn't want to unmute. I thought everybody was at lunch, so I thought I would. I'll test things. I'll turn everything off.
Muted sound. Can you hear? Can I speak again?
Oh yeah.
Oh, I can hear you. I can hear you.
Okay. I just wanted to check things out to make sure it worked.
Okay.
But I guess it does.
Fine. Actually, between the first small session in the afternoon and the second one, there is a 10 minutes break. We can still do another test.
Okay. Yeah, I wanted to see like with the camera, like what's in the view. Like, let me see. I don't want you to see the ironing board there. That's better. Okay. All right. Thank you.
Yeah, sure. Talk to you in the second session.
All right. Bye-bye.
Bye.
Do you know what's the matter with the camera? No, with the audio, with the microphone, when it sometimes stops.
We don't know the reason. Suddenly stop 5 seconds, and after 5 seconds, we work again. But it indeed bothered me quite a lot. And sometimes people talking through this one cannot work, that does not work. We need to use something like this guy and connect with the laptop. And otherwise, if the person that guy is talking in person, we couldn't connect this guy. If we connected and the Zoom people cannot hear, YouTube one people cannot hear. So it's a little messy on the problem.
Okay. There's a button. Does this do anything?
I don't know, but I believe that it's on right now.
It's always looking red, which sounds like good.
Yeah.
It doesn't look good, but I think this is not an indicator. Yeah. Okay, but there was no update from the organizer somehow.
We tried to find someone, but no one is coming. And even they come. After 5 seconds,
This was true in the other rooms as well, so I've seen this in the other rooms.
Oh, they come here to check that guy. There's sometimes they go away. So I don't know. It should be okay. Maybe 5 seconds in the middle.
Yeah, if it comes back, it's fine, but it's fine.
Yeah, in the second part, in the last speaker.
Ideally, you would have a switch when you can press it, then it will come back immediately. I don't know.
And we just reflux every time. Okay, stop a little bit. Let me reflux. Not always. Occasionally. Yeah. So there's a guy from Greece. Actually, he is in Minnesota, but he's currently in Greece. And when he gives talk, that was really bad. Okay. How many students do you have right now?
Yeah, 10.
That's good number. Wow.
I think so too. So I don't want to have many more because I'm actually quite busy with them. But it's also a good number to have some output.
Yeah.
So how is it in your group?
I'm recruiting 5 and I have 3 right now. I expect my group will grow to 10 as well.
We have easy funds for recruiting. Okay, this is good.
Actually, that is why I'm evaluating for tenure and promotion, and they asked me to give them some names that who knows my research area, who is in the same research area, but we didn't work on paper together, we didn't work on proposals that we want to give them your name. Probably they didn't contact you.
But so far there was no contact. I'm not sure if they still would.
Yeah, some people told me they contacted like the young is Aloy Wallace, and they contacted him. He told me that. So it seems they contacted several people, but
okay.
you know,
I would have imagined they would contact people from the US. Or do you think they contact people internationally?
Oh, for full professor, they prefer to contact people internationally.
Okay.
But for maybe for
I don't know, for associate professor, maybe just people local. I don't know, actually, but yeah, anyway, that is something like I try to keep some people which are not my co-authors, but in the same area, we kind of know each other. So that's and after my
Sure,
evaluation, and we, I really can work with you more. It's very
What is your latest research? What have you been doing?
Yeah, we work on something like agriculture research, and we look up something like autonomous driving. And I have some research projects from China, from foreign companies.
So you said agriculture. Is this
that is not agriculture. Agriculture is from farming. And
but this autonomous driving is not in the fields, but this is on roads.
And for agriculture, we work on several different things like factory reconstruction for cattle. And we want to robot, the ground robot and the air robot, and we try to cover the field with 3D space. And we try to track issues from the 3D construction model to build that and that is from the carbon and from the almost that to do the online sensor is for motor companies to work on something like on the road and having facing on the road, and we are actually using the camera's calibration model to try to calculate the place that's the distance of the ground plane. And using that as the input, as the negative currency as a file, and so that is the that from the one company.
So this project directly funded from this companies. Is this pretty easy to get them, or how do you start? Do they come to you? Do they ask if you post the proposals, or do they come?
I need to write a proposal, but I first need to introduce some of my research. If they are interested, they ask you to submit a proposal. That is PM for companies and more commonly like that, and for government, it's very some proposal. But in the US system, people don't care much about industrial training. People care quite a lot. And the government, I don't know whether it's the same as Europe.
Okay, I think everybody has a mix of funding sources. There's always some industry funding, but there's also always some government funding. Most people have a mix. You know, if some company is doing something that has the potential of funding some project is good, there's some government funding, then people also apply.
Actually, we don't have the industry funding, but we have government funding, that is okay. So probably have
Nice.
Because industry is really small, maybe 100,000. For government, it's usually something like $5 million. Last year we have a project from the military that is 5 million. 5 million.
It's 4 minutes before the start.
Let me see. Oh, the person is here already. Oh. So now you don't introduce the wrong person. This is the guy. But I need to work on something. I need to use my laptop.
Actually, we need to bring it on screen, right?
Who is here? In the morning, we try this one. So that's to be safer. Okay.
Hi there, can you hear me?
I can hear you. Can you hear me?
Great, yeah.
Let me have a double check, and so I need to try to use another voice result. Can you hear me?
I can hear you, yes.
Okay, great. Yeah. Perfect. Can you try to share your screen?
Yep.
Let's see whether you have the.
That looks good. You see all that?
Hey, Mark, this small session will be introduced by another organizer on the Dr. Friedrich from Dover, and just to let you know.
Okay.
Hello, I'm here.
Hi there. Nice to meet you. Thank you so much for the invitation.
Sure. Yeah, it's our great pleasure. Let's see. Oh, great. Yeah, it's already there. I just need some navigation to make it big. I think this. Oops, no.
Somewhere. Down a little bit. If you click on view options, I think click on it, then I think you can see full screen.
Let me first begin to record. Otherwise.
If you click on view options, I think you can.
Yeah. Great. Yeah. Okay. Fine. No.
Okay. I would like to welcome you back after the lunch break. So we have a very nice lineup of invited speakers in this afternoon. And we will start now with the first of the presenters. So our first presenter now will be Professor Mark Campbell from Cornell University. So he works also in the area of robotics, including spacecrafts and UAVs. And well, also something that is, I think noteworthy is he led a team on the DARPA's Urban Challenge of a self-driving car team. And basically he was one of the 6 finishers to finish the race. So his topic today will be about deep learning, and we are very much looking forward to his presentation. So Mark, please, if you're ready, you can start your presentation.
Okay, great. Thank you again for the invitation. I really appreciate it. Sorry for not being there in Seattle, one of my favorite cities. But I hope everybody's enjoying themselves. So I'm going to talk a little bit today about uncertainty quantification for this problem called visual localization. And I'll get into that in just a minute. Just to acknowledge a couple of my students, Jinan and Chiwan, who has done a lot of this work that I'm presenting on. Okay, so what I'm going to talk about, I'm going to talk a little bit about, just briefly talk about uncertainties in deep learning. This is mainly just to give you an idea of my background and sort of where I'm give you some context of how I'm approaching this. And then I'm going to really kind of talk about 2 things. One is I'm first going to introduce the Ithaca 365 data set. If you haven't seen it before, it has some unique attributes, particularly in repeated traversals, but also in different kinds of conditions, sunny, rainy, snowy, and things like that. And then I'm going to get into this visual localization case study, and we can take advantage of this data set because we drove the same route multiple times, really over COVID. And it's just a rich data set for us to explore what kind of mistakes can feature-based deep learning networks make, and is there any way for us to kind of predict them? And that's really kind of what the subject of today's talk is. Okay, so first I'll talk a little bit about uncertainties. And again, this is sort of just setting the stage of my background. And my area really is in robotics. I collaborate with a couple of people who actually do deep learning, Kilian Weinberger and Bharath Hariharan, both from Cornell. And what we particularly like is trying to find problems at the interfaces of deep learning and perception and robotics and things like that. So I sort of use this figure just to give an idea of the context of an autonomous system and where we live. So on the left-hand side,
we lost your voice. We need to reconnect and try again.
Okay.
Can you try to speak?
Yep. Can you hear me now? Can you hear me now?
Could not hear you. Oh, now it's here. We can hear you.
You can hear me now?
Yes.
Okay. And did you hear the beginning part of it?
Yes. Yes.
Okay. All right. Yeah, we have some thunderstorms coming through the Northeast, so it could be our internet. So definitely stop me if there's any problems. Okay. So on the left-hand side here is sort of the data processing. You have the raw sensor data coming in, and I've kind of highlighted some potential errors. You might have some misalignment of sensors. You might have errors in actual return. This is trying to detect pedestrians walking in an area. And then you have sort of this middle area, which is perception and reasoning, where you're really trying to fuse multiple inputs together. Sometimes there's deep learning networks to try to do both of these together. Sort of this middle block is where I've spent a big portion of my career looking at sensor fusion and integration of different kinds of inputs. So these are just a couple of examples that can be in those kinds of problems that can impact things like tracking, so incorrect classification or misdetection, occlusions, and those types of things. And finally, moving into the planning aspect of it, you typically in self-driving cars, for instance, you might want to predict, and this is where perception again comes in, you might want to predict where other cars are actually moving and use that information in planning and control. And so these are just a couple of different examples of what it is. So I sort of, I've done a lot of living in this block and worked a little bit on the machine learning block on the left-hand side, but also a lot of collaborations there. Okay, so so I sort of have this top flow diagram where I sort of classify this as most deep learning and model-based estimation. So deep learning, I think everybody knows, and model-based estimation, this is sort of column filtering or sensor fusion, typically with uncertainty models. And that's, again, sort of where I have lived. And so typically when you have a deep learning network right in here, you have some type of, let's say, query image or something like that, and you get some type of prediction from the network. And that goes into, let's say, your perception and estimation block. And so again, you could sort of combine these together in different kinds of ways. Let's, for the sake of today's talk, focus on the fact that we're not doing that. And so what I always tell my students, especially my class, is that we can do a lot in this perception estimation block, but what I really need to know is I really need to know what kind of errors these predictions or these sensors actually make. So if you buy a really good accelerometer or something like that, or if you study GPS, you have an idea of what those errors are going to be. So what I'd really like to do is this bottom block, and instead of just doing a prediction, I would actually like to get a likelihood model. And so I want to get a prediction, but I also want to get a sense of what those errors might be. And so that's sort of where we're heading in today's talk. Okay, so now that gives you a little bit of context on my background. So let me talk a little bit about the Ithaca 365 data set. This was presented at the CVPR 2 years ago. There's a website down there at the bottom. And this is the center here is a map of Ithaca. And the red line here is the route that we took. And so sort of our building is sitting in here. So what we do is we'd actually drive downtown, which is all around here. So we'd have a little bit of downtown area with traffic lights and multiple lanes and things like that. The same thing as going out here. And then we drive all the way out here, this is a main highway that comes all the way out here. We get off the off ramp, and then we drive through sort of suburbia as we come through here, and then finally through campus, which is right in here. So typically there's many students in here. So the interesting part about this is that we actually drove this many times, especially over COVID. And so we have at least 80 traversals that we've published. We have more internally. And so the cool thing about this is if you drive this 80 times, you can take a single scene, which is shown here on the right, and I can give you 80 different views of what that scene looks like over, you know, a 1.5 year period. So you might have some sunny conditions, you might have some rainy conditions, you might have some snowy conditions like you have in the lower right. So it's very interesting, rich data set that allows you to do that. Allows you to explore different kinds of problems. We collected high precision GPS. We also had some differential corrections based on an antenna on top of our building. So it's really pretty good in terms of GPS INS. And then we collected LiDAR data and camera data. We've done some, especially trying to label the roads as well as objects in the scenes as we go through. So it's been a fun data set for us to play around with. So I just have a couple slides on this and how the data, a little bit about the data and how it could be used. We were particularly interested in labeling this with sort of amodal labels. And so the idea here is on the left-hand side, you might have a road, and that road is both snow-covered, but it's also a road. And so you might have 2 different labels for that. Another thing, if you look at the right-hand side here, is that we would outline where different cars would be, as well as where the road is, because we're particularly interested in cases where, let's say, the road is completely covered, either due to snow or due to traffic, and the question is, if you don't have map data, will the robot or car know where to go? So we did a lot of work in sort of looking at foreground and background as we went through, and so it's a very nice data set especially for occluded systems. So that allows you to different kinds of problems. So this is an example from 2022 ICRA where we are actually doing shape completion on occluded objects with that data set. Another thing we were able to do is translate sort of snowy images to or night images, which are, as you'll see, particularly hard, to sunny images. And so this was in the 2023 ICRA. And so I had sort of this movie here just to give you an idea. So on the left-hand side, this is I'm going to show you a movie here of these are just the true images during a sort of shortly after a snow in Ithaca. And the right-hand side, we converted those to sunny images in the hopes of making things like object detection and those types of things a little bit better. And so we showed in the paper, you can actually make them a little bit better. So still some challenges with this. I mean, one of the nice things about this is that we were able to coarsely align the images to develop this network as we go through. And it's really can be used for improving localization, particularly in snow-covered areas, as well as some of the detection and tracking. And then finally, some work. This was work led by Yorong Yu, who was one of Killian Weinberger's students. And what they worked on was basically using the repeated traversals to develop and iteratively self-train 3D object detectors. The idea here is that if you many times when you're driving, you drive the same route to work, from work, to the supermarket, to the gym, and those types of things. And so you should be able to learn a little bit more about your environment that way, particularly in terms of where the hard to see places are, and those types of things. And so this is one example of what we were actually trying to work on. So those are just a couple of highlights of some things that we've used the data set. But what I want to talk about today is I really want to talk about this visual localization and uncertainties in deep learning. So let me talk a little bit about this. So this is kind of a busy graph, which I'm not going to get really too much into, but let me sort of highlight sort of 3 components of this. So the first one here is that you got the prior traversals here at the top. So think of this as that, this is one 15-kilometer route in the upper left. This is another 15-kilometer route. One might be during sunny days, one might be during snowy days, and so on. So then the first is, and this is mainly due to computation, is we had a global feature matching through that whole data set to find out which images were actually close enough. And then, sorry, a little bit of spelling area there. We did basically a little bit more fine tuning of a neural key point matching using some more recent CVPR papers and things like that. So in the end, we would get typically what we thresholded, it was 10 images where we had a certain amount of key points in terms of the top matches and things like that. So this is our visual localization pipeline. And I should give some context here. And that is that, again, our goal here was focused on not necessarily building the best visual localization approach. We wanted to have a feature-based visual localization that we sort of understood and we could dig into. But our goal really was uncertainty quantification. The question is, could we predict when that network made errors? That's really what we were particularly interested in. And then could we generalize that? So, so that's kind of what we were focusing on. Okay, so how does this work now in terms of the visual localization if you haven't heard of this problem? Okay, so think about it this way. On the left-hand side, we have we actually use 9 databases. So we use sort of 3 sunny databases, 3 at night, and 3 snowy databases, okay? And so these are a couple of different examples in here. So you got 9 databases. We typically pulled out about 13,000 images on each of those. And so that's how many databases are in there. So that's on the left-hand side. On the right-hand side, you're driving along, GPS is not working. So you're sitting down here. This is sort of in the downtown area of Ithaca, driving by the old State Theater, classic State Theater. And the question is, you want to know where you are. And so what you need to do is you need to take this query image and figure out which of those 13,000 times 9 images is it closely aligned with. And then from that, each of these images come in pairs. I have an image pair, but I have an XY pair in terms of latitude, longitude. And so I'm just going to use that as my position. Okay. So when I actually do my key point match, which is actually shown right in here, I might have a top 10. So then the question is it the top 1? Is it top 3? Do you want to do some reasoning about those top few? So there's a bunch of interesting questions that are still there. But what I'll focus on right now is just the top 1. Okay. So that's the visual localization problem, and that's what we're going to kind of use as a basis here. Okay, so the first thing is let's just evaluate this with 3 different data sets. Okay, and so these are now test data sets. So again, because we have 80 data sets, it allows us to really do a lot of different things with the data. And so we use 9 data sets to actually be our query or be our data sets that we're going to try to align with. And then these are 3 additional data sets for testing. So on the left, and so all we did now is we basically recorded the error just to give an idea of how big the error actually is and what it actually looks like, especially compared to, let's say, something like a Gaussian or something like that. So what you have here on the left-hand side, this is test during sunny conditions. You see it sort of, it's plus or minus 4 meters at most. So it actually does a really pretty good job. It's clustered around the center. If we do the 95% ellipsoid for the covariance, so we find the covariance of all these errors and find the 95% ellipsoid, it kind of looks, pretty Gaussian. So it actually does a pretty good job in sunny conditions. If I now look at snowy conditions, you see I sort of crop these at the same point. You can see, well, they're spread out a little bit more here. Okay, and I start to see some shape here. It doesn't look oval as much as it did before. The 95% ellipsoid is a little bit bigger. So you can see that the errors are a little bit bigger, maybe a little bit more non-Gaussian, but not really horrible. But then you go to night. And for computer vision experts, this is probably not all that surprising. But you see now the axes here are now 20 and 20, minus 20 and 20 on each. And you have these different lines going out. And these different lines are basically locking on to certain images, which I'll kind of get into as we go along. So it's definitely not Gaussian. It's definitely much larger and things like that. So the nighttime was by far the most challenging condition. So this is a little bit about the number of key point matches that came from that network, from that deep learning network, as a function of the Euclidean error. Okay, and so I'm just sort of showing these just to give you an idea of what that would be. So the sunny conditions are all the way here on the left. And one of the things I want you to notice here is that almost all of the images in the sunny condition came up with 200 or more key points. Okay. And so, and there was a few outliers up in here in sort of the 10 to 14 meter, but for the most part, they're sort of down here under 4 meters, like we saw before. Okay. What you see at the nighttime is you see a lot of images down here with very few key points, much less than 200, and the errors are getting much bigger. Okay. So the maximum here is 800 to 1,000. So very different than the sunny conditions. Again, illumination really drives a lot of these things, so it's not all that surprising of how that works. The snowy conditions surprise us a little bit. There were some outliers up in here, but for the most part, again, did a pretty good job of it, even giving a lot of key points out to 1,200 and those types of things. Okay, so that gives you a little bit of an idea with the key points, because we were hoping our goal, or one of their goals, was to maybe take advantage of the key points and see if we could actually figure out a way of using the key points to come up with an uncertainty model. Okay, but there were some outliers. Okay, so some of the big outliers were at night. And that, again, that's not all that surprising, primarily because we had very few key points. And so these are two images that are at very different locations in the downtown area of Ithaca. And, you know, there's sort of, it might be a little bit hard to see there, but there's a few sort of dots as we go through here. And, you know, because the lighting is a little bit low and all you really kind of have is some street lights and some shaded buildings and things like that, they actually look somewhat similar to what's actually happening up in here. And so there was definitely some big errors that actually occurred at night. But there were a few things that surprised us. And so this is one of them here on the right-hand side. And that is that in that downtown area near during the State Theater that I had showed at the very beginning with the key point matches, is that there's a ton of key points because of the brick road on the bottom. And this is basically a kilometer-long road. And so if you're dominated by these key points, it makes big errors, even in sunny conditions. And so this is where the big errors were actually occurring right in there. So even though you had a high number of key points, the texture of the road surfaces really created some potential problems as you go through. Okay. So what's next? So what we wanted to do is we wanted to try to use that data and use that knowledge to try to estimate an error covariance. And if we can use have an error covariance, then we can put that into some type of model-based estimator, and then we can figure out how accurate we can do for the localization. So what we did here is we used a formal test statistic to analyze the results. And so this is the test statistic, which is basically a normalized version of the error. And so Z here is just X, Y position, latitude, and longitude. We have Z ground truth for whatever data set we're evaluating. And so our goal then is to find this R hat, find a covariance that actually allows us to capture the errors of what the visual localization from Z is actually giving us, okay? So this test statistic, if this was Gaussian, would be a chi-square distribution. It looks something like this. And I'll get into that a little bit, but there's sort of no assumptions of chi-squared here, but it's a good thing to kind of compare it to. The curve is positive, okay? This thing is always positive. And I sort of think of this as if it's problematic, there are two areas of this test statistic which you can get a little bit of insight to. The first one, and this is the most common one, is up in here. So let's say this is sort of a 5% tail out in here. This is when the prediction errors, the Z minus Z hat, are very
Mark, can you pause a little bit? We lost the voice. Can you try again? Can you hear us? The video broke. He's rejoining. He's rejoining. I don't see it. I sent an email. It hasn't replied. Maybe we just wait another minute, otherwise we can.
Since we lost the connection to our remote speaker, we are waiting until we can reestablish the connection.
Oh, Zoom crashed from his side, actually. Let me, he's joining right now. He's joining. Mark, can you hear us?
Yeah, I can hear you.
Okay, okay. Yeah, let's
Sorry, was that on my end?
We are not sure.
Okay. All right. All right, let me try to share again. Did it crash here? Do you remember?
Is this one? Okay, yeah, this one.
Yeah. Okay. All right. All right. There's a few results I can skip, so I think hopefully it'll be okay.
It's
all right.
okay. We have middle break, and otherwise we just skip the middle break, and you can talk. Okay.
All right. Well, thanks for your patience. So, okay. So I think the last thing I was talking about if you have too large of a covariance, because one thing you could potentially do is just make a really large covariance, and you would pass this test statistic all the way out here. This would sort of make it a little bit larger, but the problem with that is that effectively you're saying your sensor isn't very good, and so you don't want that either. So it's not as bad as the errors over here, but it's still not really that great. So you sort of have it on two ends. We'll talk a little bit about those as we go through. So the first one is a constant covariance. So if I kind of go back to these here, and I can either do an average covariance of all of these, or I can actually do a focus point and things like that. This one ends up being an average covariance. These are the three conditions, test conditions: sunny, night, and snowy. And I've put this sort of distribution over here on the right, so that errors in red at the top, and I've thresholded this at 5%. These are errors where the Z minus Z ground truth are big. And the errors on the bottom here is when basically R hat is too big. And this is a log plot, which is why these look a little bit bigger. But it was just easier to kind of see each of these points. And then the left to right is when we're driving. So we start on campus on the left here. We drive all the way downtown, then we drive out on the highway, and then we come back to campus. So ideally, what you have is that each of these are 5%. Okay, just to represent the tails associated with the error covariance. And so at the sunny conditions, it actually is pretty close, 6% and about 6% down in here. If I go, let me go all the way over here in the right condition, I have 17%, so a little bit higher of an error over in here, but 3.2% down in here. And then finally, the big one here is the nighttime conditions. And the thing that you want to see here is that I got 30% of really, really large errors. And so what's happened here is that it actually looks pretty good, but then it really gets large in this area. So you might ask, well, what's actually happening in here? Well, right in here, these big errors are due to actually driving on the highway. So if you take a look at this a little bit more closely, what's happening here, these are a couple pictures during the sunny conditions. And when you drive on this highway, it all looks the same. So it's very easy to make mistakes and things like that. This is sort of daytime. This is nighttime on the right-hand side here. Where it actually starts to kick in is there's a little sign, a couple signs as you get up to the top in terms of exit ramps and things like that. So there's very few key points, at least until you actually get to the sign. So that's a little bit about the constant covariance. So the solution number two that we took a look at was actually just using our data to evaluate a covariance. And so what we do is, this is our pipeline in terms of a key point matches, and then we develop the same plots here of error, the Euclidean error versus the number of key points. So we're trying to evaluate here whether the key point matches are a good metric for us to actually use. And then what we do is we'd overlay them on top of here, okay? And we would basically use that as our sensor model to find our covariance. And so there's various things we did, which I'll sort of skip over at this point. I mean, we binned up these in terms of the number of key points. And so we could actually then look at the Euclidean error as a function of a confidence level, 10%, 20%, those types of things. But then we can also sort of take all these points in here and find an error covariance associated with that. Okay. And the nice part about this is, again, this is errors. And so if you have some outliers up in here, they will still be factored into the error covariance as you're using it. All right, so this is we call this adaptive covariance, because what happens is at any single point in time, you're developing a new covariance, okay? And so this is the same plot that I showed before. So the first thing I want you to see is, let's take a look at the red errors on the top here. The good part about it is that all of these are actually under 5%, even the nighttime, okay? So it's actually done a pretty good job of actually mitigating what's happening in terms of these big errors, Z minus Z, ground truth. But if I look at the 5% one, you see this is now, it should be 5% if it's Gaussian. So, and in this case, it's, we took a look at these and not quite Gaussian. So especially if even in the sunny conditions. So there's 11% here on the left-hand side. There's 11% here in the sunny conditions. And so what that means really, and at least in my mind, is that the covariance R hat has been moved down a little bit, okay? Or it's made a little bit larger, which actually moves all these points down. But the big thing you want to see here is the nighttime conditions. If you remember back from the previous one, they were all up in here. They created big errors. So, but what's happening in the nighttime conditions when you drive on the highway is there's very few key points, and very few key points at nighttime basically mean I'm going to give you a really large covariance. And that's what's happening in here. And so basically it just completely wipes it out as you're going on in here. And a little bit happens in here, but it's not really as bad. So really the snowy conditions and the sunny conditions had basically the same effect. Maybe the covariance was a little bit larger than it should have been, but the nighttime really overcompensated for it is the way you want to think of it. Now, what I'll argue though is that at least you don't have these big errors happening up here in the red. And so this, so this covariance is hard in this. And so a little bit more of an analysis to kind of see what's happening here. On the right-hand side here, this is the error for each of these conditions, sort of color-coded. And then this is the average standard deviation of that covariance matrix. And so unfortunately, I didn't get this replotted, but I want to just point this out to you. And that is that the scale, and that is that the sunny conditions here, the maximum here is a standard deviation of 1.3. The maximum of snowy conditions is 1.8. The maximum of the nighttime conditions is 120. Okay, so basically what's happening in each of these areas here, this is the highway driving right here at the bottom. The standard deviation is 1.2. It's about 80 in this area, sometimes going all the way up to 100, but for the most part, it's about 80. And then it's about 1.8 down in here. So basically what's happening here is because there's very few key points, it's generating a very large covariance, and that really improves the filter consistency. Okay, so now we're going to take that and we actually tried to put it into a common filter-based localization. And this is kind of what we're looking at here. What we wanted to do is now we have these sensors, we have the prediction from the network, but now we have a likelihood model. We could do some type of measurement integrity. If you haven't studied this before, this is a chi-squared test that evaluates whether you have an outlier measurement or not. It assumes a certain distribution. So we did a little bit of studying on that. I'm not really going to get into that. That was sort of in one of our papers from ICRA 2023, which I'll sort of skip over for right now just due to time. But the thing that's coming out here now is I have my prediction. I now have my covariance. I do my measurement update, and then I do my prediction around here. So basically, this is my filter as I'm working. And for our prediction, now typically what you'd have is you'd have an IMU, right? If you have an IMU, again, if you've studied these things, IMU, if you have a good one, it's pretty easy to see outliers and things like that. We actually didn't use the IMU in this study, primarily because we wanted to understand the impact of the bad measurements. And so, and we felt like the IMU itself would sort of just allow us to throw everything away, and we didn't really want that. Okay, and then what we're comparing, again, is the baseline constant covariance with our approach, which is the adaptive covariance. And so there's a couple tables here coming at you. The first is this just gives you a little bit of some of the definitions. So in terms of, this is the average error average Euclidean error of the databases for testing. So in sunny conditions, the average error is under 1 meter. In snowy conditions, it's 1.4 meters. And in nighttime conditions, it's about 8 meters. So that's just, think of that as that's coming out of the visual localization. That's the average Euclidean error. Okay. And then what we're going to do is we're going to compare the baseline constant covariance with our approach. So the first thing to look at is, okay, what does the average error look like? And just in terms of, again, Euclidean distance. And in each case, of course, it's a little bit better. We were a little surprised here that the average filter error for the nighttime didn't drop as much as it did. This was dropping like, 25% and things like that. I mean, I guess this, dropped to less than half of what it was, but we thought it was going to go down a little bit more, just because it was we thought it had a little bit better covariance. And I basically our analysis of that is we rejected so many measurements when we were on that highway portion that basically we were just doing prediction without an IMU, which still created quite a few errors. And then we had a little bit of a drop here in terms of the snowy conditions. So the average error did reduce, so we were happy about that. By adapting the covariance to the scene itself. And then we used a covariance credibility. This was just if we assume that it is Gaussian, and again, that's a big assumption, it's one that we know is not quite correct, but we sort of wanted to use it as a comparison. We could look at the 1 sigma, 2 sigma, and 3 sigma thresholds, and those ideally would be 68, 95, and 99.7%. And so if you sort of look at these in the sunny conditions, it does a pretty good job of sort of aligning what those would be. That this is sort of a slightly different analysis than just looking at the tails. This is looking at sort of partly the tails, but partly the internal covariance and things like that, right? Even in the nighttime conditions, it does a pretty good job of that, maybe a little bit high in terms of what's happening in here. And then the snowy conditions are a little bit there. So the covariance credibility is certainly better, but not quite aligned. And we do believe that one of the aspects of this, we could do a better job of looking at this in terms of just maybe Gaussian mixture or something a little bit better to capture what the errors are going to be. This is a video, just to give you an idea. The center here is the baseline constant covariance. And then this is this is the query image, and then this is the closest image. I think this is the closest image for ours. And what you want to see here is the blue oval is the covariance associated with our estimator. And then the green ground truth, if that green ground truth is within this oval, that means we're doing a pretty good job. So, but you want to see what's happening on the right here is that this covariance is a lot bigger. This one is much smaller, which is basically because it's assuming that the visual localization is giving you a really good measurement. And so as we sort of come along in here very quickly on the left-hand side, this actually goes, the error goes outside of it. So the green is not outside of it. But once we actually get near one of these signs, then it sort of locks on that sign. It has something to really lock onto and does a pretty good job. Whereas, what's happening over here on the right-hand side is, for the most part, at every time step, it's actually doing a pretty nice job in terms of the consistency of the filter as we go through. We also did a little bit of studying of corrupted images. So in this case, we could actually just study them all on our own. And so we did different things like taking—
1 second. We lost your sound. Let me try again.
Okay.
Can you speak right now and test?
Yeah, can you hear me? So close. Can you hear me?
Can you try again?
Yeah, can you hear me?
Please do. Oh, you can try.
Can you hear me?
Yes, yes.
Okay, all right. I'm so close. Okay, so we just took a couple of these images, and these are the original images, and we added some blur, we added some noise, so we could actually study how well it works in these different kinds of conditions, and we put them in different kinds of areas in terms of just trying to detect when these images are problematic, A, and B, find a different covariance. And so this allowed us to actually do some formal hypothesis testing with the adaptive covariance. And so we could identify with very high degree of accuracy whether these were problematic or not. And so we did different levels of blur and different kinds of noises we went on. Okay, in summary, for this part, basically the deep learning visual localization uses key points and it creates non-Gaussian errors. Really, the sunny is the best, and it's pretty close to being Gaussian, but the nighttime conditions, because the number of key points are pretty low, still creates it creates non-Gaussian errors. And many times what it'll do is lock on to images that are in the sunny database that can create problems and things like that. We found the number of key points is an okay but not great metric to define the error covariance. We feel like there's different ways of doing it. We did a pretty good job of figuring out, it did a nice job of adapting the covariance to those number of key points with the database based on nighttime conditions, but you still have sometimes these scenes that have artificially large number of key points, like a brick or cobble roads and things like that. When we integrate it into a common filter network, it really mitigates the errors even more. And I think if we integrate it with an IMU system, each of these actually would be pretty good, but we kind of lose insight in terms of what's actually happening with the visual localization. Some of the work we're working on right now is using Gaussian mixture models rather than Gaussian models to actually do that. And then looking at the semantics of the scene to try to get a little bit more unique parts of the image and weight it based on the semantics, so we can actually do a little bit better job of using the key points. So really, the key points then would be weighted by the semantics. Okay, that's it. Thank you.
Okay, thank you very much for this nice presentation. I think we have time for a few questions.
Maybe a couple questions.
Yes. Are there some questions? I think you need to come up to the microphone.
I can start it from
Okay, yes.
Yeah, you go ahead.
Thanks for the nice talk. I have a question. I mean, when I look at the slide here, you see a lot of cars parked at the road. Those are kind of dynamic objects. And if you think about the localization problem, how do those dynamic objects influence this?
Yeah, that's a good question. If you only have one database, the number, if you have parked cars or something like that, it actually really impacts it. But if you have sort of multiple database runs, it does a little bit better of a job associated with that. Where we really found it was problematic is that if you're driving at night and you come up right behind a car, so it wasn't the dynamic part, it was how much of the image is it covering. And so when you drive up behind a car, let's say at a traffic light, and it's covering, 60% of the image, and the rest of the image, you have very few key points, that's where we actually had different kinds of problems and things like that. So we've looked at masking out basically the dynamic objects, which is pretty easy to do, and that certainly helps. That's part of the semantics of the scene. And so as long as you can sort of detect those, it does a pretty good job with that.
I have a
good question.
Also along those lines. So we worked on something similar, but more for the structured promotion case. And there we saw like points in the sky were a huge issue for us. So we got a lot of key points on clouds, for example. And those are really far away. So translation is super hard to estimate from there. Mostly garbage, but you get a lot of matches. What do you do with points in the sky?
Yeah, so that's a great question. I mean, I'll tell you what we're doing right now is we're trying to use semantics, and we're trying to not use the sky and not use the basics of the road.
That's nice and phrase.
Yes.
Yeah, market phrase.
Okay. So we lost connection.
Yeah, maybe we just move forward.
Yes, I think so. Maybe you can write him.
Yeah, I can write him. Yeah.
Yes. Are you ready? Okay, so I think we will continue with our next speaker. And while this setup, I will introduce our next speaker. Our next speaker will be Cornelia Perrella from the University of Maryland. She's at the Institute for Advanced Computer Studies. And well, she has been part of our research community for a long time. And her contributions were in the area of action recognition. But most lately, also she was working on event cameras, she was working on ego motion, she was odometry. And we will hear from her today about the area of this works. Of visual odometry and visual localization.
Hey there. Sorry about that. Thank you so much. Appreciate it.
Yeah, sorry for that. And we have to move forward and we're waiting.
Oh, this is chair. This is chair. Yeah. Okay.
How do you see that I'm not connected?
I see it here on the screen.
Well, oh, yeah, I can, but here it's not connected.
Okay, but let me try one more time. No?
Now it works. Yeah, it works. Great. Yeah.
Okay.
I think the speaker is ready, so please now.
Okay.
Oh, you are sharing wrong screen. You are sharing this screen right now. Think that.
Okay. Share this screen. And now and now I have to go back to sharing. Okay, sorry. Well, sure. Okay, good. Share. Okay, so in our group, we have been working a bit different, not visual odometry, but we call it direct approaches to visual odometry. So you all know the classic approach is we look at the scene from multiple views. Usually we find correspondences in the views from which we then triangulate all these constraints in order to get a 3D motion, the transformation, and from that then using this the correspondence plus this 3D, we can get the structure of the scene. And the classic dominant approach has been probabilistic, visual slump here, it's just shown by example. And well, this workshop is about, there are still issues of various kinds, especially when it comes to fast motion. It's also very expensive. And we still have difficulties with moving objects. These were the last questions. But it's obviously underlying all the technology that we know, being from drones to car to virtual augmented reality. And the motivation, it exists everywhere. Biological systems with very tiny neural systems also solve it. And that has been our motivation to not compute visual odometry and structure at all times, but solve less information necessary to solve the task and couple that directly with the control of the system. And over the last number of years, we have been developing such capabilities which start with the first one, you gotta know the visual odometry, your own motion, kinetic stabilization. Then you build up and segment independently moving objects. You need to have capabilities of avoiding obstacles, target pursuit. Then when you build up a memory, you can find your home or build shape maps for landing. And we have implemented this in various drones, partly homemade of the increasing sizes. And small size is especially attractive where it matters. You can't put many complications on. You need the vision. So to give you a motivational example here with the DVS camera, the event-based camera, a drone is here looking at other drones, and all it can really, if it has an event sensor, all it can really see then from this event sensor, it can see the propeller that on the classic video would be very blurred because it has such high resolution. And that is sufficient, for example, to detect the wings of another drone or to do in another application here, this landing as a direct approach. And next, we recently had a paper where we used the concept of uncertainty, just uncertainty, and demonstrated in various applications in the science robotics paper. So what is computed, under the hood lies a network that is trained on flow. It learns in a supervised way the values of the optic flow, and unsupervised the uncertainty vector, the variance, a two-dimensional vector. And with that, we can solve tasks like dodging or navigating, because the uncertainty, for example, of things that are closer by is higher. The uncertainty at the boundary of objects is higher, and other tasks were flying through unknown gaps or segmenting. And two of these are shown here, navigating through an indoor forest, where you see the uncertainty maps of the object here, what you saw on yellow, what is yellow color is high uncertainty. And that is then given directly to the controller of the drone that controls itself, plus the distance to the object. Or the second example, the dodging, where the object that is closer by has high uncertainty on its boundaries, and that was the only thing to segment it and avoid it. So now I'm going to talk a bit this idea of bio-inspired computing of the pipeline. And then it would show a little bit of our event-based motion segmentation work. And finally, a new paper where we have augmented event-based sensors. So the concepts that underlie this motion, structure for motion, we get first some kind of correspondence, or in a continuous case flow from which we computed 3D transformation, and having 3D transformation and correspondence, you can get geometry, and then you also have to solve for object segmentation, which actually have to be solved in some way, but here is a semantic segmentation. Sure. Well, I like to show this illusion. Who hasn't seen it yet? It's the Auchi illusion, and you may see it with eye blinking, or I can jiggle the paper for you, like moving with 45 degrees, and you probably see the insect moving with respect to that. But there's no more. Motivation. This is this motivation. There is some problem with flow estimation, estimating accurate flow. And the reason is going back to the aperture problem, when we look at edges in the first stage very locally, we can only compute how the edge moves, the perpendicular or normal flow. And then we apply, in the simplest case, we just say in the neighborhood, the flow is constant, or more sophisticated, we apply various regularization approaches in order to solve for the flow. But that stage is actually, it's an estimation problem. So geometrically shown, one edge gives us one constraint, and out of the two-dimensional correspondence of flow, we can only get the one-dimensional normal flow components. Two of those will then constrain it in the ideal case. But in reality, all we have noise. Those directions aren't perfect. And then that's why you apply some estimation process. And you try to find, with respect to some criterion on the burst, the best solution. So if that criterion is least squares, we can show it basically amounts to solving a linear equation system, AX is B. And it's very well known if there's not only noise in B, which means in the lengths of the normal flow vector, but also in the orientation, and even if it's uniform, symmetric distribution, anything symmetric, as long as it's symmetric, it's very well known in statistics, the solution is biased. We're getting the full solution plus an additional error term. And you can study that error term on the basis of the texture. And long ago, I also went through all estimators. The problem is it's very hard to correct for this bias because you would need something about the noise, and that you have to estimate again from the data, which again changes over time. So coming back to the Auchi illusion, what this means here, the pattern is set up in such a way that in the inset, the bricks are vertical, and you have thus for a 45-degree motion, many more vectors going to the right than up. So you have a better signal to noise ratio in that direction. And in the outside, it's the opposite. So usually when we estimate motion, we estimated the ego motion, our own motion, eye movement. You can see it just from the eye movement you cause it. The periphery gives you this ego motion, and then the inside has a relative motion to it. And that's what you see. So here's simulation. So then we set out, being this the motivation, developed many constraints. Let us not compute flow or correspondence, but start the process differently. Get ego motion from normal flow, from those well-refined measurements. And then when we have ego motion, we can go back and segment to other things. So here we trained, like you train an optic flow network and like cell flow or light flow, a normal flow network. And you see here in color the errors. So you see the normal flow network has much less error on a texture that is similar here than the Auchi illusion with bricks, for example, where the distribution isn't uniform, where it is kind of balanced. So the 3D motion equations, just to give you the motivation, we know the motion consists of the translation and the rotation, with the translation dependent on depths. And when you have correspondence of flow, we minimize just the deviation of this from the flow. So in this case, we derotate the flow, and then we say this has to be perpendicular to the translation component. In the simplest case with L2-1. So our approach now works as follows with normal flow. We train a normal flow network, and we want to use this normal flow network. And so if you have normal flow, you only have an inequality. So our approach goes like this. We start out with some kind of closeness just to get some initialization for an estimate. And then solve via this inequality, which is really So if you have the normal flow, you say the translation, the normal flow, which is just this 1D component is the translation plus the rotational normal flow. And you can just say subtract the rotation times the translation and normal flow. They have to be greater than 0. Because the scene has to be in front of you. The depth has to be positive. So that's the only constraint you have if you only want to use this normal flow value, basically just the sign of the normal flow value. So when we, long ago, I was trying to solve this normal flow constraint and implement it in algorithms with voting or with linear programming, but now we want to solve it with networks. And the idea is actually pretty simple. Instead of solving this inequality, we solve a function of this, and naturally this could be this, a function that we put over it. So it could be the value function, which kind of says that if the depth is positive, I don't punish, and if I estimate the depth to be negative, I punish it linearly with the value of negative depths. That's what it encodes. But in order to make it differentiable, we put the Galo function. So now we have a function, this whole function that can be differentiated and embedded in a network. And that's what our network does. Oh, something. So we solve in a forward way for this differentiable function, which can be done with many packages. And then there has been work already done. Now you have an optimization problem. Basically, you solve now a constraint optimization problem. As you feed it back, you just need to compute the one-layer network, the derivative of this function, in order to put it back. And then you go back to your original estimate. So you have estimated from the positivity constraint, the motion estimate. You use that implicitly to get depths, and then re-estimate the motion, and then feed it forward again to re-estimate via the positivity, and you let it run for a few cycles and basically train the network then. The trick is, how do you feed back these non-differentiable functions? And that is done by the so-called differentiable data. Differentiable program. So some optimization packages that allow you to feed any function back. Well, here's some results. So what does this do now? What is the expectation that you have embedded this constraint? Normal flow as opposed to optic flow, what is usually done in a data set, you expect better generalization. And yes, so we get these results. What we did, we trained on the air data set and tested it on riding data set. And it does show better generalization. Here shown via the classic loop closure, that is the best here for our algorithm. And it was compared also on works on deep learning networks and classic SLAM networks. And generally, so trained on pattern applied to Kitty, the networks, the learned networks are usually superior in translation, and the geometric methods estimate better than rotation. So our methods even gets definitely better in translation, but it also gets the rotation error here down. So here compares. Well, so what I said is, in summary, and then went into details in how we implemented it at the network, we can change. There is the idea, if you want to solve it directly, you can change the pipeline. Instead of estimating flow directly, go for normal flow, estimate equal motion, come back, refine flow, get then refine scene structure, and then also refine segmentation. And it seems these biological mechanisms, like those even described by Adelson, burdens, partial energy models, or even a Reichert detector. That's what they get. They get normal. The other thing with which has been really employed in our that I've employed now for about 10 years is this event sensor coming out of the neuromorphic community, but there's a chip, but there's electronics at each pixel that records asynchronously just the motion, just when there's change at the pixel, at very high temporal resolution, high dynamic range because it's coded logarithmically, low bandwidth, because you only record the changes. But of course, it also has a lot of noise that we have to deal with. So just seeing this, the motivation, you can see what's immediately clear to me. This sensor you see on the left, the regular camera, and on the right, the GPS camera, and an arrow goes through. It's very blurred on the left, but can still be seen on the right. It's good for segmentation. This camera, because of the high temporal resolution, because of showing the data at the boundaries only, it should be used for segmentation. And that's, we're getting closer to really compute the complete loop, going ego motion, going segmentation. But right now, I'll show you some earlier segmentation work. So this is what you see with this camera. As you run it over, you get this cloud of points coming out, only at the edges. That's your data. And the way it can be dealt with, one way, not the ultimate, that you take the data within a certain amount of time, we call it a slice of data. And in that slice of data, then what ego motion estimation means now, I warp the data. So if I take the last events, and each event has its own timestamp. So here, a simplified model, if I model the ego motion with just 4 parameters, then I know what the direction of each vector is, where it should move, and I know the timestamps. I can warp it back to time t0 of the time slice. And then the algorithm naturally means if I got the right warping, the right compensation, the right motion parameters, I sharpen the image. That's the idea. So, and that's what we applied. And we applied this to the data in different ways. We can use the timestamps just. So what you see here is a blurred data on the left, under A. And then under B, you see the timestamps coded as color. So what you would like to achieve then is warp it back, which means if you count just the events, you get a sharp image. Or if you here on the right bottom, number D, you see the timestamps. So what is not aligned when we compensate for the ego motion, that's then what's independently good. Yeah, and by using timestamps, you can do the optimization very fast. Because basically, the gradient is going in the direction of the flow. So you have it in those 3 steps. Well, so these were our first algorithms and we implemented them. And then we also included the same concept here in a neural network, but for complete motion segmentation. So what this does then, instead of images, it gets these time slices. And we compute from one thing here. This is very classic, actually. It's a depth network that computes depths. And then at the bottom, you compute multiple slices from times and space. And you try to unwarp them. That will give you the ego motion. So the standard networks are this concept. If I have estimated the correct depths and the correct 3D motion, I know what the displacement is. And that's on the basis of that, then I can formulate my cost function to train in a self-supervised way. But you can also, what we did here, we used also independently moving objects. And the way it was done, that each point was considered then a linear combination of multiple points. And that's how so each point can then get then gets its own ego motion, plus how much it belongs to a certain model. And for that, it was trained in a supervised way. So here are some results. Even we can train it unsupervised for ego motion. Advantages are this, but they come from the DBS, that you can train on daylight and transfer it to night scenes. It fixes the data sparsity, and it's a very lightweight architecture. And we can also segment in this way. So here the network also to show its complexity was set up something like a RaceNet architecture, which you can set similar to it at multiple levels, so you can get the segmentation higher accuracy on the left or less accuracy if you use less layers. And in order to make all this work, we have this data set, EBI and O, and then EBI and O2, where we can basically scan objects high resolution and put vital markers on it, calibrated the whole system. So there's a rig of DBS cameras and also some regular cameras, recording now the independently moving objects. And you have the exact ego motion and the exact 3D motion of every object now. And the code is also set up to give you the masks, the segmentation in fingernet frames, and you have the image motion coming. And that's available for anyone doing segmentation or flow work. Well, so somehow the same network here shown in the demonstration, EB.dot, where the camera was equipped with two such sensors. One at the bottom to get the ego motion and one forward looking, and we use the ego motion to segment and to dodge objects here in the scene that are flying towards it. So it runs that same network, but it's a little bit simplified since we're looking down, since it's a drone, the ego motion is modeled as a homography. You see here the objects are segmented. And if you can avoid, you can also pursue. Well, that's it. Yep, a drone, a funny drone. So what that is and work is going on, that data is coming, that's what the data is that's coming out. It's cloud in space-time. And it lends itself to study it. What does the geometry do? A C translation as you move along the C-axis, that's how it looks like, the point cloud with the color coded in time. And as you have in the video, you can basically, on this cloud in space-time, the normal to the local surface, that's always the normal flow. And we're doing now, have now finally the algorithms ready also to learn normal flow in much better ways, and the ego motion that we was shown in video going to events. And the next step is now to use this also for segmentation. And finally, one last work. So one thing of this event camera is it is like a stereo camera because it's a motion camera. So when you move it horizontally, you don't, like in stereo, you don't see the horizontal edges. In a similar way, what you move in parallel, like horizontal motion, you won't see horizontal edges. Or you will get a blur. So there are drawbacks to this camera. Texture fades as the motion decreases. If there's very slow motion, it fades away. And we wanted to say, so humans have the same problem. But what do humans do? We do these tiny movements, these tiny eye movements, the microsaccades, right? So we've taken from some internet saying, if you want to see your microsaccades, your tiny eye movements, stare at the dot for a while And after a little while, you won't see the blue ring anymore if you really fixate and suppress these microsaccades. So that's one function of these microsaccades that's well studied in psychology, to introduce additional motion to prevent the fading. Earlier days, I was trying to put motors on the event camera to simulate this. But recently, what we did, we built some mechanisms, some microsaccade inspired mechanism. Well, it doesn't matter. By putting a wedge in front of the lens, and that wedge keeps rotating. And as it keeps rotating, it creates at each point a little displacement. So each point moves along a circular structure, introducing some additional motion. Yeah, I don't have to. So as this camera moves, it introduces this additional motion. Now we can compute what that additional motion is about and compensate for it. And this way we have some microsaccade algorithm that improves now the data quality for spatial tasks the way we know in different representations. It improves the event screen representation, the accumulated event image, but also people are working with these events and reconstructing the image. It's low power, now can we get back? That's the companies are already working on putting it on the phones. This way you have a low power acquisition. So what you have then, where you have before on the left shown perceptual fading, now you have a nice stream because of these events and much higher density. And we demonstrated this in a recent paper, also in Science Robotics, this event sensor. I will show you for various tasks like feature tracking and motion segmentation. So what you see here is with this, this is a classic camera on the bottom left, and then a regular event camera at the bottom middle, and then our event camera. In a task like tracking, we're not losing the points, similar to a video camera. There's a classic event camera, because certain points get lost when you move parallelly, would lose it. And you can also use this now for motion segmentation. Here it shows you the number of points that are tracked with this new sensor on the right. It doesn't, because of this additional motion, it doesn't lose things. So going back to the way we think, if we use tracking as points or segmentation of points, we can solve these low-level tasks now better. We can also solve higher-level tasks better. People have, groups have been interested in tracking people, human detection. You have the same problem here. You lose the people in tracking with the classic DBS camera. Of course, so if you want to do high-speed tracking with a regular high-speed camera, that's of course very heavy. And here it shows the main author, Bodao. A regular camera will give you motion blur. A DBS will give you perception fading, but on the right, you don't have this fading anymore. And you also can now track the human skeleton tracking in various ways throughout, like at the quality of video, but at the high speed of a high-speed camera with this additional attachment. And of course, the next step, this is regarding spatial tasks. We can also study that. So thank you. We have a group at the PRG lab, and these motion students that have really contributed in various ways, and I keep contributing to it now. And some of them, like Nitin and Jahad, are professors. Chetan at the company, is at Amazon, Anton is at NVIDIA, Cheng is at Google, and the other three are still with us. So thank you very much.
Thank you very much. I think we have some time for questions. So could you please come up to the microphone?
Is the normal optical flow computed from the optical flow? How is the normal optical flow computed?
It's the other way around. Without computing optic flow, you compute normal flow. You can compute it either just from the gradients, just the gradients, just from the image. I mean, one way is to just compute the image gradients, and the ratio of temporal over spatial is the normal flow. When you compute flow, you take this and then you solve some estimation. You have a similar equation in energy space. You can use phase filters where you have the same equation. So it's before optic flow. It's much less. It's much easier, right? Geometrically, normal flow is the projection of the optic flow on the direction of perpendicular to the edge, on the gradient. But computationally, it's before optic flow. You just get it as output from the, if you use video, you just compute the derivatives back, and then temporal derivatives over spatial derivatives. Let's say in the 1D case, it's just minus IT over IX.
Yeah, it's a bit hard for me to follow.
Okay. Normal.
Was it invented before?
So invented.
Well, discovered.
Yes. Well, if you the very basic optic flow going back to Kundering and Van Dorn, we just assume the image intensity between two frames remains the same.
Yes.
Right. From which we say the total derivative is 0.
Also by adding the difference between the two frames, right?
Or you can compute the difference between two frames if you compute it free. If you think it, just the change is 0, right?
Yes.
Which means the total derivative is 0, which gives you an equation, one equation in the spatial derivatives. And that's the normal flow.
And that's the normal flow.
That's the normal flow. That's equation Ix u plus I by E plus IT is 0. That's the normal flow.
Wow, I thought that was
No, you have to have at least 2 such measurements to get the flow.
And instead with the normal flow, you just do one.
Yeah, one equation, yeah, because it's perpendicular to the gradient.
Okay.
Yeah, it's perpendicular to the edge.
All right.
So optic flow is 2 numbers, right? So you need
Yes.
at least 2 measurements.
Yes.
2 measurements in 2 different
But
directions.
instead normal flow is that you have a distance, right? Plus an angle, right? No, the normal flow.
No, I don't have an angle because I'm measuring the spatial derivative. The spatial derivative means perpendicular to the edge. The gradient. So you have it. Yeah, it's the image measurement itself. So you basically just say the length is perpendicular to the edge. So that's your measurement.
All right.
Well, I'll show you more later. Okay, I didn't. Well,
okay, so
obviously I have it on my slides, but yeah.
Okay, thank you.
Yeah.
Do you have some other question?
I have one question, not too mathematical. So it was interesting to see the bridge design for the event camera and like getting against like high and motion and all, but like what full stack like, localization, we still need the RGB or like.
No, you don't need. I mean,
for example, localizing myself, like is event camera.
I mean, localizing yourself means you have your ego motion, right?
Local motion, I understand, I guess
Yeah,
it's you,
yeah.
but like, for example, like I was in this room yesterday, I'm still in the same room, for those type of things, like, how we think like the motion is gonna be like.
I mean, if you want to compute from the motion, this whole structure of the scene. Yes, you can, right? And that's the very heavy computation, right? Which we can, people have done it too, yes, in some way compute these points, and with the wedge you can compute it a little better, and you can do the same thing. You have correspondence from which you go and lots of it. But yeah, you can do that too. The point being, I think the that's the point. The classic pipeline is all of this. First we reconstruct, compute the globe, the transformation, and to build the world model. And the point being, if you are a small system, you don't need to have a world model for everything. You just need to compute what you need to get the job done. If it is going through a hole, you would need the flow on the edges of the hole, and that should be sufficient for you. For B. Yeah.
Thank you.
Yeah.
There was another question in the back. With your wedge, rotating wedge, for dense seams, do you run into certain approach on bandwidth limitation?
Well, I mean, with the DBS, it does get a lot of data. Right. Yes, you do. If there's a lot of texture, you move it. If there's very fast motion, yes, currently. But all these, so the wedge doesn't run too fast, right? But all these things are under development. Maybe the DBS sensor, new technology. But yes, right now, very fast motion.
Actually, two questions. First of all, does the wedge so how large is this?
No, it's up to 3 pixels. I mean, this additional displacement that whatever it would go on. It's like on a line, now it goes on. So it's a circle of 3 pixels, and that's exactly what we take advantage of. We compensate for it and then.
Can this pixels be displacement be estimated, or I guess you have to know the
Yes, we don't estimate. I mean, we estimate them. We approximate them. We approximate it like a circle everywhere.
If you have like the pixel, I'd like if you want to have pixel accurate. Actually, I mean, if you're sending the feature tracks back in,
yes,
the pixel accurate.
So it is accurate enough what we do right now by modeling the curve, the circle. You could do more, but then you really need to calculate the count of pixels. Yeah. But it's good enough for all these things. It was good enough.
Second question is about the speed of the. So I guess you go faster than generate more data, but at the same time you'll be able to capture higher speed. So if you're going too fast, probably the prism is not moving fast enough, but still behaves like a quasi-static prism, right? Or did you ever?
They did at about 20 per second. Yeah.
So if you run now very, very high speed and nothing that the prism is like quasi-static in the sense where you still don't see certain edges.
No, I think you get the edges, but then you get, but right now in the mechanical problems also, right? But there's things around, I mean, people solve it also. There's optical solutions, how you can get actually some additional motion in optical ways with crystals, and so we haven't done that yet. Optics research, that very
I think we should stop the discussion now to continue the program.
Yeah.
Thank you again.
Okay, thank you.
Maybe we just have a couple minutes for getting a break, getting a coffee, and we will get the next session after 3 minutes.
Okay.
Hi.
I will stay here.
Okay.
But you don't see me.
Well, you're always welcome to be here. Yeah,
But you can continue with the introduction now.
If you want,
No,
you
no,
can
please,
go ahead.
please continue.
Okay, okay.
I
I
will
work
be
on
here
it.
anyway because you need to monitor this fix. This is
Okay.
really complicated. for the setup. So yeah, I think you now need to get your speaker back, right?
Yeah. He's here. Everything should be fine. We just need to wait a couple minutes and getting break.
I just want to talk to him.
Sure.
Hello. The one who's organizing that.
Let's see. I don't know if can you hear me?
I can hear you very well, actually.
Okay. And then in terms of, I have no idea. Do you just see the slides now, or do you also see me?
I also see you, actually.
Oh, okay. But you don't see the slides.
I see the slides as well as you.
Oh, okay.
You are above the slides. You are above the slides.
Oh, okay.
Yeah, everything should be fine right now.
Okay, good. I have no idea what you actually see there or not, what you hear there or not. I get a sense of what the Zoom experience is like.
Yeah. Currently, it seems like very well, actually. Let's just wait another minute, actually.
Okay.
So people can come back and after grab coffee.
Okay. Yeah.
Well, let's get started. Let me introduce the next speaker. Dr. Michael Gleicher is a professor in the Department of Computer Science at the University of Wisconsin Medicine, and Professor Gleicher is the founder of department's Visual Computing Group and co-directs those Visual Computing Lab, as well as the Collaborative Robotics Lab, and his research spans different areas: visual computing, data visualization, robotics, and virtual extended reality. His recent work he includes exploring perceptual issues in visualization, visual simulation for robotics, and geometric approaches to enhance robotic perception and interaction. And he has been paper chairs for Euro visualization and area chair for attribute visualization. Prior to joining the university, Professor Gleicher was a researcher at the Autodesk Vision Technology Center and as well as the Apple's Computer Advanced Technology Group. He earned his PhD in computer science from Carnegie Mellon and bachelor degree from Duke University. He was a visiting researcher in INRAE of France. Professor Gleicher is an ACM distinguished scientist
He holds a concurrent appointment as a design scholar of Amazon Robotics. His talk will be on the topic of miniature time of flight sensors for robot perception. Dr. Gleicher, you can take over to introduce your research. Thank you very much.
Hey, so thank you very much. I'm sorry that I couldn't be there, but I'm here in Madison and hopefully can sort of tell you a little bit about our work about using these miniature time of flight sensors for robot perception. So a little bit about me. I historically worked in the area of computer graphics, and then over time started working more in data visualization and robotics. This work that I'm going to describe is more part of my robotics work. I sort of consider myself more of a robotics researcher rather than a computer vision or perception researcher. But of course, perception is a big part of robotics. So now, I want to start, because at the end there's never enough time, I want to acknowledge that all of this great stuff that I'm going to talk about is really, I want to sort of give credit to the main people involved. For this work, the main student is Carter Sifferman, and my collaborator on the work that I'm going to talk about is Mohit Gupta. They are both there in Seattle with you at CVPR this week. So if you have any questions about the work I'm going to talk about, go seek them out. So just to give you an idea of what I'm going to be talking about, this is quite different than the last few talks that I watched, in that I'm going to focus on these very small miniature time of flight sensors. So whereas Jason Corso's talked about getting depth with only traditional RGB, I'm going to not have anything. I'm just only going to have depth. Where the last talk showed some very sort of larger sensors, I'm looking at very, very small sensors. And what I want you to take away from this talk is that you can actually do lots of cool stuff with these sensors, but you have to have a few tricks up your sleeves, like modeling them carefully, using their internal data, not just the data that they give you in the naive ways of using them, and trying to bring multiple observations together to figure out what they all mean. So to give you a sense of where this is going, I'm going to start a little bit of motivating why I care so much about these sensors. Then I'm going to tell you about how these sensors work, because they don't necessarily do what most people think they do. And by the way, with each of the pieces of the talk, I'm going to connect it with a paper that shows a robotics application. So we'll start by talking about how the sensors work. We'll look at an application. Then I'll talk about the different ways we can actually make use of what goes on inside the sensor, again, with an application. I'll talk about using better models of these sensors to improve what we can do with them. That's actually, I have a laser pointer. Again, with an application. And then finally, I'll talk about the inherent and fundamental ambiguities in using these sensors. And again, an application. So try to interleave the ideas and the applications of what we're going to do with it. All right, so all of this work, those 4 pieces are basically 4 different papers. And the student who really led this work is Carter Sifferman. And again, he isn't at the workshop because he is presenting at another workshop actually now. But he is there. So if you're interested in this, please seek him out. He'd love to talk to you and answer questions about it. Okay, so let's begin. A lot of robotics, we put big sensors. We have our big fancy LiDARs and things like that. We put them on top of the robot. And that has a problem that if you want to cover the whole world and see everything, well, that's expensive, in part because you don't necessarily know where you need to look. So you have to look everywhere. You get lots of coverage where you don't need it. And worse, if you have your big fancy sensor, say, on up in the sky, and you're trying to, or in the ceiling, and you're trying to watch what a robot arm is doing, not only are you spending a lot of time looking in places that you don't really care about, but you also have this problem that the robot arm and other stuff is likely to block what you're looking at. And the sensors, because they're up in the sky, up in the air, they're not right there in the problem, showing you what you really need to know right in the moment to do the sort of small term short decisions. So what could we do instead? Well, our idea is to distribute the sensors over the robot and potentially in the environment as well. The idea is to put lots of sensors all over the place where you think they're going to be useful. This makes sensing both distributed, it's all over the place, but also strategic. We put sensors where we think we need them and where we think they're going to be most useful. And this, I think, is sort of the core of the vision, is I want to be strategic with how we do sensing. I only want to do sensing when and where I need it. Now, to do this, I'm going to put lots of sensors out there. If I'm going to put lots of sensors out there, then they need to be small because they have to fit, covering the robot. They need to be cheap because I need to buy lots of them. They need to be very low power because I don't want to have lots of power going to the robot. I need to be able to do things with small amounts of computation, and they need to be able to communicate very efficiently. If I had to send an image from 20 sensors, then that would hog up all the bandwidth I have in my network. So I want sensors that have all of these properties. So if we look in what we can actually buy today, well, first I say we're not the only ones who are trying to do this. There are a bunch of people out there. On the left is some work from the group at Colorado, where they've been doing something very similar with the same kinds of sensors that we're doing, of putting sensors on robot arms. And then well, lots of people use these little crazy flies, and you can actually buy the same sensors that I'm talking about today. Crazy Fly will sell them to you, so you can put them on the robot. Right. So this idea of distributed sensing with these small little sensors, I should say a little bit about these ones that you can buy. So they are time of flight sensors. So they measure how long a photon takes to hit something and get back. So they measure distance. And there's an acronym there, SPAD. I'll explain that in a moment, but it's single photon avalanche diode. But the fancy term, these things are really small. You can see the one that we buy. It's mainly circuit board. And these things are everywhere. They're in your phone, like most phones have them to detect whether your ear is close to it. The thing that they sometimes call solid state lidars, like in an iPhone, are the same technology. These things are all over the place, and you can buy them. Here's a few of the ones that we've bought. They have this great thing that they're really cheap. If we buy them quantity one, it costs $3 to $10. So if you're going to buy a lot of them, you can probably get them a lot cheaper. They use very little power, and they have a pretty reasonable range. They don't work very, very far because they do send out light pulses and wait for stuff to come back. But at the opposite extreme, they work very, very close up. They're good, a couple centimeters away. They're still good. So they're cheap, they're light, they're small, all those things we want. And if you go to pick your favorite online retailer, you can buy them. They're easy to get your hands on. SparkFun and all those will sell them to you on nice boards that are really easy to interface with. Everything seems great. All right, so you can buy these things. What are they trying to sell you? Well, you would think, all right, it's a laser. It sends out a beam and it gives you a number back. So it gives you a single measurement in that direction of the line of sight. And if you look at what they tell you in the marketing literature, they kind of advertise this. It's a laser, you get a beam out there, it tells you how far stuff is away. Now, in practice, that isn't what's really going on, because in practice, these things have fairly wide field of views. And what it does is it uses some internal algorithm to give you some kind of averaging over the entire field of view. And for this reason, they're often seen to be noisy and unreliable because you don't know exactly what's going on. And if you have lots of stuff out there in the environment, you get some of the close objects and some of the far objects. So if you don't, well, without the stuff I'm going to talk about next, the people, they've kind of gotten a bad rap. So let's drill into this a little bit. Actually, before we do that, well, all right, so these things, all right, so you're not getting what you're paying for, but is that model of pretending that it's just sending out a single narrow stripe and getting a single point measurement. If you think of it that way, can you actually do anything with it? Well, it turns out the answer is yes. We had this is an RAL paper from a couple years ago where we took on the problem of, I want to understand where on the robot the sensor is. So if I want to be able to localize it very precisely, so the calibration of how I place it on the robot, all I want to know, I don't know where it is on the robot. I do know how the robot is moving. And for now, just all I am going to assume is I'm looking at a plane. So if I know I'm looking at a plane and I know the robot motion, the equations all turn out to be simple. So we can use many, many observations as we move the robot around and put them all together and get very, very precise localization of where the sensor is on the robot. Kind of works out pretty cool. And this is all based on just using that direct measurement of pretending the sensor really is shooting out a beam. And part of this is because multiple observations, we're able to average out over the errors that you get from having the wider field of view. Now, that's kind of like a special case. In general, I want to be able to view the wider field of view, not as a problem, but as an advantage, because often with robotics, I really do care about everything in the scene. So I do want to know everything that's out there. Now, another caveat here is when you get everything in the field of view, the sensors that you can buy are actually able to chop the field of view up into smaller, quote unquote, pixels. The sensor that I'm going to just mainly talk about can do 3x3 grids. Some of the newer ones can do 8x8 and probably more. But the point is, even if you get more than one measurement, it's more than one field of view, each one of these fields of view is a pretty sizable cone, and it's still relatively low resolution. And internally, it's averaging everything in that zone. So for the talk, I'm generally going to be talking about a single zone, but you can think about it as either, well, first I could treat the whole big thing as one big zone, or I could treat each of the zones independently. Okay, so this is what they're selling you. Let's crack the thing open and see what's actually happened. So the way these things work is they send out a laser pulse. So a laser pulse, even though it's very short, is a lot of photons. So they send out these pulses, a lot of photons. Those photons bounce off of things. Some of them come back to the sensors. And of the ones that come back, they get sampled, and individual photons, based on their timing, get timestamped so we know how far they are.
Michael. Let me reconnect. Can you try?
Yeah.
1 second.
Okay. Yeah,
now we can hear you. We can hear you. Can you repeat the last 1 minute?
All right. So where did I lose you? Did you get? All right. So just a quick version.
I remember you. The last several sentences is something like you shoot one single ray, you still get quite a lot of photons.
All right. So we were talking about here where we had with a single ray, we're able to do something, but what I'd like to be able to do is take advantage of the fact that I get a wide field of view, because when we cover a large area, we get information of the whole area. So this is sort of, I want to be able to make this as an advantage. Now, one of the things that the vendors have done is they divide the entire field of view up into zones, kind of like pixels. And they give you a measurement per zone, but each zone is still a finite region. So each one still is going to cover a whole bunch of area, and get a single measurement isn't going to capture everything that's in there. It's kind of still averaging, and they still are generally pretty low resolution. The sensors I'm going to talk about are 3x3. You can buy some now that are 8x8 and maybe a bit more, but overall, all right, they're pretty small, and each pixel itself is still pretty wide angle, covers a pretty substantial field of view, and I want to try and actually use that as an advantage rather than as a problem. In order to do that, we have to look at how these things actually work. So a little bit of the theory of operation of a SPAD. a SPAD sends out a laser pulse. So that you see here, right? A pulse of photons. It's a lot of photons because it's a laser pulse. It sends out a lot of things. They bounce off of stuff and come back. Now, a lot of photons are going to come back. You can't count all of them, but what it will do is it will sample all the ones that have come back and timestamp them. So let's see. Let's just look at one photon, right? So I send a photon out. It bounces back. And that's one that just happened to get sampled. I know how long it took. So I put it in a bin. I count that there's a photon that came back from that far away. Now I send another one, right? Well, actually within a pulse, I probably count a lot of these. I get another one back. I count, all right, this is how far this one came back. And it can do lots of these for each pulse. And it can do lots of pulses per second. So very quickly, you get lots of photons. And within a bin, right? Each bin is a distance, so you get a count of of how many photons came back from that distance. Now, this is where it depends on how well it depends on lots of things, how many come back. But ultimately, what I end up with is for every distance, all right, as I go out, or corresponding to a time, I get a count of relatively how many photons came back. Time is distance. I get a number of photons, a photon count per how far things are. Now we call these things transient histograms because they're a statistical measure, a histogram of the different timing that things took as they traveled over the as they travel back. Okay, so it's a little bit more complicated than that because the pulses aren't cleanly and exactly just like all at once. There's this idea of the pulse, the laser pulse has a shape, so you have to understand how when the pulse comes back. But more or less, it's the idea of I send a pulse out, I count the photons that come back at different times, I get a histogram. And this is exactly what these sensors do. The sensor that I'm going to talk about for most of the experiments, it will do each one of these for a different zone. So it'll actually give you 9 little histograms of what comes back from each one of those little non-overlapping field of views. All right, now, if you use the sensor out of the box, what happens is internally on the sensor, it takes that whole histogram that summarizes that whole broad field of view and tries to use some internal algorithm to guess what the single best measurement is. This is the sort of the per pixel or per sensor when I talk about depth estimate. And that's the main way that these things have been used. We're going to say, well, what will happen if we directly use the histograms themselves? So I view this as the opportunity of, rather than say for this 3x3 pixel sensor, rather than just getting 3 numbers back, I get 3 histograms, potentially dozens of numbers back, and I can use that to get richer data to do better things to solve my robotics problems. So we get more information. That's good. We get a whole histogram, not just a number. And we understand what these numbers are. They aren't coming from some proprietary algorithm that's munging stuff together. And we can use them all however we want. However, there's a problem, or a bunch of problems. One is a new kind of information that it's sort of the statistical summary of what's going on within that field of view. There are some ambiguities, and this means we need to have new approaches for how we're going to apply these in robotics. And that's what I'd like to talk to you about. So the problem fundamentally is when you get a count of things back, the amount of photons that you count back, that you get to count, depends on a bunch of different things. It depends on the amount of stuff that it hits, how reflective that stuff is. If it absorbs all the photons, you don't get any back. There are systematic problems in how these sensors work, right? That's that sort of complicated model that I sort of waved my hands over. And then also, like any sensor, there's a potential for noise. Now, those first two things, the amount of stuff and how shiny that stuff is, both actually are a fundamental ambiguity. And I'll come back to that at the end because this is kind of the most interesting one. But let me deal with those other two problems first because they're kind of easy to talk about. First, let me talk about noise. We did a demo. This demo will make a little bit more sense in a bit of why this particular demo, but we took a picture. We took a piece of white cardboard. We took a piece. It's thin. It's about 1 millimeter thick. We put a piece of that down. So it's a millimeter thick on matching itself. Now it's the same chipboard, so you can't, with a camera, you couldn't even see it. It's so thin. But if we look at the data we get back, we can reliably see that, well, here where you expect to see more or less stuff, you get to see, you can see, right? So you can sort of tell that there is something there. Reliably, even though that thing is really, really small, really, really thin, and photometrically is nearly identical to the background. There's a bunch of catches here, but the takeaway here is the signal to noise ratio on these things is much better than we expected. So let's not worry about the signal to noise ratio for the moment, because in practice, the other issues are bigger. All right, let's talk about modeling the sensor. So to talk about this, right, this is what's going to let us really make use of all that data, is understanding how to interpret how that data actually turns into the numbers the measurements that we get. So for this, this is a paper that was an RAL paper presented at ICRA last month. What we did is we took a very simple problem and then tried a bunch of different approaches to figuring out what we can do using these sensors for that problem. So the problem is really simple. I have the sensor. I know where either I know where the sensor is, and I want to figure out, well, what is the relationship between the sensor and the plane? All I want to do is capture the degrees of freedom of a plane. Now, this is actually useful in robotics. So like if you're trying to land a drone, you want to know where the flat surface is. If you're placing something using a pick and place algorithm with a robot arm, you want to know, like, where is the surface? Is it oriented the way that I think it is? I want to do this with a single measurement from one of these little SPADs. Now, to evaluate this, we tried this with a whole bunch of different surfaces. So 8 different surfaces, and we tried a whole pile of different orientations and distances. So we have this evaluation test suite. And I make this point because with this evaluation, I'm going to show you a bunch of different things we could try. I'm going to show you 4 different ways to use the sensor. First, using the measurements that they sell you. Second, using simple approaches that just sort of do the obvious things with the histograms. Using some data and heuristics methods that rely on our knowledge of the task. And then finally, say what will happen if we try to use a really good model and a render and compare, which is sort of a thing right now in computer vision. So the naive method, I get, we have the sensor gives me those 3x3 distance measurements back. I can use those exact measurements. I have 3 points. I project them back out into the world. I pretend that they're laser beams. I know where they would have come from. I fit a plane to it. All right, so that's method 1. Preview, it's terrible. Method 2 is, given that we have the histogram, you could do the sort of simple things with it. You could say, all right, the first bin that I get something to bounce back from. Well, you kind of know that that's wrong because you really want kind of the middle. You could do some simple bin finding, simple peak finding, looking at the whole distribution and where's the most of it. You can do some interpolation to get things better than a per bin accuracy of things. But I'm not going to talk about those because none of them work very well compared to the idea of remembering we know that this is a plane. Therefore, we know that a histogram of the plane will have a shape. the shape, the details matter based on the geometry and the reflectance, but overall there's going to be, we expect to see a single peak about as far away as the plane is. So since we know there's going to be a single peak, we can look for that peak shape and figure out with high accuracy, sub-bin histogram accuracy by doing interpolation, where the peak is. Now, this requires us to sort of have that assumption that we know there's going to be one peak, so that peak finding works. But we know we're sort of making the assumption we're looking at a plane. And also, there is a data-driven element of this where we look at we use some known data to tune the parameters, like how sensitive different regions are, because it turns out like the sensors are not completely uniform. And then once we have that, we use spline fitting to localize the peaks accurately. Well, this works really well. Even if you don't do the parameter tweaking with data part, it is still far better than what we get using the internal distances from the sensors. So this is really promising because it means, hey, look, we were actually able to do something using those histograms. But it was a little bit of a hack. So let's talk about doing something a little bit more principled. Now, a bit of a motivation for this is there is more information there. We were only looking at the peak, and we weren't using the shape of the distribution at all. If we looked at the shape of the distribution, that gives us more information about both the geometry, but also potentially about the surface reflectance. So if we could do that, if we had a better method, maybe we could make use of these things. The way we're going to do this is through using a differentiable render and compare approach. Now, this is kind of a standard practice in computer vision nowadays, where we build a model that says, given what we know what the world is, I know the geometry and reflectance, or at least I have an estimate of them. If I knew the geometry, the reflectance, the sensor characteristics, and the information about the laser impulse, I could predict what the sensor would see. This is like drawing the picture, right? You have a model of the world. You get the picture back. So you get the picture back. Well, this renderer, we write this in a differentiable way so that we can feed this into an optimization loop where we now know, all right, I think I know what things are. I see what I actually get. I then adjust, go through an optimization process where I tweak the parameters until the histogram that I generate matches the one that I actually see. So this is a standard, computer vision render and compare loop. We have to simulate the process of the sensor. We figure out what we think the histogram would look like. We compare it with what we actually what we captured. We make adjustments using the gradients, and then we sort of iterate until we converge. So if we do this, the key to this, of course, is we need a good model of the sensor. We build this model by first understanding how it works. I told you sort of how it worked. We sort of didn't get into the details. We use known data to fit and tune the parameters of like the intrinsic parameters of the sensors. And then the things that we don't know, like the surface reflectance and the geometry, we leave those as the variables we optimize. So we're actually going to optimize for both the surface reflectance and the geometry. Now, our sensor model, it uses a very basic computer graphics reflection model. We have models of how the sensor works that get some of the nonlinearities of measurement. We have the histogram formation process, how it sends out lots of things and measures them. The laser impulse, how it's not uniform over the pixel. There's some timing things. We model crosstalk. So there's a lot of things in the model. Once we have this model, we get something that actually, you can sort of read the fine print. It is even better than our hack that relied on of understanding that the thing is a plane. Now, you might say, well, this is a lot of work for a very small amount of benefit. The benefit are first that it's a little bit more of a principled approach, but also that because we're not just solving for the geometry, we're also getting parameters of the surface, so we can actually say things about the surface and recover the albedo of the surface, which is kind of cool. So that's what we can do with modeling. Now, what happens if the model gets even better? Well, that was a year ago. A year later, we take more. We have a slightly better model of how the sensor works. And we'll use more observations. That was just using one observation, I can recover a plane. What would happen if I wanted to recover some arbitrary geometry? Well, the trick here is first we need many observations, and then we need a better underlying model of the geometry than a plane, right? Has more than 3 parameters. For this, we use a neural occupancy field. It's kind of like a neural radiance field, except it's a volumetric representation. With this, it's kind of the same thing. It's rendering compare, where we simulate what all of the different SPADs should see from all of the different viewpoints. We look at what we actually saw. We optimize both the scene parameters and the reflectance parameters, and iterate until it converges. And all right, to do this, right, we use a robot, which allows us to very carefully put the sensor so we know the geometry, so we can then we know where the camera was coming from, and the only parameters there are the underlying volumetric representation, that neural occupancy field. What would you do if you didn't have this method? Well, one thing you might say is I could just treat this thing as the laser beam model. It hits something in a straight line, and you could back project the geometry. These results are terrible. The other thing you might do is say, all right, I know that there's an empty gap before the first bounce, and I could do space carving, the standard computer vision technique. It turns out this works terribly. Part of the reason it works terribly, full disclosure, is it's really difficult to set the threshold right. So it could be you could get better space carving results with some dynamic thresholds, but it would be tricky, and it probably still wouldn't be as good as what I'm going to show you. Okay, so the short thing is it works, right? We get things where we're actually recovering some things that really kind of get the real essence of the geometry using not that many observations, and these are just a single histogram. We're not using the 3x3, so a single pixel, but a histogram per pixel. We're able to get these kinds of reconstructions where space carving reprojection isn't going to get much at all. Here's some more examples. Well, actually, so same thing, just to give you a sense of how many different poses we're using. So these are roughly 200, 240 observations. We're able to reconstruct the geometry. And not necessarily simple objects. Okay, so the magic here again is that we're able to understand the observations well because we have a good model of how the sensor works. Okay, so now on to unfortunately I didn't leave myself to talk about sort of the most interesting problem with the sensor, which is this fundamental ambiguity that we don't necessarily know where the photons came from. When we count a bunch of photons that come back, we don't know if it's from things that are spread out or a concentrated place that just happens to be shiny. They could all, right? So let me explain this a little bit. So I know, say this histogram bin here, that comes from bouncing of stuff in this spatial slice here. But, right, I don't know where they came from. All I know is that they came from this slice. So where could it be? It could be that they're spread out. It could be they're close together. Or it could be that there's just a small object and it's just really shiny, so all the photons that hit it bounced back. So a way to think about this is that the reflectance matters. That because I have roughly uniform illumination, a big object that is dark, a shiny object, a small object that is very reflective, I'm going to get the same amount of stuff bouncing back. So why does this matter? Now, this is that picture I showed you before. Remember, I said it was going to come back, right? Here, right, because this object is different, right, is similar, because I sort of know the background really, really well, I can look very, very closely. Notice the numbers here, right? We're talking very, very small amounts. If instead I had a different background, this is a piece of tile of our floor tiles rather than the cardboard. The difference between cardboard and the floor tile is much bigger than the difference between object on the cardboard. So if we want to try and detect these small objects, we're going to have to do something different. We can't just rely on the sort of the seeing differences. So the application that we looked at is to try to use one of these sensors to detect small objects on flat surfaces. Now remember, if you get a single measurement back, all it's going to tell you is there is some floor out there. We want to be able to see, is there something on the floor? Now, we aren't able to say necessarily what the object is, or even that is it something that's on the floor or a lack of floor. So for example, if there's a cliff, right, here's the robot gets to the edge, or a hole, that looks just the same or has the same kind of it isn't the floor than if there's an obstacle like here, this marker out here. And notice that the application is obvious of taking a mobile robot, putting a few of these sensors on it, looking down at the floor. Now, the place where this comes in is we have this ambiguity problem. A light patch of floor and an object on the floor could look the same, right? Here, we could probably get a little bit of extra stuff in this zone. Well, here we'll get a little extra stuff in this zone because it's bright. We'll get a little less stuff out here because this thing in here is blocking it. Out here, it could just be dark out there. So that ambiguity really messes things up. Now, we're used to ambiguities in vision. So here are some perspective ambiguities. All right, so because of other cues, you probably realize that this is chalk art. It's not really 3D structure. Expose that it's chalk art. So what are we going to do? Well, the idea is we'll have to model the background carefully. In the paper, we do this with Gaussian mixture models. We use this to build up a library of different surfaces. We assume, and we can either assume that something is from that library, or we can assume the robot starts out on clean floor and drives around to build up a patch and build its specific models. And basically what we're doing is saying out of distribution implies deviation from the model. It basically works. The sort of details in the paper. I'm running out of time, so I won't give you too many more details of it. But we have actually built it. We actually are driving robots around with this, and the parts are small enough and cheap enough that we can cover the robot with it. So to summarize, these sensors are small and cheap and easy to use, low power and all that. They're great. And we can get a lot out of them by just really looking at the data carefully. We have to make use of those internal representations they have, those transient histograms. This requires us to do sensor modeling to correctly interpret the measurements, as well as to make algorithmic choices to perform tasks given the ambiguities. So what's next? I've only shown you using these simple, sort of in simple ways. We have to think about more applications, more tasks, using motion to disambiguate, putting multiple sensors together, using multimodal things. But overall, I think the vision is how can we be strategic with our sensing such that we can put sensors everywhere and just use the sensors that we need to do what we want to try and get at it. So I've skipped the bigger picture because I think I've gone a little bit over time, but I want to thank you all for your time and attention. And again, to thank my sponsors, and to again say that Carter is there at the conference. So if you have questions about any of this, seek him out. He'd love to talk to you. So again, thank you very much.
Okay, thank you very much for your talk. And any questions? We might have time for 1 or 2 questions. Yes, I see one.
Great talk, Michael. I'm just wondering how you model the crosstalk in your sensor model.
Okay, so the crosstalk. a lot of the crosstalk was done, modeling was done empirically, where we took some known scenes and saw, right, if something is in one zone, it spills, how much does it spill off into the next zone? So so the idea is it's a 9 zone sensor. Or I should say, there's two kinds of crosstalk. There's crosstalk between histogram bins. So a photon ends up in the wrong bin. It turns out that's the signal that's kind of like signal to noise. It doesn't happen that much. It's kind of related to the ambient light rejection. The bigger problem is that photons end up in space when you have the multiple zone sensors. Photons end up in the wrong bin. Now, one way, wrong zone, so basically the wrong pixel. One thing you can do is just say, I'm going to ignore the pixels and treat the thing as one big sensor. But if you don't do that, we sort of empirically modeled that, there's some spill that if you get a lot of things in one zone, it probably, some of those came from the neighboring zones, and do a little bit of sort of almost like deblurring, to say if there's a large amount here, just sort of spread it out. It's a very simple crosstalk thing, and it's a place where doing a little bit of it helped a little bit. Doing fancier things, at least the things that we tried, didn't necessarily help anymore.
Yeah, thank you so much.
Any other questions? Maybe a short question. Yes. Well, it's in the right time. Seems like I couldn't hear Michael. I couldn't hear from you, Michael.
Oh wait, what?
Oh, now I can hear you. I can hear you.
Okay.
What?
I didn't hear a question.
I mean, somehow. Can you hear me?
Yes.
Okay. Actually, my question is just, you have quite a few photons, and I believe the reflection based on material, based on color, based on the shape, and I'm wondering whether the robustness of the you knew this kind of sensor is reliable, or there are some robustness issues.
Okay, so I mean that's a great question. So the sensor is basically averaging over the region. So if you have a dark surface or a light surface, it will sort of get different amounts back. You will still get some bounce back from that distance. So the distance measurement, the fact that you get some, that there is something out there at that distance, that is very reliable. The thing which is quote unquote unreliable is you can't distinguish the amount to say, is it that it's a dark thing or is it a small thing? And that, sort of the amount versus albedo trade-off, that ambiguity is kind of the source of the lack of robustness of the algorithms. And I think that going forward, that dealing with that ambiguity in various ways is going to be the fundamental challenge of really using these sensors. Can you use another an RGB sensor that would let us understand what the color is? That doesn't quite work because the RGB, it would have to be an infrared sensor because these things work in infrared. But some way of getting, can we measure the reflectance? Could we use two of these together to disambiguate? There are all sorts of things we possibly could do to try and get rid of that ambiguity and to build robust systems around these sensors, despite the fact that they have these fundamental ambiguities.
Okay. Thank you very much, Michael.
All right. Thank you.
Yeah. Then let's talk about then let's line up with the next speaker. You are using your online laptop, right? Yeah. We will not connect this one because otherwise people cannot hear.
I need to connect this?
No, you don't connect this one. Just connect this. Let me introduce Dr. Amit Roy Chowdhury. Is my pronunciation? Chowdhury. Okay. Amit received his PhD from University of Maryland, College Park in 2002, and joined University of Riverside in 2004, where he is currently a professor and a endowed professor as well, and which is named Bonus Family Faculty Fellow of Electrical and Computer Engineering. And he's the director of the Center of Robotics and the Intelligent System, and he leads the video computing groups at UCR and working on the fundamental principles of computer vision, image processing, machine learning with the applications in cyber physical system, autonomous and intelligent systems. He has published over 200 papers in very prestigious journals and conferences, and he has published 2 books. One is Camera Networks, the acquisition of an analysis of videos over wide areas and person re-identification with limited supervision. He is on editorial boards of multiple major journals and the program committees of multiple conferences, and he is a fellow of IEEE and the IAPR. And he received his doctoral dissertation advising and monitoring work from UCR and the ECE Distinguished Alumni Award from University of Maryland. And his talk is on the topic of scene understanding for safe and autonomous navigation. Thank you very much.
Okay. So is this okay, the way I've shared it? Can you hear it online?
Yes, yes, we can see that.
Okay, okay, good. Okay, so thank you, Goyo, for inviting me. So as Goyo mentioned, I'm in electrical computer engineering and computer science at UC Riverside. I've been there for about 20 years and lead a group of a relatively large group, currently about 30 students. Our group works on many things, but what I'll talk about today is specifically on some of the work that we have done recently on joint perception and planning in autonomous systems. So when you look at a scene like this, so this is from Cityscapes, as many of you probably recognize, there are many things going on, many things in the scene, right? So there is this person on the bicycle at a very corner at the edge. There are vehicles, and you need to be able to detect these objects. You need to be able to understand the scene, and you need to be able to plan in the scene. So there are multiple tasks that are happening at multiple scales over here. At the lowest scales, there is the problem of detecting objects, detecting vehicles, detecting people, tracking them, and so on. As you move to a higher scale, there is the problem of being able to understand the scene. So to be able to understand there are trees, there are cars, there's a crosswalk, and finally there is a decision-making and planning problem, which is given an understanding of the scene, can you now make decisions? Can you navigate through them? This is one example, but as I'll show towards the end of the talk, there are many other situations where many other use cases where similar scenarios arise. For example, a robot navigating through an indoor environment towards a particular goal. The scene may be different, the objects may be different, but the basic problems are very similar. You have problems at least at 3 different scales. One is at the level of individual objects, then at the level of groups of objects in the scene.
The reading is not a movie. How do you share?
I shared. Let's stop the share.
Let's retry.
Okay, so let's just share. Let me share this. What happens? I do it in this mode. This is moving.
Yeah, this is moving.
I don't know. Shall I just keep this maybe?
It's an option.
Um,
Or you can find it, maybe you can find it. Duplicate on the screen.
Sorry.
We can duplicate on the
So
screen.
it is showing up here properly, right? So it's not a problem with the duplication. Okay. Screen settings. Duplicate extension.
Or you select.
No, but then this is going to show up here. That's not the right thing to do. Yeah, so I am sharing the screen. Okay.
You have share. You have share.
Okay, so you're suggesting I share the whole screen? I can do that, yeah. Okay. Yeah, now it's showing. Yeah.
Here is not actually on Zoom. It's on the same screen. Actually, on Zoom it's showing this screen.
Oh, that one I think can be fixed here.
Just
yeah, this is. That can probably be.
Yes. They are.
Okay. Now it's. I think I can make this. Can you go to the Zoom now?
Sure. Yeah.
Yeah. Let me just leave it with this.
Okay.
This is fine. I don't think I need the next for the next slide. So where was I? Yeah. So if you look at this scene, there are okay, let me. I'm trying to regroup my thoughts here. So when you look at a scene like this, and your final goal is to be able to make decisions. So, for example, to be able to plan through the scene, there are tasks that need to be done at different levels. You need to be able to identify the individual objects, the vehicles, the people, and so on. You need to be able to reason about the overall scene. That is a crosswalk. There are trees, cars, and there's a relationship usually among them. And finally, you need to do the decision making. And if you think about this, there are problems at multiple levels, and at least there are 3 levels. The way I think through this is you need to think about the individual objects, you need to think about groups of objects, and then you need to do decision. And we have been working on all of these problems over many years, and there are multiple students who have worked on this, and we have been fortunate enough to have had funding from different agencies, and we have collaborators from different organizations. So I'd like to acknowledge all of them who have contributed to this. They are currently working in good places. and also funding from NSF, DARPA, ONR has funded a lot of this work, and also we've had collaborations with Google, MERN, Cisco, among others on this work. So I'll go through some of the tasks that I outlined, and I'll also present an overview of some of our results along these lines. I'll organize the talk into 3 parts, starting with individual objects. How do you analyze them? How do you robustly analyze for example, the location, the pose of every single features on every single object. Then we look at groups of objects and scenes, and we'll here specifically talk about multimodal scene segmentation and scene graphs to understand the scene. And then finally about decision making. How do you adapt learned models to different dynamic scenes? And how do you do navigation once you have obtained an understanding of the scene? I'll start with the first one, which is the robust person detection and representation. And I'll specifically talk here about silhouettes and pose estimation. There are many other things like face recognition, for example, but for most navigation tasks and planning tasks, you probably do not need to do face recognition. So our focus here has been, how do we estimate and learn representations of individual objects? And especially, how do you do that for people? There has been a lot of work on silhouette estimation or pose estimation that I assume many of you are familiar with. What we have looked at specifically over here is, how do you obtain this in a robust manner? And this, in spite of all the work that is out there, there are very important challenges. So a lot of this was funded through an IARPA program, where data was collected in very natural settings where there was occlusions and so on. And it's actually not easy to get silhouettes and pose in many of these situations, even using state-of-the-art methods. And I'll show you some of the challenges that we face. So if you have a person and there is significant occlusion, can you obtain a robust silhouette of that person, which is necessary in order to be able to do some downstream tasks? If you just take the state-of-the-art silhouette estimation models, they give you results that are extremely noisy. And here is an example on the top. What we proposed here in some recent work that we have done is, how do you combine these silhouette estimation or segmentation models and obtain with pose estimation models, which can give you more robust estimates. Pose is much more robust to environmental issues, for example, partial occlusion, as compared to silhouettes. And you can now combine pose and silhouettes in order to obtain a better estimate of the scene. So the way we did this, so you have a pose estimation model, and that gives you a pose, and you have a silhouette estimation model that gives you a silhouette. And this particular approach that we had on POISE, which is a pose guided silhouette estimation, is to be able to combine the two. Pose does not give you a good estimate of body shape, but silhouettes do. And the question now is, how do you combine these two together in order to get a better estimate of the overall silhouette of the individual? And once you can get that estimate, you can now apply that for downstream tasks, whether it's recognition, whether it's tracking, and so on. So this was, so the details you can find in our paper that was presented earlier this year. But this is the overall high-level idea. And in order to evaluate this, we generated some data with significant occlusions. Isn't the video playing? Okay, we generated data with significant occlusions, and then we tried to see what is the, can we get a good silhouette from here? So here are some results. These are qualitative results. I'm not going to put up tables in any of the presentations. If you are interested, you can look at the paper. I'm just putting up tables with different methods and comparing and then showing that, okay, ours is the best. I don't think it's a very informative way of looking at things. So I would rather present qualitative results. They are anecdotal, but they do give an intuition as to what is working, what is not working, and how is this happening. So let's say we take Deep Lab V3 for segmentation. And these are in the second column, you have the segments that are obtained here. Okay, anyway, on the second column, you can see the silhouettes. Now we get the pose estimate, and from the pose, we generate the silhouettes. And if you look at the fourth column here, you see that this doesn't have a body shape. And these examples we picked so that you can get that idea. And then when we combine the two together, the pose and the silhouette estimation, we are able to get a much better silhouette overall of the individual. And this ultimately leads to better performance on downstream tasks. Now the question is, where does pose estimation come from? How do we do the pose estimation? And what are the challenges in pose estimation? Overall, pose estimation has been handled in two ways. One is a top-down approach, the other is a bottom-up. In top-down approaches, you essentially try to get the pose from a collection of features, while in bottom-up approaches, you do detections first, and then you get the features, and then you try to estimate the pose. And this is important for many, many problems. For example, action recognition, we need to get pose. The methods that have been successful, very understandably so, has started with synthetic data, because here you can get ground truth. Well, where else are you going to get ground truth from, where someone will mark each and every key point on a person? Synthetic data, it comes for free. The problem is, because of the domain gap, when you go from a model trained on synthetic data to real data, performance degrades significantly. And the question is, how do you bridge this gap? So, and then also, in order to bridge this gap, it has to be done in an unsupervised manner, because you cannot assume that on the test site, on the target data, you have labels, you have annotations, because if you had those annotations, you might as well have trained your model in the first place with that. So so there are ways in which this has been addressed in some of the papers, which is the unsupervised domain adaptation, where you take a model that has been trained on synthetic data. If you apply it to the target data, on the left is an example of the kind of results that you get. On the right is what you get after adaptation. The question is, how do you do this adaptation? I'll talk about that in a minute, but in order to do this adaptation, there are some other issues that we specifically focused on. We focus on privacy issues. That is, I do not specifically have the source data. So there could be models that are released, and can we use those models in the target domain without having to use all of the data that is also being used to train those models? A lot of work in domain adaptation, if not the vast majority of work, essentially uses the source data. And there are multiple challenges to this. One is it cannot use models where the source data is not available publicly. The second challenge is the memory constraints. If you want to be able to use all of the source data, you might be talking of gigabytes of data now that you have to use in the domain adaptation process. So in the paper that we published in ICCV last year, we asked the question that, can we take pose estimation models trained on synthetic data and show how they could be applied to target data without having any of the source data set that is available? So we have just the trained model and we have the target data, no source data set. And how do we adapt these models? And the results that we obtained they were almost as well as, in fact, qualitatively, there is almost no difference. Quantitatively, there is a couple of points difference. Qualitatively, there is no difference in the results that you get when you have the source model and when you do not have the source model. So here are the results, some example results at the bottom. And how do we go about doing this? So the basic idea is not different from what has been used for domain adaptation when the source data is present. So this is a classic student-teacher model using an exponential moving average to train the teacher from the student models. What we introduced over here in order to compensate for the lack of the source data. Remember, this is domain adaptation. We do not have the source data. So what is it that we can do in order to compensate for the lack of the source data? And this is where we introduce the idea of using a pose prior, essentially a pose manifold, which captures how poses look in general. And this is possible for human poses because there are only certain body configurations that are possible. And there are many that are not realizable. So this pose prior models the manifold of plausible poses. And from that manifold of plausible poses, this can be used as a constraint to estimate the pose in the domain adaptation setup. So you start off with a pre-trained model, no source data, and you adapt the model to your target domain. Since you do not have the source data, you need to have some constraint. And one of the ways in which we impose this constraint is using this manifold of poses, of plausible poses. And this prior, which is trained as a regression model, can be used as a regularizer in order to get better estimates of pose. So this allowed us to obtain an unsupervised domain adaptation framework for pose estimation without source data, and it gave us results almost as good as the state of the art. Again, we worked with this Breyer project where we had data at different distances of individuals. So there was data at close ranges and data up to 700 meters, data from UAVs. And we start off with the source model. And on the first column in each of these, you see the results, and they are absolutely junk. In the second column, you see the results with domain adaptation, with the source data present. And in the third column, you see the domain adaptation results without the source data present. And in almost every single case, you cannot make out any difference when the source data is present versus the source data is not present. And this is something we have seen in many other problems that we have worked on in domain adaptation without the presence of source data. That the performance is almost as good as if you can have. We have covered, so what I've talked about very briefly is our work on individual object level. You can do similar things for vehicles and so on, but specifically doing this for people is in a way very challenging, probably more challenging than doing it for vehicles. And I find it quite interesting. So that's what I talked about. Now let's move on to the next higher level. Let's say I can detect individual people, I can track them, I can identify their poses, I can compute the silhouettes, but that's not enough to be able to understand the scene. I need to be able to get more information. And here I'll talk of two things. One, or I'll highlight two of our works here. One is on multimodal semantic scene segmentation, where you identify different objects in a scene and you want to segment it out. And the second that I'll talk about is on dynamic scene graphs. And from there, I will then move on into making decisions in dynamic scenes. So we all know what the segmentation problem is. So I have a scene, I have a segmentation model, and I want to be able to get these pixel-wise labels on that. So that's the classic semantic segmentation problem. And I train a model. Again, there is a domain gap issue. Semantic segmentation has also been trained a lot with synthetic data, again, for very natural reasons, like who is going to give you pixel-wise annotation? But if you synthesize the scene, you get this for free. The question is, how do we adapt it to novel scenes and bridge the domain gap? And that is, again, the domain adaptation problem. And we've worked on this for many years, and I'll actually present, I'll start off with work that was a couple of years earlier, and then talk about work that we've done recently in this domain. So you want to adapt a segmentation model, and you do not have annotation, or you have very minimal annotation. One of the things that we looked at was, can we work in a situation where there is some annotation, but the annotation is at the level of the scene, not at the level of the pixel, or even at the level of identifying some points on the scene. You just know that this scene has these objects in green and does not have the objects in red. How do you use this very weak level of labels in order to get a better segmentation? And we showed in work that was published probably 2019, 2020, that it was possible to do unsupervised domain adaptation with these weak labels, and here are some results from there. So even with these very high level labels that a scene has a car, has a tree, but not where it is, we are able to get almost state-of-the-art results. Moving forward, more recent work that we presented at last ICCV looks at a more interesting problem, which is a cross-modal semantic segmentation, but with two unique characteristics in this problem. One of them is that this was a multimodal segmentation problem. However, that is, you have RGB data and you have, let's say, LiDAR or thermal imaging and so on. However, we do not have multimodal trained models. So the reason for this is simple. So if you have multimodal data, let's say you have image IR data and an RGB data, do you go back and obtain training data that is also multimodal? Doing that is extremely expensive. However, we do have pre-trained models that are unimodal. So you have unimodal models that are, let's say, for RGB, and you have unimodal models that are for depth or for thermal images and so on. So can I now combine information from unimodal models that have been trained separately and independently, but of course on somewhat related scenes, but have been trained separately and independently, and apply them on target data, where the target data is now multimodal. So I have an autonomous vehicle that has RGB and LiDAR, let's say. I have a model trained for RGB, I have a model trained for LiDAR. These could have been trained independently in two different countries. Can I use these unimodal models for my multimodal segmentation task? The second thing, the second assumption that we relax, again, goes back to the source free setting. I do not want to carry along all of this data in every single scenario. Can I work in a situation where I do not have the source data, I just work with the models? Again, it could come in for privacy reasons, but even if privacy is not an issue, it could come in from memory constraints and computation reasons. So how do we improve performance where we have unimodal models trained independently on multimodal data like RGB and LiDAR? So this was a problem there. Now that I say, I actually missed one of the acknowledgements. This was work that we did with the Army Research Lab, who are very, very interested in this problem because they have vehicles with multimodal sensors on them, and they don't want to go back and train all the models in all the different combinations of sensors that you have on the target site. And here, so we showed how we can adapt unimodal models to be able to add new sensors. So one of the advantages of this is if you now have, let's say, an RGB and a LiDAR, but you now want to add a thermal sensor to it, you don't have to go back and now capture training data and train the models. You can have separate training data and you can still combine them together. And we don't need to spend time and resources managing the source data sets. So the reason this works is that, so you have unpaired data on the source side and the data is not even available. But if you look at, so you take these models and you obtain the outputs on the target data, and then you look at the agreement between the target data sets. So you have RGB and you have let's say thermal images, and you look at the outputs that you get on the scene. These are coming from two separate models. That agreement now can tell you how good you are doing. In a statistical way, if you now backpropagate through those models, you can adapt the multimodal model using the unimodal ones, because if you have lots of labels and lots of pixels that are agreeing, then that means that for those particular pixels, there is a high agreement and you can use that to update your models. On the other hand, if there is more disagreement, then that tells you that those are the ones where there are problems. And doing this and doing this approach in a principled way, we actually showed that you could take data sets that were collected, let's say, in USA and Singapore, separately on different modalities, and then you could apply them to multimodal data sets for autonomous navigation applications, especially in semantic segmentation problems. And here are some results from there. So this was 2D and 3D data. So on the top left is the ground truth, and on the bottom right is the 2D and the 3D data. The differences are not that visible qualitatively, but if you look at quantitative numbers, there are actually very big gaps. Once you, if you sorry, excuse me, if you work with the individual models, and if you do the fusion with the 2D versus 3D, versus if you just do the 2D or just the 3D, and the other aspect that we really liked in this work is to be able to work with unimodal models and transfer them over to the multimodal side. I actually was very happy with the ultimate results because it allowed us to work in different domains, autonomous navigation like this, but it also allowed us to work in some other projects on agriculture where, again, you have similar problems. You have depth data, or you have LiDAR, you have thermal images and RGB images, but we don't want to go back and train models separately for all of them. So the semantic segmentation is one part where you get all the regions in an image, but that is still not enough to be able to reason about it overall. And this is where some of our work on dynamic scene graphs comes in. Again, this is an area where there has been a lot of work. What we specifically focused on is on the dynamic nature of the scenes, and to be able to build scene graphs that evolve over time. And the other thing that we specifically looked at is the long-tail nature of the scene graph. So when you generate these scene graphs, they do very well on classes that occur very frequently, but on classes that occur much less frequently, the performance varies a lot. So if you have, so this is on a standard, the visual genome data set, and if you look at different classes, there are many classes which have a very small number of examples. Can your dynamic scene graph be able to obtain good results even in these scenarios? And of course, there are issues with noisy labeling, with temporally inconsistent object classification, and so on. And the question here is, can I still obtain an understanding of the scene in order to be able to reason through it? So this was work in the last CVPR that we presented, where the idea was, how do we obtain a scene graph where we have multiple classes where the number of instances is very poor? So how do we transfer knowledge from data-rich classes to data-poor ones? And the reason we can do this, or the hypothesis based on which we built this work, is that is to have mechanisms whereby you can have a memory bank. That is, if these are the highly occurring classes, and you have a few classes that are not occurring or are very rarely occurring in those scenarios, what are the relationships between the rarely occurring classes and the more frequently occurring classes? What kinds of features co-occur, and how do we use these kinds of features in order to transfer knowledge from the data-rich ones to the data-poor ones? And this actually prevents forgetting. So if you have a data-poor class, it does occur sometimes. But when it occurs, can I remember something about those data-poor classes that I can then transfer over when I see that class once again? And this allowed us to generate these scene graphs that were robust to the data-poor classes and that evolved dynamically over time. So with that, where are we overall? So we started off with individual objects. Then we moved to a higher level, a more abstract version of the scene, which is the scene, the semantic segmentation of the scene, the dynamic, the relationships between different objects, which help us to reason about the scene, and so on. The next step is now the final step in the process, which is to be able to do the planning. And this is where I will come to the reasoning part, and I'll show you how we can navigate through complex scenes once we have an understanding of the perception. So here we'll talk of two problems. One is to be able to adapt models to dynamic scenes. So if you have a scene that evolves over time, you need to be able to adapt the trained models you have. And you need to be able to adapt them not once, but continuously over time. And you have multiple models. So you could have obtained, for example, a semantic segmentation model, in sunny weather, rainy weather, snow, and so on. And then you encounter different kinds of weather over a long period of time. Or you could have had in an indoor navigation scenario, you could have had a room with a lot of lighting. You could have gone to another room with less lighting, and you could have gone to another room which might have a lot of lighting, but which has a very different look, like going from the kitchen to the bedroom, for example. And you need to be able to adapt these models dynamically as you encounter different scenarios. And this is a work that is currently under review on multi-source domain adaptation. So I have multiple sources and I have different scenarios that are evolving. How do I adapt these models? So one of the problems when you have adaptation is forgetting. And if you have dynamic adaptation, you have different scenes that occur, then one of the challenges you have is, let's say you adapt to a sunny weather, and then you encounter a rainy weather. What you have adapted to earlier, you may forget about that. So the question is, how do you not have this forgetting? And one of the things that we proposed is to have multiple models. And then from the multiple models, you choose the one that is the best to adapt to and for a particular condition. And you focus on adapting just that model so that you don't forget anything in the other models. So this multi-source adaptation allows you not to overwrite the source knowledge in the other models. And so you first find out what is the most closely related model and update only the closest related model. And this prevents forgetting. So whatever models you have, let's say a semantic segmentation model, you then adapt it dynamically to different scenes. And now that you have that, that semantic segmentation model hopefully gives you good results in that particular scene. And from here, we then ask the question, can I now do navigation in whatever scene we have? So the navigation problem is set up as follows. So I have a particular object, or I have an agent that is in a particular location, and I need that agent to go to reach another location 3. How is this location defined? It could be defined in many ways. If this is a mapped environment, it could be given as a waypoint. If this is, this could be in this particular example, I'll show you, it could be a sound source. It could be given, I'll give you another example where the location is given in terms of a visual description of what the agent is likely to encounter. So given these different endpoints, can the agent navigate through the scene? In order to be able to navigate through the scene, it needs to understand the scene. This is where the lower level understanding of the scene graphs, all of that could come in. However, scene understanding is not perfect, and it will, in my opinion, it will never be perfect. The question is, how can we handle situations where it is not perfect? And this is where a collaboration with a human could come in. And given the recent advances in natural language understanding, this collaboration can happen in a natural language. So the question now is, can the agent figure out situations where it is in trouble? Query an oracle, which could be a human operator, get feedback from the oracle in a natural language, which is what we are used to giving. We are not used to giving feedback, go to waypoint at this latitude and longitude. That's extremely difficult for us. But we are used to giving feedback, go to, as I'll show you a little bit later, to the bedroom, or go to the orange sofa, or something like that. And then the agent can figure out what to do based on a vision language map. So in order to do this, one of the ways in which you could do this is to learn a policy that is based on, or learn multiple policies, one that decides when to query. You do not want to query too often, because if you query too often, you're slowing down, and there is a cost to querying every time. So you want to decide when to query. And then you need to decide based on what to query. Right? You can ask the agent, the oracle for some help, and then you have to, once you get the feedback, you need to be able to come up with your navigation decisions or your planning tasks of where to go. So this was, again, a paper that was presented last year at NeurIPS, and I'll now show you, so it was based on this reinforcement learning strategy. And I'll show you a video where you can see this is the agent, this blue arrow. And on the left, you can see the scene and it is navigating through the scene. So this is the multimodal navigation. And you will see at some point, and I'll try to stop it at the right point, where the agent is confused. So, so it is over here, and you'll see the agent now actually going around back and forth. And at some point, it decides that it's better to query than to keep doing trial and error. Yeah. So at this point, it asks, and it gets feedback in a natural language, walk straight down the hallway. And using vision language models, and this is overall a mapped environment. So using vision language, it has an idea of what is a hallway. And it then figures out that that is the hallway, and it proceeds down that. So that the instruction is coming in a very natural language format. And that is something that humans are very used to. And then again, walk straight into the bedroom. These are things that all of us can give very easily without having to worry about waypoints and so on, which has typically been the way in which navigation has been done in robotics. I'll show you another example. And this is so the earlier was on simulation. This is in real life, in a real life setting. So let me explain quickly what you'll see. So this is a grid in our engineering building, and the agent will start from the top left corner, and it has a particular point it will need to go to. And there is a path that it plans out. It starts navigating along that path, and it encounters an obstacle. It actually will encounter a closed door. And at that point, it does do a replanning, but it's a very long path that it replans through. And it then goes and asks the human, so the reinforcement learning agent figures out that it's better to now query a human rather than following that path. And then it will query the human, and then it will follow that. And you'll see what the human's feedback is. Here you'll see the first person view from the agent. And this is actually a student of mine walking behind the agent, taking a view, a third person view, to give an idea of what is happening. So I will play this. And this is the agent starting to move. Okay, and and you can see over here where it is moving. On the navigation view, you can see how it is moving. And now it encounters this closed door. So its original plan was to move, and then it finally asks for the human for help. And the feedback was, go near the circular orange couch, and then proceed to your waypoint. This is again feedback that we can provide in a very simple natural language. And all of us can do that. And using a vision language map, it now knows where a circular orange couch is. And this was done in a very natural environment where there were other things going on. You saw some students leaving the lab and so on. You'll see other people also coming in and out. And now it knows where the circular orange couch is. So this is a mapped environment, but it is a dynamic environment. So it is initially mapped, but there are other objects that are moving around. There are people still moving around, but the static objects do not change. The doors and also do not change. And this is now moving through. So you'll see, so this is where it goes to the circular orange couch, and it realizes it's reached that point. And from there, it can now again replan and move on to waypoint 4. So, and we have done this and we are actually doing this in more complex environments now. And I will have some results probably in a week or two in far more complex environments also, where the agent gets stopped multiple times, it's confused, asks a human for help, and based on that, it then navigates, replans and navigates its way. So to summarize, the overall problem that we have been interested in, that we have been working on for a good part of the last decade, along with many funding agents and many of our collaborators, is this essentially this high-level problem of scene understanding and navigation within the scene. There are complex scenes. How do I navigate within? In order to do that, our focus has been on the scene understanding. When we get to the navigation part, I usually work with roboticists who are adept at working with the hardware and the robot, and I collaborate with them a lot. And some of the lessons that we have learned is, in spite of all of the work out there, low-level tasks still remain very challenging. There are still issues with detection and tracking in challenging environments. There are tracking softwares that work in many situations, but the same code does not work in many other situations. And so these low-level tasks remain challenging. Scene understanding, segmentation, so on, there is a lot of progress. Yes, we can get results with slightly higher MIOUs. I don't know how valuable they are in getting even 2, 3, 5-point increases in MIOUs for downstream tasks like navigation. But one of the things that we have found that does matter is uncertainty quantification. Can you say that this is an object, or what is the uncertainty with which you can say that? Like for a person, you never probably want to miss that person if this is an autonomous car driving. But for many other objects, it's probably okay to make some mistakes. So this uncertainty quantification is a big part. How well will a model do? And can you predict that ahead of time? And given a result, can you provide an uncertainty or a confidence measure of how well that does? And finally, planning that is robust to scene understanding errors. Assuming perfect scene understanding, which has been an implicit assumption in many planning tasks, is absolutely unrealistic. And we need to do planning where there are scene understanding errors and to be able to model for those errors within the planning tasks. So these have been some of the problems that we have worked on over the last 6-7 years, and I've given you a high-level view of some of this. There are at least 6-7 students who have worked on this, and we have projects where we are still working on some of these. They remain challenging problems and expect them to remain challenging problems for a long time. Yeah, thank you very much.
Okay, thank you. Maybe we have very limited time for 1-2 questions in the audience. Let me get started with one question. So it's very fascinating to see the vision and the language navigation. I guess we don't really want the human's instruction to be too frequent. Otherwise, that will give a burden for the human navigation, for the human. And in that case, in which scenario your robot will ask for the instructions?
Yeah. So this is where the reinforcement learning comes in. So there is a reward, so that if you ask a question and you get a good answer and you can plan, and you can replan, there is a reward for that. On the other hand, there is also a cost. So the reward has a negative part to it also, that every time you ask a question, there is a cost associated. So now the question, now is essentially it boils down to coming up with a policy of when to ask the question such that the advantage that you get from a good answer and being able to replan is, the advantage outweighs the cost of asking a question in the first place. And it's a trade-off between these two. It doesn't necessarily have to be a policy learning. I think it could be simply set up just as a much more simple optimization problem, but there has to be 2 parts to it that has to be modeled. And that could also come in from the training data itself. Like if you can train in some way that, given the complexity of a scene, can you now decide whether it's better to ask a question or basically to proceed by replanning?
Okay. Any other question from the audience? So for the source free part, actually, is there something like you have combined with few shot learning or no shot, zero shot learning, and
which part?
Source free.
Source free. Okay. We have, so this is not zero shot. However, for the source free learning, what we have is a completely unsupervised adaptation. So it's not zero shot in the sense that we are not looking at adapting to completely new classes. So it's still a dictionary of classes that is given, but it is an unsupervised. So everything we have done is completely unsupervised on the target side. We have never assumed any labels on the target side at all. But it's not completely zero shot in the sense that you have completely new classes. We have some work on open set classification and zero shot, but not in the settings of what I presented.
Okay. Thank you very much. We will have our last speaker. Time flies. Yeah. Let me introduce our last speaker, Dr. Vinod Kalutamani. No, here. Oh, you doesn't have the lecture. You don't have that. This one? Yeah, they only this one. This is my actually my laptop. Yeah. Otherwise, you can use one. Anyone has the adapter between your HDMI with the Apple's computer laptop?
What adapter do you need?
Apple's HDMI.
I have a USB-C adapter if that works. C probably not. Yeah.
Okay. No people have adapter for the Mac system. Otherwise you can use one. Yeah. You want to send it to me, or you want to use one? It's on Google Drive. It's okay. It's okay. It's empty.
You might share it. Yeah. It's my work. Thank you. This one. You try it.
Let's continue. Vinod is currently a principal scientist at Amazon AWS, where he leads the core AI research and development for several innovative research projects on Amazon smart shopping cart that leverage the latest advanced technologies in computer vision, machine learning, signal processing. Specifically, he has developed a real-time cart localization and the product location reinference system that lays the foundation for features such as product lookup, wayfinding in stores, and the localization for the centric advertisement, and a multi-sensor fusion system that infers shopper actions and maintains a shopping receipt with the stringent requirement on accuracy and latency to ensure a pleasant shopping experience. Prior to joining Amazon, he was chief scientist at T-Vision, where he led the design and implementation of vision-based activity recognition system on self-constrained platforms. And before joining industry, he was tenured associate professor at West Virginia University from 2008 and until 2018, where he managed several large research projects on multi-sensor system and information centric data distribution location services, and which are funded by multiple resources such as DARPA, Los Alamos National Lab, and he has more than 40 papers on prestigious journals and conferences. He holds a PhD in computer science from Ohio State, and his topic is mapping and localization in large-scale retail environment. Thank you very much, and please introduce research.
Yeah, thanks, Girish. My name is Vinod, and I'll be presenting about the mapping and localization in.
Oh, you haven't shared the screen yet on Zoom.
Share screen.
Oh, here from this side is not the correct screen. Oh, right now it's good. Here, it's good. Yeah.
Cool. Yeah, so this is a more product and business oriented presentation of how we do like localization and mapping for large scale data environments on something we call as the smart shopping cart or the dash card. So give a little bit overview of what the dash card is. So the dash card basically allows you to sort of like skip the checkout lines when you're shopping. So it's a card that's equipped with all these sensors, a weight sensor, cameras, and so on. And when you're shopping, it allows you to add things and remove things as you go, pick your items, and then it keeps a tab of what is on the cart. It identifies what is going in and out. It verifies things, and it keeps a tab of what is on the cart, what displays the live receipt. And at the end of a session, it basically lets you skip the checkout, verify the receipt, and pass. So that's basically the dash card. It's a multi-sensor system essentially. And it poses lots of unique research challenges. And it's sort of bridging all those research challenges with what is out there. So that's what we do here in this group. So if you can imagine, like, the problems that you see from the sensing side are like, identify when products are added or removed, whether there was a take or a remove, what is going on, and whether the whatever the shopper scanned, whether that matches with what was actually added or removed. So that's an interesting problem. There are weight sensors which tell you how much, what is the weight of the product. There are vision sensors that tell you whether something went in or out. So you got to fuse all of this. And then the real thing is, also in real time, present a feedback to the shopper saying, hey, if the shopper, for example, forgot to scan, you got to remind them saying, did you forget to scan? Did you add something without scanning and all this in real time? So that real-time interaction makes this a very unique challenge in terms of applying all AI technologies. But in today's talk, what we're going to focus on is another feature, another autonomous feature that the dash card provides, which is basically a location system. So this card is equipped with a location system, but basically, and our goals for this are to localize the shopping cart within a retail store. It's an indoor environment, and these are really large spaces, 40,000, 50,000 square feet. So you got to know where the shopping cart is. The second thing that we focus on is how to learn product locations within a store. There are products scattered around the store, and they don't often follow any specific system. The product can move around. So the idea here is how can you learn those locations dynamically without having to manually rely on somebody to change the locations? How do you automatically infer where the products are placed within the store? Then location is basically relative to some origin, right? So it's not enough to say that I'm at X, Y, which is 1,000, 1,000. You need to know where it is relative to the structure of the store, what aisle it is, or what shelf it is. So you got to project the cart and product locations on a store layout map. And finally, you also have some algorithms to efficiently look up nearby products. So that is the system that I'm going to be talking about. So what are the applications? Once we have such a card in the location system, you have lots of applications, right? So you can have this, this is a search and navigate to products. So you can search for your favorite products, and then, you often have trouble in the stores looking up where items are. So this will give you a direction as to, where that product is. So on this picture, the green arrow that you see on the left side near the produce is basically the cart's location. And then where the bananas are posted. So this is like, then you don't have to ask an associate as to where the product is. So that's a very useful feature to have if you go shopping in a large store and you cannot find a peanut butter. Right? And then you can have all of this from a merchant's perspective, a location-aware product recommendation. So, you're walking through a specific aisle, you get advertisements for that specific products that are near you. So that's what you can realize with this. And then adding produce, like, for example, if you want to, these products don't have barcodes, right? So often they have 4-digit PLU codes. And entering those PLU codes onto the screen is sort of cumbersome. So what we can do here is once you go in to say that you're adding a produce, it sort of selects automatically the nearby items for you. And then you can just click on them, and then you can add those items. So basically, because the dashboard knows which products are nearby. So this is an example of of these features in a store. So you'll see that the cart goes and there's onions nearby. Then once you press the PLU button, you see all of the nearby products around that cart, and that makes it easier for shoppers to just pick it and add it into the cart. And then finally, we can have all these zones that are mapped inside the store. One example is a checkout zone or a store exit zone. It basically allows shoppers to walk through that specific area and it automatically checks them. It can also act as a fraud protection because, if you did not pay and then you exited the store, you can create an alert. So you can have all of these zones. You can even have zones for, like, say, alcohol sections or things like that. Or so you can map this out with this location feature. So it enables all of these features and many more that you can imagine. So that's why we have this feature on the card. Now we focus on the technical side. So how do we bridge this gap? We want all these features on the card. What are the technical constraints, right? The first thing is that there's a limited power budget in the sense that these cards are battery powered, and stores would like them to run throughout the day, right? So the card battery is expected to run for the entire day. So this means that you cannot have very computationally heavy algorithms running on them all the time, right? And the computational cost is also, driven by cost and battery cost, right? And then these cards are sort of pushed by humans, so they don't have a deterministic motion model like a robot. We don't know the exact speed or acceleration at which they're going. So simple solutions that only use IMUs probably will not work here. And then large store formats. Basically, these are extremely large areas that we're to map. And some stores that we could even exceed 100,000 square feet. So our idea essentially is that that we use to solve this is basically we decouple the SLAM part from the localization part. So what we do is in step one, we use an offline SLAM solution to create a map of this entire store. Right? We did a structural layout of this entire store. And while we do that, we concurrently have a separate hardware that we're going to use for localization in real time. So we do not use the SLAM solution for doing localization in real time. We concurrently use another, potentially another hardware, a camera that we can use for real time. And in the step two, which is the real time, once this map is created, and then shoppers are pushing it around. At runtime, we match each query against a database to associate the query with a SLAM location. So that by decoupling these two, what happens is that in real time, we don't have to run the SLAM system. So we run a much more computationally efficient thing, which does just the relocalization, right? Now, yes.
Why not have the same hardware?
You could have, potentially you could have same hardware, but this gives us more flexibility. So, and I'll say that for the localization, what we do is we focus the camera on the ceiling, right? And so what that provides us is basically that the ceiling features don't change, and that gives us much more leverage in terms of not having to continuously recreate this database of real-time. So that's the thing. But potentially, you could have a SLAM system also using the same way, but this gives us much more flexibility. And there are also other advantages as well, which I'll talk about when I talk about the localization. Yeah. So that's what I said here. The camera hardware can be separate or the same. If the same camera, then only the SLAM footage is enough. But if it's a different camera, then we basically synchronize those two systems together. So every database image that we collect with the second system has a position on the map, right? And that was a good point. So basically, by having this, what happens is that we also have a very dense database that we can collect with the localization camera, which we can use it. That's the other. So that's basically the outline of my talk here also, which is basically that the first part is how we create this offline map. And the second part, which is the real-time GPU optimized relocalization by RGB image matching. So that's the second. Putting these two together, now the card knows exactly where it's in the store, and it's aligned to a specific structural data. Okay? And the third problem is like, how do you maintain this map over time? And finally, comes the fourth one, which is basically, how do you infer where the products are located? So this is all about the cart's location. The products are on the store, and how do we know where they are related to the cart? So that's a fourth problem. So the store map generation, we use a very typical SLAM solution. There's nothing like, nothing very different about it. So those basic elements are still the tightly coupled keyframe based, nonlinear optimization, loop closing and relocalization. And then finally, we also potentially could have a dense point cloud mapping. This is again optional. What it gives us is like a more clear outline of the structural layout, but even we could do this with a sparse point. So there's nothing very unique about it, but this simple solution alone does not work when we go to really large scales. That's the biggest problem. So this is the difference between sparse and dense map. Sparse map itself will work for our purposes in most cases because we clearly see what the aisles are and so on, but this gives us much more easier way to annotate those maps. But the challenge that we face is essentially robustness at scale. Like when you go to really large store sizes. So the problem is like, we ask these associates to collect this data for us to create the map, right? And the hardware that they use is not capable of producing this map in real time. Basically, we collect the data, we ship it, and then we create the map, and then we understand. Associates don't want to do this again and again. So it has to be like a one-time success, right? So you collect this data, ship it, and it better work. If you say that, okay, this time something did not work, we have to do it again, that's going to be really frustrating, right? So you want to avoid this repeated data collection. And so basically, there'll be drifts during the data collection. How do we account for that? Distract errors caused by motion blur, illumination changes, all of this. So an approach that we add on to the typical SLAM solution is a dynamic failure detection to stop tracking and then initiate new sessions as soon as we detect that there could be something wrong. So these are some of the ideas that we use to detect that there could potentially be a failure. This doesn't mean that there's always a failure, but whenever there's a potential for failure, we stop that session and create a new session. So some of the ideas that we can use to detect potential for failures are this feature co-visibility between frames. So basically, if the same feature is being visible across multiple frames, so we then stop that session, right? The number of 3D track points or the ratio of newly detected features, right? So these are all indications that, the cart is probably looking at a very featureless scene. And that means that the track errors are going to accumulate. So we stop the session and create a new session and then merge that. Right? The divergence based on frame to frame distance is essentially like we have an estimation of how fast these carts go. Now, if the track suddenly jumps way more than what is expected, we know that there is some divergence here. So again, that's a potential that there's some failure to stop. So this failure detection recovery, we add on top of the typical SLAM solutions. So here we'll see that, we'll suddenly encounter a situation where there's a plain wall. And this is a place where track errors could diverge. So basically at this point, we create a new session. And then when it goes out, we start doing it again and snap it back. Okay. So this is an end-to-end SLAM workflow, and the addition that we have is essentially here the health tracking part. So if the health tracking is okay, then we go with the regular flow where we do the loop closure and proceed. Otherwise, we create a new session and then continuously do a loop closure detection with all the previously accumulated frames. So that's the addition that we have on top of typical SLAM. And that helps us really scale to large spaces in almost like one try. So we have associates that walk through the store, a 90-minute session on like about 40-50K square feet. And with this recovery thing, we are very successful with respect to creating this map at one. Okay. So this is the part where we have created this map offline. And while this map was created, we have potentially we could use the same camera, like you said, like about collecting these images of the different features that we see in the store, or we could use a different camera. Our idea is to use a different camera that's essentially focused on the ceiling, Mainly because ceiling has this, the ceilings of grocery stores, you will see like they are very, very industrial features, like, they have these pipes and lights and all those things. So that's perfect for us in terms of being able to identify where in the store we are. So we have a one-to-one correspondence with every point in the store and a position on this. So that goes to the second step. And this is a dense map example that we have for about a 50K square feet store. So now we'll talk about that image mapping stuff. Right? So the objective is that, we are given a database of spherical imagery tagged with XY locations that we get when we do the offline mapping. And then what we have to do is at runtime, we match any image that we get from the camera, and then identify where in the store we are, which is the closest map. That's as simple as that, right? So this is the part what I wanted to highlight, like what we get by having a different camera system for this. So what we do is, like, for example, if we use like 3 GoPros attached to a cart when you go, you get a really dense view of the entire store as the associate drives the cart through the store. So for every point, we have 3 different views, spherical of that. And then what we can do is we can project that into how it would look on the cart scan. So we don't have to rely on the cart's camera that we have, which is potentially a cheaper camera, which is not very expensive, and it probably has a limited field of view. But while data collection, we can have, like, for example, a 180-degree field of view camera, multiple of them, spanning through the store, collecting the ceiling views, right? And then we project that into exactly what the cart's camera will look like. And then we do a one-to-one correspondence between where we are. So that's essentially the idea. Now there are 2 options here, right? One is like a more modern way where we could use a neural network to map from image to location or image to post directly. It's certainly achievable. So initially we did not pursue that, mainly because, like, because it's less interpretable, and, like, for example, somebody puts a hand on top of the camera, then we don't know what that location is going to come out to be, right? So there are those risks of robustness. So initially we did not pursue that. What we do instead is a key point descriptor, very traditional kind of approach. But we port that to a GPU in order to make it much faster to be able to run on the camera. Right? So both of these are potential options that we can do. We can use a deep learning based approach, which directly maps from every image directly to a post, or we could do the descriptor. Okay. And for descriptor matching, what we do again is, like, it's a shift-like operator, but we do not have any scale or rotation invariance, right? And that makes it very easy to parallelize it on a GPU, because running this on a CPU would be extremely both power and time intensive, right? And the CPU is shared with so many different applications on the shopping cart. So you want to do this on a GPU. So that's why we do a very simplified version of scale invariant feature transform. And what we do is, in order to compensate for scale or rotation invariance, we have a very dense database collection. So we have, like, basically, once you have a spherical imagery, we can project it from all the potential angles that we have. And so we can avoid the rotation invariance that way. And the scale invariance is achieved basically because most of the times we are looking at the ceiling. So the reprojection for the different view angles is expected at runtime. So this is the overview of the method. When during the original data collect, we form this discrete set of linear projections as it would look like from a cart's camera. And then in real time, we compute the key point locations and descriptors. Then first, we have a hierarchy of, first we do some force elimination of where the cart is likely to be, and then do a fine-grained matching, right? And so that hierarchical method helps us, like, to further speed up. And for this, we can also use some kind of temporal filtering, which gives us a better measure of uncertainty. So we can, using the previous locations, we can sort of, like, eliminate many of the potential matching areas and then do the fine-grained matching. So that's the overview of what we do for the real-time image matching. So this demo will probably highlight that. So on the left side, we see the runtime query, and on the right side, we see what's the closest image that is picked up from the database. And then here we plot that location on the map. So using the SIFT idea basically makes it also more robust to illumination changes and all those things. Whereas like in a deep learning, we don't know exactly how these things would. It's certainly a work in progress, but yeah. Then very briefly, I'll cover over how we handle map updates. So let's say that the structure of the store changes, right? So, which is very rare. Like, what we are interested in just knowing where the aisles are, where the produce tables are, and so on. It doesn't happen a lot. So one approach, of course, would be to periodically resample and the store. We could get an alert saying something has changed, and then we just go and repeat that same process. It's a little bit cumbersome, but it's great for very infrequent structural changes. If things are not changing as much, there's no harm in it. If, for example, we hear that aisles only are moving once every 2 years or something, that's fine. So we don't have to do one thing. But if we have a situation where we have to continuously update, for example, the produce tables, they keep moving around a lot, right? So for that, what we could do is we could use a collaborative approach between the cards, right? So all of these cards, when they are operating in real time, they could keep sampling in a collaborative way, and then we could use that to recreate the map. So what we could do is basically we could use a relocalization error as an indication that something has changed, and whenever cards go through that area, they could sample more actively. So the proportion or the rate at which they sample these images would be proportional to whether they suspect that something has changed or not. And by doing that, what we can do is we can have this the system where all of these cards are collaboratively collecting data, pushing it to the cloud, and we can update the. So that's the idea we have for handling map updates when things are not when things are changing more frequently. And the last part of this is the inferred planogram, which is basically estimating where the products are located in the store, right? So now we know how the carts are moving and where the carts are in the store, but how do we know where the products are? Where are tomato ketchup or where are peanut butter? How do we know that? One way obviously is for stores to provide us that data. They keep manually updating whenever things are moving. Instead, what we do is we use an idea of where people buy products from as a clue to where they're posted, right? So every time somebody buys a product, let's say bananas or peanut butter, we keep a tab of where that purchase location is, and then we cluster those locations to identify where the hosted. So that allows us to learn automatically as to where the products are, right? So the idea is just to divide the store into cells and maintain a very simple idea, maintenance count of purchases per product in each cell. And then what we'll see is in the true posted locations, these cells will be concentrated with purchases. Whereas obviously people could purchase bananas from far off. You could park the car really far away and take bananas over there and buy it, but those will get outnumbered, essentially. So we could eliminate those and identify where we are with respect to, and it's automatically adapted to location changes. So if something moves from one place to the other, you will see that certain cells start decreasing in density and other cells start increasing in density. So automatically we can infer the product. So that's the idea we use to run this and maintain this in a continuous way. So this is an example of how it is. So the black dots here are the purchase locations, and the green dots are the inferred locations for the product. So what we have is we automatically learn that this specific product is near those. What it gives us is a very seamless way, because now when the carts go through that area, those products can be advertised, whichever is nearby. So it solves us a problem, because essentially what we don't really want to know where in the shelf they are, but rather which cart positions host that location. That's what we are learning, and that is beneficial to us because that can be used for all of these other locations. So that's how we do the product applications. Yeah, so that's the 4 part that we covered. So how do we do the offline mapping and then project real-time locations on top of the offline map, and then how do we learn product applications? So that's the and this is a real-time view of how this. So you have the carts moving on the right, and the locations that are being plotted on the map on the left side. So the cart cameras are basically pointed outwards, and we do the real-time matching. So this will be a good time to take questions.
Any question?
Yep.
Yes.
Thanks for the talk. I was wondering, like, in terms of most supermarkets that I've seen, kind of the route tends to be quite a repetitive structure, like maybe not quite locally, but globally over everything. Have you run into any issues with that? Like how dealt with that?
No, so if you look at these stores, the ones that are in ceiling, so there are repetitive patterns to our naked eye. Like, we feel like there are these pipes going, but incidentally there are these, because the field of view is also wide, you have distinguishing features at these points. So that's what we are learning. I mean, that was our initial worry too, that this which is but using the ceiling really helps a lot. Side views, not so much, because the shelves are like, they can constantly be changing. That's what this fixes. Yeah.
I saw that you are using the image matching to kind of convert the kind of visual information to the localization to the location, right? So and also I saw you also use some depth information. So why not just use the kind of the matching the point cloud, like using kind of ICP to do that? And also like you also mentioned you use like RGB depth and the ambient data, right? How do you do the kind of substitution? I know there are many substitution algorithms. And how do you select the best one for this case? Thank you.
Yeah, so the expensive sensors that we use, like the depth camera, those are all offline. And so that's only for the initial part where we collect the data to create the map. We want the cards that are used in real time to be as low cost as possible. So there we use just one camera. There is nothing else. And so we use the image matching from that camera to get the location. Whereas the maps are pre-computed using a different equipment altogether. And so that's how we are here. So that's why they are separate. Thank you.
Thank you for the talk. This was a really interesting product. I have a few questions that I learned myself to a couple. It sounds like you're doing global relocalization every time. Is that right?
The relocalization is global, yes. It's exactly one map that we get, and the database will be mapped to a position on the slide.
I see. Is there a reason you haven't considered visual at all?
Yeah, so purely visual automatic. Yeah. So that's definitely we can do on top of image matching. But visual inertial odometry, if you want to use it in real time, at least on the CPU, it's going to be very intensive. And we want to minimize the CPU usage as much as possible. So that was the real motivation. I can't disclose exactly how we do it on the GPU, but the main key here is that image matching part is entirely offloaded to the GPU. And so that's what fetches us the advantage. Now, potentially, yes, we could, if we can squeeze in visual inertial odometry on the CPU, that would help a lot, because then we only need to do image matching once every certain interval and then cover it up with VIO. It's definitely feasible if we have CPU space.
Okay, so it's a combination.
It's a combination that we could use. Yeah.
And have you considered using learned features as opposed to say?
Yeah, so that is certainly a topic of exploration. It is, like I said, our main concern originally, before we wanted something to get it to work, is the robustness aspect. How does it handle illumination changes or sudden changes and so on? So, I mean, we can work through it. We have some ideas to work through it, but yeah, definitely we can.
And our last question for the mapping, have you considered adding a LiDAR to, since you have separate mapping equipment anyway, to handle that failure?
Once again, it's a frugality concept. Like, try to keep it as low cost as possible. That works. So, yeah, so we want to avoid that. So, I mean, camera plus IMU works for our purpose, right? Or even if it's a sparse point cloud, that's enough for us to get a layout of the. That's what we are interested in.
Any other question? By the way, how many stores has been deployed with the card?
With the card, we have about 40 stores. 40.
Yeah, the number is ever increasing because we're launching almost every week. At this moment, we have 50 plus stores and the managers across the United States.
And we also have a demonstration of the card tomorrow until Friday.
Yeah,
booth
so
number 152.
Friday, around noon time to the afternoon, we are showcase the advanced card in the community. So feel free to come in, take a look at the card and take a look at how small the camera is for localization. Take a look at how small the battery is for all of us. So it's very confident how the thing is, but the team comes with constraints which right not like the big scale big slant or big scale LiDAR based approach, because we're actually constrained on cost, compute, power.
Okay, if no further question, thank you very much, Vinod, and this is actually this ends up our whole day's workshop. Fantastic 9 keynote talks, and including industry as well as the academics. And thank you very much for your attention. And I want to ask everybody's opinion. Do you want to get a group picture together or something want to disappear immediately? I'm thinking we can get a group picture to get together somehow, and as a memory somehow. Maybe we all of us can come to the front.
Who will take the picture? Who will take the picture? Should I take the picture? From our experience, most stores, they always show me where the product is. That's why our prototype one. It's not better. If you look at your nearby grocery store, you probably will see that the shelves and then the locations are almost there. Yeah, they just shifting. But you are okay with the products you got? Yeah, we can learn from images because the image has to be matched and can be uploaded. Yeah. Maybe we can move over here, then we can do that. Sorry.
Take the images of product function and match them. Can really blow up.
Right. Yeah.
I have to do one for the rent.
No. Yeah.
Unless you have a really hot.
Yeah, I think.
Yeah.
You wanna move closer, everybody?
Oh,
Get the head. 1, 2, 3. Smile.
Thank you.
Okay, great. Thank you very much. Yeah, sure. Thank you. I hope you attend most of that because I was like,
yeah, I didn't
part of this.
Yeah, so product we are not Google, we are kind of luxury. I just want to develop a kind of VIL, like the visual LiDAR kind of SLAM kind of things. Yeah, like we try to kind of match kind of one cloud. I saw that you just match image, right? That implementation.
For the point cloud method, it's a little bit hard if you want to go in such a big area.
And you have to do all, like, I worked on clinical matching before.
Yeah.
Most people, like classical method using ICP.
Yeah, ICP.
So you do a local kind of, ICP matching.
Yeah.
You get a rough orientation.
Yes.
And then you do refinement. Refinement comes down, extracting features out of clinical.
Yeah, yeah.
Yeah.
So is that kind of too consume too much power?
Yeah, for getting the point cloud in real time, you can need the same hardware that you used before.
Nobody has
Right?
processed it. I mean,
That is harder, that makes it hard. Car, you want to keep the camera on board,
Yeah.
You only RGB.
Yeah.
But to generate the point, we need other kind of LiDAR.
Yeah.
That's really much more expensive.
Yes.
Which is why we are not.
Yes.
Yeah.
But if we can,
Absolutely.
if we can afford it, do you think it's more accurate? Like,
Accuracy would be pretty consistent. We're also getting like, for the image,
You don't have as many.
the image matching, that might be more accurate. Might be.
Our customers are really expensive.
If you're like, it depends, like, if you have like.
Their costs,
Half of it to about two.
we have LiDAR.
Changes. Again, because like, if you're something that's not very significant.
Yeah.
It can snap back. But the point of maybe a little more.
yeah, I read some paper. They kind of like someone use kind of visual input as kind of a system for the LiDAR matching kind of thing, or LiDAR can the visual matching kind of they all kind of that, and also there is kind of wire smoothing and matching. There is a people there, like maybe Lucas, someone like do that without matching. It's kind of like kind of using the factor graph, kind of do the kind of factor graph optimization of each data source. Like did you do that thing?
That's for the slam we did, not for the real.
Oh yeah. I mean that's
It's a very standard.
Yeah, we have a similar problem that we already have.
Failure detection, make sure that it runs smoothly in one. Rapid correction is what is.
Are there any like open source?
And office, try the office library. That's what we built on top of.
We don't want the car to roll it down because of the hardware. That's why we choose those.
Yeah, we have a similar challenge in which we can't really change hardware and it's like a maintenance issue where you have different versions, they just like lots of.
Getting the job done, 90%. Okay. And even if it's like it's very irrespective of like which sensors you have.
Yeah, I do as a
Almost like similar kind of case.
Okay.
That's why we are helping maybe teaching them.
I see. Okay. Thank you.
Yeah.
Yeah, I would have.
I'm good.
Yeah.
I'm doing kind of mobile robot navigation. Yeah, but I'm doing an outdoor setting. It's not indoor setting. Yeah. But I'm also a PhD student at UDA. Like last year I did a class scientist to intern at Amazon Robotics.
Okay.
You guys are from Amazon.
So for outdoor, what is your use case like? Autonomous driving or?
Yeah, kind of autonomous driving, but we are doing kind of data center automation. It's kind of data center campus.
So why outdoors data center? Not most data centers are.
They have a campus there.
Oh, I see. So you want to transfer things between buildings?
Yes.
Okay.
Yeah.
Then I think you can afford for LiDAR.
Yes. We have everything. And there's no frugality.
Then you can use more powerful GPU.
Yes.
You probably can power by more batteries.
Because
you also have motors, right? You need to drive those motors.
Yes. And we use the Jetson to do that.
Yeah. Our budget for localization $75.
Less than $100. That's what I give you the task. Less than $100, you need to solve it. That's it.
What board are you using? You have a GPU.
So this is the Jetson.
That comes with it.
We're switching. I mean,
I was very careful to not reveal it.
no, what I'm saying is we're switching between NVIDIA and Qualcomm for every generation.
Not painful, like realizing what I'm Qualcomm.
It's also a maintenance
from the television.
Correct.
Or your.
So you also use Gatson things, the Gatson orange.